Hello.
Director needed for the তো তাহলে আমি ওইদিকে চলে যাই।
না আমি ডিজাইনটা করে রাখছি। ওটা ওখানে কাল হয়ে যাবে তো।
এটা কি মানে যে যখন কথা বলে তার কি ঘুরিয়ে দাও?
না 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 এটা ঘোরানো যাবে। হ্যাঁ সেটা করা যাবে। মানে ক্যামেরাটা না স্যার
I can speak from here.
Yes sir, yes sir. That is the mic.
I don't have to bring it closer to me.
No need to. It will capture from
Okay. I think you will go with the speaker and all. I mean, first speaker at least, second speaker I may introduce. Good morning. When should we start? Madam. Good morning, everybody. At the Indian Association for the Cultivation of Science, we are observing Science Day today. Science Day was formally announced in the year 1987. I think it started from that, coinciding with centenary year of C.V. Raman, although the significance of the day was to remember when Sir C.V. Raman and his co-workers formally announced the discovery of Raman effect phenomena, which was very different from fluorescence spectroscopy. And this was made known to the public on this day in the year 1928. It was the idea of National Council of Science, Technology and Communication, which was established in 1982 to commemorate to this day as a National Science Day. And from 1987 onwards, we have been observing this. Today, we have arranged a number of programs to celebrate science. There will be lectures given by leading experts. And at the same time, we will have some programs where students will participate. And now I would request Professor Srivastava to introduce the first speaker of the day, that is Dr. Nina Gupta.
Thank you. Well, I take great pride in beginning the technical session of the National Science Day celebration, as well as the Golden Jubilee of Department of Science and Technology, organized by Indian Association for the Cultivation of Science. I am speaking from a hall of IACS, where the spectrography is right there in that corner, used by Professor C.V. Raman, on which he did his Nobel Prize-winning experiment is kept. India celebrates Indian National Science Day in honor of Professor Raman, who did his famous work at this institute at IACS. So, ladies and gentlemen, welcome to IACS. Our first speaker is Dr. Nina Gupta, who currently has a permanent position in ISI Kolkata. Nina works in a central area of mathematics, which lies at the intersection of commutative algebra and algebraic geometry, called affine algebraic geometry. However, at the end of the day, she plays only with polynomials, one of the most basic objects in mathematics, which even school students know. Nina created a sensation in the world of commutative algebra when at a very young age, she solved one of the most difficult problems called heuristic translation problem in the area, which had defied all the experts in the area for over 7 decades. Nina has won numerous prestigious awards and honors, which will take a long time to list. However, I must mention that so far, she is the youngest Bhatnagar Prize winner at the age of 33 and little past 33 or before 34. So she is the youngest Bhatnagar Prize winner in mathematical sciences. I am very proud because she attended numerous courses and seminar series run by me at ISI. His PhD guide is illustrious algebraist and historian of ancient Indian mathematics, Professor Amartya Kumar Datta, who is also present in the audience. So Nina, please start enlightening us about mysteries of polynomials.
Thank you, sir, for this warm introduction, and thank you very much for this kind invitation. It is indeed a matter of privilege and pride for me to be here and give this talk on the National Science Day, which again is in the honor of Professor C.V. Raman. Today, I will also like to mention my tribute to Mahindra Al-Sarkar, who founded this institute, the first ever institute in India for basic fundamental science. So we are really grateful to these peoples who thought about our country, and of course people like C.V. Raman, who showed us that we can do something very great, something which is not routine and so now I'm sharing my screen. I am also indebted to Professor S.M. Srivastav. He said that I attended many of his lectures in ISI seminar series. In fact, I have learned a lot from him, and I'm really grateful to these peoples in ISI who taught me at a very young age when I probably knew nothing, and he brought me up to this stage. So thank you, sir. And so today we will talk about mysteries of polynomials. But before that, I will start with a quote from C.V. Raman. So C.V. Raman in this quote has trying to wake up us to saying that we need a spirit of victory. We as inheritors of proud civilizations, we have to come up and do something great so that our country rise. And so we have to come out of this defiant spirit and achieve something great in the history. So with this tribute to C.V. Raman, I will progress. So now this is another Indian mathematician because it's a National Science Day, and I should pay tribute to our, he is the person behind our area, Professor S. Abhyankar. So he promotes the education of polynomials and power series, which sort of have been surpassed by many technical things today, which we do in research, but he was the one who once fascinated by the powers of polynomials and power series, he wrote a poem, and these are the two lines from his poems. Polynomials and power series, may they forever rule the world. So let me just say that polynomials and power series are this kind of polynomials we have been seeing from very early in our school days, right? And power series also is not something not new to us. So we have been seeing this right from our school days, and because they are as basic in mathematics as natural numbers. In this, what's the peculiar good thing about this is that we can add any two polynomials, we can add any two power series, so subtract, multiply, and multiplication of two polynomials and power series is again a polynomial and a power series. It was Professor Isaac Newton who had initiated or studied the polynomials and power series in 17th century, but in India it was studied well before that. In 1628, Brahmagupta had defined the algebra of polynomials. He discovered that this set of all polynomials have a structure where we can add, subtract, and multiply. Again, in 14th century, we have Madhava, who gave the power series expansion of the trigonometric functions. So if you remember, we have seen this in our high school days. And so in some sense, it is there in our blood. We know how to, but there is something inherited, and we have been doing it unconsciously without even understanding what is it. That is the addition of two polynomials or the multiplication of two polynomials, and the subtraction of two polynomials is again a polynomial. So just let me put it an analogy with the decimal system. So we know that our decimal number, any integer, how do we write it? We write it as an minus 1, a1 and a0. But we as a mathematician, we know it is nothing but sum of elements of this form, right? Any integer is a polynomial in this form, where this a0, a1, ai's, they are all integers lying between 0 to 9. In fact, suppose we have a number like this 2108. It is nothing but 2 into 10 to the power cube, 1 into 10 square, and 0. Of course, there is no coefficient. So 0 coefficient with 10 and 8. But in decimal nomenclature, we write it as 2108. So if we carefully look at this decimal system, our decimal system, then this generalization to polynomials is a very natural concept, which is indicated in a expression, in a quote by Newton in 17th century. So just let me place before the quote of Sir Isaac Newton. He said that computed with numbers, which we have been seeing for years, are very close, has very close similarity with variables. And he said he was amazed that it occurred to no one to fit the doctrine recently established by decimal numbers in fashion to variables. So as we know that this decimal system is a gift to the world from Indians, and so Newton was saying in a very sarcastic way, surprised way, that no one thought about the generalization to polynomials from number system. It is not true. In fact, in India, the Brahmagupta had discovered all these things in 6th century. Especially since the way it is open to more striking consequences. For since the doctrine in species is the same relation to algebra that the doctrine in decimal system has to arithmetic. So it's operation of addition, subtraction, multiplication, division. So of course we don't know how to divide two polynomials or to divide two numbers. We get
Yes, Jubilee,
yes. So we get it generalized to rationals, functions, root extractions. So let me just so this quote has been taken from this treatise of the methods of series and fluxions in 1671 of Isaac Newton. Now, so this lead to the definition of rings and fields, which probably this term will be used, but it's not so serious. So let me just introduce. So this definition of decimal system or this number system or this polynomials lead to this definition of rings. So a ring is a set where we have the concept of addition, subtraction, and multiplication. So I just won't get into the technicalities of the definition, but give you some examples. So the set of all integers, that is a ring, because here we can add, subtract, and multiply. The set of all real numbers, or the set of all complex numbers, and the set of all rational numbers, they are all natural examples of rings. The set of positive integers, however, is not a ring, because here you cannot subtract. The subtraction of two positive number need not be positive. So n is not a ring. However, z is a ring. If in a ring, we also have the concept of division, that is, then it is called a field. So some examples are the set of all real numbers, the set of all complex numbers, the set of all rational numbers. They are all examples of fields. However, the set of all integers is not a field, because the division of two integers is not necessarily integer. Can you hear me now?
Yes.
Yeah, I can.
Okay. So these are some technical terms, rings and fields. In fact, the mathematics was going on without these terms. Many important results were proved without this definitions like the Galois theory, and many important developments took place even without this definition. But since I will be using these terms, let me mention. I will now give you another example of rings, which again are the polynomials. So see, a polynomial in one variable is like this. We can generalize it to a polynomial in two variables or three variables or n many variables. So you can think of a polynomial in two variables as a polynomial in y with coefficients from um, fx. There's coefficients from the polynomial ring fx, kx. Or this polynomial in three variables can be thought of as a polynomial in z with some coefficients. So they are very basic object, and these coefficients aij, aijk means these are coming from some fixed field or some ring. See, for instance, the most natural thing which comes to our mind is that these a0, a1, an are coming from rational numbers or real numbers or field or say complex numbers. So that is the most natural thing which comes to our mind. But we can, it's not necessarily we have to just take a complex reals or integers. You can take it from any ring. Therefore, this generalization. So these coefficients a0, a1, an, if we take it from any ring, then this f0x, f1x, fmx, they are also coming from a ring. So it is therefore the definition of polynomial rings for any two polynomials f and g in n variables over a ring R. Fg is again a polynomial. Thus, the collection of all such polynomials form a ring called polynomial rings. We denote by Rx the polynomial ring in one variable over R. For polynomial ring in two variables over R will be denoted by Rxy. More generally, Rx1 up to xn will denote the polynomial ring in n variables over R. The ring structure makes Rx1 x to xn a very important object of study in modern mathematics. So this ring structure, say for example, why we study this? The study of this ring structure, the polynomial ring Cxn up to xn in n variables over the complex numbers, has been very useful in making the algebraic study of the geometric spaces like Cn using powerful ring theory machinery, just as the study of algebraic equations is used in coordinate geometry. So do you remember in high school days, we used to study the equation of circle, ellipse, parabola, hyperbola. So what is it we were doing? We were doing some, studying some geometric space, some geometric properties of that object by using some ring theoretic machinery. Means we were using the change of coordinates, change of some variables. So that is algebra. So that is we were doing unconsciously. So this is the utility. In fact, there are many important results on polynomial rings. The first of this being first landmark, early landmarks, we can think of it as Hilbert basis theorem. So throughout my talk, I will denote K to be a field. So this field K can be the reals, complex, or even the finite fields like the set of our in 0, 1, this binary digit, that can also be a field, or say finite field Z mod PZ. They are all, this K will denote a field. So this was one of the early landmarks of Hilbert basis theorem. It says that every ideal of the polynomial ring is finitely generated. So this term may look a bit technical, and but it solved a very fundamental problem in invariant theory, which Hilbert had listed one of his problems in 1900. He had listed a list of 24 open problems, out of which Hilbert's 14th problem is one of them, where he mentioned about this finite generation of ring of invariants of group actions. But geometrically, the statement that every ideal is finitely generated, you can explain it to any layman by just saying that this statement is equivalent to say that zero locus of any number of polynomials. So if you start looking at intersection of any number of polynomials, and the common points where these curves intersect, that can be obtained by the zero locus of only finitely many polynomials. So doesn't matter how many different polynomials, you just keep on intersecting the polynomial zero locus of this polynomials, the surfaces of varieties, then what you get as a set, that zero locus can be obtained as a intersection of only finitely many polynomials. Another important result is this Hilbert-Nussdalen sets. This is precisely the result which builds a bridge between the geometry and algebra. So on one hand, you have the geometric spaces like the space Cn or the zero set of a variety, say f equal to 0, the surface defined by f, or then on the other hand, you have corresponding to Cn, you have the polynomial ring Cx1 up to xn. The zero set of f corresponds to the coordinate ring Cx1 x to xn mod f, or the variety V corresponds to the coordinate ring of the variety, which is given by the quotient of this ring. So in some sense, these geometric properties of these varieties are reflected in the algebraic properties of these rings. So these are rings, and here where IV is the all those functions which vanishes at every point of V. For n equal to 1, this is the fundamental theorem of algebra, which was proved by Gauss in his thesis, which says that every polynomial has a root in complex number. So this was a theorem of Hilbert, which builds a bridge. Now I will come to some important challenging problems in the area of affine algebraic geometry, which are affine algebraic geometry is basically the study of polynomial rings. So which are very interesting, and sometimes it's very probably easy to state, at least to some people who know a little bit of basic mathematics, but they are certainly very difficult to solve. So there are many such problems. I will list today in this talk, I will talk about only 3 such problems, namely the Jacobian conjecture, the Zariski cancellation problem, and the epimorphism problem. So the main theme, or I should say the main difficulty in solving some of these problems is, so sometimes what we have to essentially do, so this is what the work which we need to understand is to when is a given polynomial in n variables is going to be a coordinate. That is, when can you find another set of polynomials f2, f3, fn, such that the polynomial ring Cxn up to xn is Cf, f2, f3, fn. So that is after some change of variables, or to determine if there is an automorphism or the isomorphism of the polynomial ring, automorphism of the polynomial ring, such that the x1 goes to f. So geometrically it would mean that can you deform the space an in such a way that this zero set of this polynomial f, you can make it one of the axes. Or another problem which we face is usually to determine when is a ring isomorphic to a polynomial ring. So in some sense, it means that if a variety is given, if the zero set of a polynomial is given, when is that zero set going to be like the affine n space? So let me just illustrate you with an example that we have all seen in our school days. So do you remember that we used to shift origin to a point AB in the R2 plane, or we used to rotate the axis? So what were the equations which we need to make? Means the change of variables, what is it we need to do? We used to look at this kind of transformations, sending x prime to ax plus by plus. So this is a linear change, right? This linear change of variables we have been seeing in school days. But so what is this AB, lambda, CD, mu? There are some scalars from R. What is so special about this? Is this any choice of ABCD allowed? No. We need to ensure that AD minus BC is non-zero. Otherwise, this change of variables is not allowed. There can be also, these are called linear change of coordinates. There are also some sort of conic changes which again we have been seeing in probably in BSc level, that change of variables of this form, sending x prime to ax plus y square, where a is a unit, is a scalar, non-zero scalar, or y prime to y. And further changes, means after making this one change, we can make a further change of coordinates, sending x double prime to x prime and y double prime to y prime plus fx prime. So, and we can keep on doing this. We can keep on changing our coordinates by using this machinery. So either apply this linear change or apply this kind of conic changes, right? Y prime plus a polynomial in fx prime. Then we can fix y double prime and take x prime and some polynomial in y double prime. So this can keep on continuing. In fact, the striking result is that any such change of coordinates, see, first of all, this any such change of coordinates give rise to an automorphism of the polynomial ring. The striking result is that the converse is also true. So if you are looking at an automorphism of the polynomial ring Rxy, that will be obtained by a combination of these two types of automorphism, these two types of transformations. So any such automorphism of Rxy will be obtained from these two only. So you keep on applying these two kinds of automorphism. This is a little difficult result, but it's in some sense does not use higher machinery. So it is involved, and but it is if a school student with MSc background can look at this proof. So these are the striking results. So why I am saying it is striking, because when I say that every automorphisms of Rxy is obtained is like this, we don't know how will an automorphism look like. In fact, another one of the most difficult and notorious problem in the history of affine algebraic geometry is due to Jacobian conjecture, which is based on this kind of problem. So let me just illustrate what is it means, the Jacobian conjecture. This is probably the first problem which I can illustrate to anyone who have a very basic background of mathematics can follow this. So take any two polynomials over the complex numbers. So just take any two polynomial. Then we can define this matrix. So this matrix, this is the usual partial derivative we have seen in class 12 also. Del f del x, del f del y, del g del x, and del g del y. So this is a matrix obtained from f and g and taking the partial derivative. The determinant of this matrix is called the Jacobian of f and g. Now suppose it so happen that there exists P and Q in CXY such that you can obtain X from F and G by applying it to P, or Y from F and G by putting it in Q. So in some sense, X and Y can be obtained from F and G, and F and G is to start with our polynomials in X and Y. So F and G is an automorphic pair. Now, from this theorem, we know how will this f and g look like. Okay, given x is a polynomial in f and g and y is a polynomial in f and g, we know that how this f and g will look like by using that kind of linear and conic transformation. But for this Jacobian matrix, we see using chain rule of partial derivative, apply del x del x. So you will get del p del f, del p del f del x, del p del g del x, and del q del f del y, del p del f del g del y. So using this, you get that this product of these two matrices is identity matrix. And now if we take the determinant on both the sides, we will get that determinant is a multiplicative function. So determinant of this matrix times determinant of this matrix must be determinant of this, which is 1. So it means, but what is the second term? The second term is a determinant of that is a Jacobian of f and g. So it means that the Jacobian of f and g is a unit. It is a non-zero complex number. Okay, are you convinced with this? That Jacobian of Fg is going to be a non-zero complex number?
Go ahead.
But the Jacobian conjecture asserts that the converse is true. And this is probably the most notorious problem. So let me just give you an example. So take a f equal to x plus y square and g equal to x plus y square cube. Then it is easy to see that f and g is a Jacobian, it's a variable pair. Why variable pair? Because from g you subtract f cube, so you will get y. And once you get y, you will get also x. So this is a variable pair. So it is an automorphism. Now you can just compute the Jacobian of f and g, which is a determinant, this matrix. So this matrix, the determinant of this matrix is 1. So if f and g is a variable pair, the determinant of fg is 1, which is a unit. The Jacobian conjecture asserts the converse is also true. So the conjecture is that if f and g is such that the Jacobian of f and g is a non-zero complex number, then you can find polynomials p and q, which will give rise to x and y. So in some sense, you can recover your x and y from f and g in polynomial expressions. This problem, you can also generalize it to n variables. So if f1, f2, fn are polynomials in n variables, such that the Jacobian means that the determinant of the Jacobian matrix is a non-zero complex number, then you can recover your xi's from fi. So that is how I should say that you can find some polynomials p1, p2, pn such that you can recover xi's from f1, f2, fn. So this is a conjecture. These are not theorems. In fact, there are several equivalent formulation of this conjecture in most branch of mathematics, in affine algebraic geometry, or say in number theory, or say in logic, or in differential geometry. There is a version of Jacobian conjecture. One doesn't know which field of mathematics will be useful, or if at all some new mathematics has to be developed. One doesn't know how it can be solved. There have been many incorrect attempts. That is why I'm calling it the most notorious problem, because there have been many attempts by many mathematicians, in fact, well-known mathematicians, and even published incorrect proofs. This problem is one of the 18th problem which was listed by Smale in 1998, inspired by Hilbert. So Hilbert in 1900, I mentioned, he listed some 24 open problems, which in fact guided the 20th century mathematicians in research. Smale, a field medalist, has written some 18 such problems, and Jacobian conjecture is one of them. So it is a problem of very high level. So now I would like to go a little more and talk about Oskar Zariski. He was a supervisor of Professor Abhyankar, and who guided many PhD students who were Fields medalists, including Mumford and Grothendieck. So he, in fact, developed this link between this commutative algebra and geometry, algebraic geometry. And now I will talk about this C.P. Ramanujan. He was an Indian mathematician from TIFR who worked in this area of affine algebraic geometry and of very high level. He in fact said about David Mumford, the Fields medalist, he told about him that the spirit of mathematics demanded of him not merely routine developments, but the right theorem on any given topic. So he was also worked. In fact, he was working towards this Zariski's cancellation problem. So I now talk about the cancellation problem. Okay, so cancellation is a theme which is not unknown to you. This theme we have been with this theme from very early days. So we know that whether this is necessary sometimes to know whether elements in the structure or the structures themselves are cancellative. See, for instance, if ax is equal to ay, we would like to know whether x is equal to y, whether we can cancel a from both sides. But we have to be careful. In fact, if we are not then we may land into mistakes. We may start proving 0 equal to 1. So, but so why we have to be careful? Because 0 is not cancellative. If we have 0 times b is same as 0 times c, but that does not imply that b equal to c. So it is necessary to know when are these elements cancellative. For instance, this kind of property does not hold for matrices unless the matrix is invertible. So based on this theme of cancellation, the algebraic structure group is also defined in such a way that every element is cancellative. All its elements are cancellative. So this is about the cancellation of elements. Sometimes we are also interested in cancellation of spaces, like in vector spaces. If we have seen vector spaces, we will know that it is well known that if V cross K is isomorphic to Kn plus 1. So if V is an n-dimensional vector space and adjoining one more dimension to it, if it is a vector space is n plus 1 dimension, then it is easy to see that V is a vector space in dimension n. So Zariski cancellation problem is about, again, the cancellation of spaces. In fact, it's little more than cancellation of vector spaces. So here, these are not treated as a vector spaces, but as a varieties. So, so it's just not a vector space. It also has some sort of topology called Zariski topology, which has a sheaf structure. So I will not get into the definition of Zariski topology and the structure sheaf, but if you look at the zeros locus of a system of polynomials or a surface or a curve, then it will easy to see that. So the Zariski cancellation problem is about the cancellation of such varieties. So geometrically, let me explain you with this diagram. So suppose this is a zero locus of a polynomial. So it's a zero set of a polynomial. So if you look at the affine cylinder over this, so over this curve, I am considering an affine cylinder. So suppose this surface, now this you can only visualize this three-dimensional space. So suppose this surface is isomorphic to the affine plane. The question is whether the curve with which you have started is like an affine line. So whether it is like a line, if the surface is like a plane, whether the surface which you have crossed, taken the cylinder, whether it is like a line. So this is the idea, this is the conjecture, or I should not say conjecture, this is what Zariski asked and thought. So equivalently, this geometric problem can be said in the ring theoretic way. So it says whether the polynomial ring in n variables is cancellative. That is, suppose the polynomial ring in one variable over a given ring A, if it is isomorphic to a polynomial ring in n plus 1 variable over a given field K, does this necessarily imply that A is isomorphic to the polynomial ring in n variables? Let me just tell you with an example. So suppose this polynomial ring in n plus 1 variable, you can think of it as a polynomial in xn plus 1 with some coefficients, right? But these coefficients can be written in a various way. For example, just take the polynomial in two variables, kx, y. So you can think of it as a polynomial in y with coefficients from the ring kx, but you can also make it as a polynomial ring in y with coefficients from x plus y or x plus y square, or you can change it to any polynomial x plus 5y. So the polynomials in y with coefficients from any base ring. So the Zariski cancellation problem asks basically that whether all these coefficient rings are necessarily isomorphic. So of course they are not equal. This kx is not equal to kx plus y, but the question is whether they are isomorphic as the rings. So whether all such coefficient rings are necessarily isomorphic. This problem was known to have an affirmative answer. So it was known that the polynomial ring in one variable, the affine line, is cancellative. And in fact, Abhyankar, Ikina, and Heinzel's, their result was much more general. So it follows from their result that the polynomial ring in one variable is cancellative. So the cancellation result for the affine plane that was proved by Fujita, Miyanishi, and Sugi in characteristic 0 for n equal to 2. In fact, the solution of this problem for k is equal to 2, it was not so easy, and it took a decade to solve this. the first major breakthrough was made by C.P. Ramanujam, who tried to give a geometric proof by giving a topological characterization of the affine plane C2. But unfortunately, this topological characterization was not did not lead to the solution for n equal to 2. It was later proved by Professor Gurjar, again another Indian mathematician, who used these ideas of Ramanujam to give an alternative proof of n equal to 2. And this proof for characteristic k equal to 0 was later soon generalized by Peter Russell over any perfect field k. And we did it for any field. So this is another thing. But this problem, what we know is for only n equal to 2. For n greater than equal to 3, what we have shown is that this problem does not have an affirmative answer for n greater than equal to 3 over a field of positive characteristic. And over a field of characteristic 0, it is an open problem. It is still a very well open problem. It's very difficult. Now let me give you that example which lead to this solution for n equal to 3. So this was due to Asanuma. So Asanuma has constructed this example in 1987. He constructed this ring. Basically, it's not the ring, but basically this polynomial, which was constructed by Asanuma, and he wanted to study this ring. This was constructed over a field of positive characteristic. I will not get into the detail, the properties of this special polynomial, but this ring had a very special properties. Asanuma had shown that this ring is a stably polynomial ring. And later in 1994, when he was doing this linearization problem, he asked whether is this ring a polynomial ring, because if the answer is yes, he would have gotten counterexample to the linearization problem in positive characteristic. I will not talk about the linearization problem. So if the answer is affirmative, if A is a polynomial ring, he would have gotten counterexample to the linearization problem in positive characteristic. And if no, it's clearly an counterexample to the Zariski's cancellation problem in positive characteristic. Peter Russell had referred to this problem of Asanuma dichotomy as Asanuma's dilemma in one of his survey articles. I have showed that this ring A is not a polynomial ring for any integer m greater than or equal to 2. And this leads to the solution of the Zariski's cancellation problem over a field of positive characteristics. And this polynomial means this again is a mystery for m equal to 1. We don't know whether A is still a polynomial ring. This example of Asanuma was generalized again in higher dimension. So this is a polynomial ring in m plus 3 variables, and this is one polynomial with a linear polynomial in y with coefficients x1, x2, xm minus fzt. And I showed that this ring A is a stably polynomial ring that is adjoining one more variable. This ring becomes a polynomial ring in m plus 3 variables. So if this small f, now the property is about this small f, if it is a non-trivial line, so this term I will not explain, but there is something special about this, then A is a non-trivial A2 fibration and A is not a polynomial ring. As a corollary, we get that the Zariski's cancellation problem does not have an affirmative answer over a field of positive characteristic for any integer n greater than or equal to 2. So this completely solves the Zariski's cancellation problem in positive characteristic. So now I will talk about another important polynomial which was due to Russell and Chorus. So he talked about this polynomial. You can see it's a polynomial in 4 variables, which is linear in y, and some quadratic in z squared just one term, t cube just one term. It's just 4 terms. So, but this polynomial had been a mystery for several years for mathematicians because the coordinate ring of this variety, one doesn't know whether it's a polynomial ring in 3 variables. Why we were suspecting it to be a polynomial thing in 3 variables? Because this ring A shares several algebraic properties of C3, and this zero set of this polynomial shares several geometric properties of C3. So in fact, this V is this topologically it is like C3. Topology is C3, but algebraically we don't know. So if the answer is yes, if A happens to be a polynomial ring, then we would have got a counterexample to the linearization conjecture and also to the epimorphism problem. But fortunately, Makalimanov had developed a technique in 1996 where he proved that this ring A is not a polynomial ring, and which led to the solution proof of the linearization conjecture for C3, and also to the epimorphism problem is still, so linearization conjecture has been solved affirmatively for C3. Now the epimorphism problem is open for C3. And this polynomial is again now a threat for the Zariski cancellation problem for C3. So one does not see, now we know that A is not C3, but one doesn't know that after adjoining one variable, A is not C4. So that is open. Now, I just want to talk. So people say many things about mathematics. So there is a quote by Thurston who said that mathematics is not about numbers, equations, or computations or algorithms. It is about understanding. So what is this all happening about this polynomial? So we look at equations of this form, x to the power my equal to fxzt. So it's a linear polynomial y. And then we try to see two examples. One is this example of Asanuma, which is again in this family. So here this zp squared t plus t to the power sp is a non-trivial line in CZT. So I will not talk about what is this. So Peter Russell, who solved this ZCP in perfect field for n equal to 2, he asked me whether Peter Russell asked me whether if you take any non-trivial line instead of this special polynomial, if you take any non-trivial line, will this ring A still be not a polynomial ring? So one doesn't know a characterization of a non-trivial line. Again, there is an example of Russell and Chorus, which again is in this family, x plus z square plus t cube. So this leads me to investigate, Miss, why? What is so special? Or so investigate problems like this. So take a general threefold, which is determined by this polynomial, which is linear in y, and ask questions like this. When is this ring a stably polynomial ring? When is this ring a polynomial ring? And when is this ring, this equation x to the power my minus fxzt, this polynomial is going to be a coordinate. So with some change of variables, you can replace it by some y or z. So that is some problem which I was thinking about, and so this leads to my solutions for this. In fact, we found many interesting results. So we discovered that this structure of this equation basically depends on small f, which is f0zt. So what we showed is that if f is a line, so this definition, this is a definition of line. So f is a line, then A is a stably polynomial ring. So this is a sort of incomplete thing because we don't know the converse of this. And if f is not a coordinate, then A is not a polynomial ring. Again, we showed that if f is a coordinate, if and only if this whole thing x to the power my minus f is a coordinate, and it is a coordinate along with x. This leads to the, in fact, we also classified the isomorphism class of any two surfaces. So we proved that any two such surfaces are isomorphic if and only if these integers m equal to n, and this fzt is an associate of gzt. So in some sense, if you vary your integers m and n, you will get an infinite family of rings which are not isomorphic, but they are all stably isomorphic to the polynomial rings. This also leads some new insights into the famous three forces like Asanuma and Russell and Chorus. In fact, we proved an equivalence of 10 statement, which each of them may look a little different, but this connects many important problems in mathematics, including the cancellation problem, epimorphism problem, and the fibration problem. So this is the 10 equivalent statements which I have proved about this ring x to the power my minus fxzt. So this is a Dachshund invariant. I will not talk about this definition, but the first 5 of them you can read without knowing the definition of Dachshund invariant. So this ring A is a polynomial ring if and only if x is this small x is one of the coordinate, if and only if the small f is a coordinate in kzt, if and only if this g is a coordinate in kxyzt, and rest of it is related to the Dachshund invariant. So we won't get into that. Now I just want to end with a few other important well-known results, in fact famous landmarks in polynomial rings by Abhyankar, Moe and Suzuki. So this I can explain it to any student or anyone with even science people can understand this. So let K to be a field of characteristic 0. If you are not comfortable with field, just forget about it. You can take complex numbers or real numbers. So suppose f and g are two polynomials in one variable such that you can obtain t from f and g. So f and g are two polynomials in t with coefficients from say complex such that you obtain t from f and g. For example, you take f to be t square and g to be t plus t6. Then if you subtract from gt minus ft cube, you will get t, right? Means t6 minus this cube of this, you will get t. So this is one example. Suppose there are two polynomials f and g such that by some polynomial framework you get t from that. Then what will happen? Then this is the theorem due to Abhyankar, Moe and Suzuki, that either the t degree of f will divide t degree of g, or the t degree of g will divide t degree of f. So this is a very non-trivial result proved by Abhyankar, Moe and Suzuki. It's really non-trivial, means, but the proof is elementary. Of course, it runs over 100 of pages. That doesn't matter, but the proof is elementary. You can read it, and this is the beauty of mathematics. Another important embedding is the Trifold Knot. So this knot which we all familiar with. So if you look at the knot in 3 space, means in 3-dimensional space, you can put it in such a way that there is no self-intersection and it is like a straight line. But whenever you try to strengthen it, means you try to make it a straight line, you will get into an intersection. So this is this question of a Sastry, whether in every embedding of C and C3 equivalent to the standard embedding. So geometrically it just means that suppose you have an embedding of a line. So if you have a map from a line to a affine 3 space, whether you can make it as one of the coordinate, whether you can make it as an axis. So this is the Trifold Knot. So this example was given by another Indian mathematician, A.R. Sastry, who gave this polynomial representation of the knot. So from topology, we know that we cannot make it strengthen it. So the question is whether we can also not do it over complex, because in complex we don't have any topological hindrance, and so it is not known whether this example, so this is a very simple 3 polynomials parametrization of that curve. One doesn't know whether you can strengthen it over complex numbers. So from topology, we know that we cannot extend it in over real numbers. In fact, using this Trifold Knot, you can construct a polynomial ring. Means you can construct a ring which we don't know whether it is a polynomial ring. Professor Asanuma had shown that this ring is going to be a stably polynomial ring. So after adding one more variable, it will become a polynomial ring. but one doesn't know whether to start with B is a polynomial ring or not. So I just end with another important, interesting polynomial. So you can see that this is a polynomial in 4 variables, which is linear in Z. But unlike this asynchronous threefold, the coefficient of Z is not x to the power n, it has tx to the square. So this is very interesting. This was constructed by Professor Bhatwadekar and my supervisor, Professor Amartya Kumar Datta in 1993. And they proved that if you consider this ring A is a polynomial ring in 4 variables, and the subring R is generated by T and this polynomial F, then A is an A2 fibration over R, A is a stably polynomial ring over R, and the zero set of F is going to be a variety in affine 3 space. So F is called an hyperplane. So it is like a epimorphism theorem. And the question is whether A is a polynomial ring over R. So this is one question. And if you are unable to do it, why don't you try that whether A is a polynomial ring over the subring CF? This is probably a weaker question than this. So at least whether you can show that A is a polynomial ring over F, CF. And if you answer it affirmatively, means if you say the answer is no, then you have solved 3 very important problems: the affine fibration problem, the cancellation problem, and the epimorphism problem. So cancellation problem I have already discussed. This epimorphism problem is related to what Abhyankar, Moe, and Suzuki had done for C2 to C1. So it is now from C4 to C3. So embedding of C3 in C4. And the affine fibration problem is again a important thing which it talks about. So it says that whether if all the fibers are affine space, whether globally it is an affine space. So it's going to be the history if one solves this. So it is going to be written in golden words in history. So I end my talk here. Thank you, sir.
Thank you, Nina. We don't have much time because there is a next talk within 10 minutes or so. But I will allow a maximum of 2 questions. So if any of you have a question, whoever asks first, you can switch on your mic and ask. Whoever has a question. Yeah, Anushka, you gave a question. Anushka, can you hear me?
Hello.
Yes.
Actually, this is probably my question. I put a question. I am Satrajit Odhikari.
Okay.
You can see in the chat box.
Which conjecture are you talking about?
No, can you state your problem, please? Your question, please.
The question is, in the case of the determinant partial derivative and the determinant for f and I think p and q, and then you did another partial derivative, and then you finally proved that it is a unit matrix.
Yes.
Then finally you said this is for the real function. You say for it is proof for the complex.
No.
But I mean, it must be maybe, but I didn't get it how it is valid for the complex. I understand clearly for the real, of course. That was one of the questions. Yes.
So probably you're talking about this Jacobian matrix.
Yes.
Just let me take it out.
Are you sharing your screen, Nina?
Yes, sir. Oh, probably I have not started share. Okay. Yeah. So can you see the screen now? So are you talking about this matrix?
Yeah.
So this is true over complex as well as over reals. You just take the partial derivative. Means, see, partial derivative, some coefficients. In fact, I didn't told about this. If you are in math student and you know about implicit function theorem, have you heard about this? Inverse function theorem, sorry, inverse function.
No, sorry, I am not a math student. I am a quantum chemist professor here.
Okay. Sorry. So I was wondering whether have you ever heard about this inverse function theorem in analysis?
Yeah.
So
I mean,
inverse
I
function
do not
theorem.
understand. This is proven easily. It can be proven easily for the real function, but I do not understand how it is also be proven for complex. Can you explain
How
little
do
bit?
you prove this
I
for
think
real?
that is
Yeah.
The way you prove for reals, it will same work for complex also. It's the same thing. Yes, sir, you were
if
saying.
the product of two functions, if the product of two functions is 1, then both the functions have to be of 0 degree.
Yes.
Whether the function is over reals or complex.
Okay. I mean, I didn't get the answer. Okay.
Okay, so we have a second question from the person sitting next to me, Moito.
Thank you, ma'am. Thank you, ma'am, for the wonderful talk. Ma'am, I just one small question. Towards the end of the talk, you stated an example by Shastri 1992 about probably the embedding of C in C3. Ma'am, I just one question, ma'am, is the example which you stated unique? I mean, have mathematicians found any more such examples?
No, there are other embeddings like this. There's an embedding of the figure 8. You can also embed. So basically, you topology from means you can have non-trivial embedding of a line in R3.
Okay, ma'am.
So that is known. That is due to Shastri. So Shastri, what he did, he given polynomial representations of some such lines. So, but we doesn't
Knots, not lines, knots.
knots. Yeah. So this, So this knots we can represent in R3, but we don't know how to see this in complex, because in complex the dimension increases. So in complex we have a 6 dimension, and this knots become surfaces, 2 dimensions thing. So there is no topological obstruction there, but the same polynomials work.
Thank you, ma'am.
Okay, so I think we don't have enough time for more questions because
I have just one comment. I think this Suzuki's theorem is different. The result that you quoted is due to Abhyankar-Mo.
Yeah.
Okay.
The corollary is due to Suzuki, Suzuki didn't think of these things algebraically.
Yes.
Okay, so this was Amartya Datta, her supervisor is speaking. I recognize his voice. I can recognize any time. But I wish to, first of all, thank Nina. And I will end up with not an anecdote, but actually an incident. Asanuma was a very, very major player in cancellation problem. And Nina, who became very famous for solving it, she got an idea even much before she published or she actually solved when she was in TIFR. And she went with her ideas to Asanuma when he was visiting ISI. And as soon as Asanuma realized that, oh, she's trying to solve a cancellation problem, Asanuma said, no, very difficult problem, don't try, something like that. And it stopped. So Nina...
Very difficult.
Very difficult. So, very difficult. He discouraged Nina. But then Nina went to, very determined, she went to TIFR when she was a postdoc there and solved this problem. Okay, so I conclude this session here, and thank you very much, Nina, for taking your time out. I know you are very busy. I know your problems, so thanks a lot.
Thank you, sir. Thank you very much.
Okay,
we have to start this again at 11:15. That is scheduled.
हाँ, ताले 11:15 तो होते हैं लो तो 5 मिनट यूजी ठीक है यूजी both के पाठिए
हाँ मना है
अच्छा आखिर हमें तो लिंक पाठिए
Okay, yes. So what do you do? This so the second part,
question came nothing.
Two, three questions. Two, three questions came. Across you must have to stop because the time is.
Oh, have to stop. Why Amartya is showing? I know.
Because he has also joined.
Let's not talk with her.
So that she gets the time to prepare for the exam.
So Ashish, you can start, right?
I think. Why we are not showing up?
Okay, no problem.
Should I start?
Yeah. She has kept it on mute, so please tell him that.
Please.
I'm
You have
unmuted.
Okay.
I'm
all
unmuted.
All right. Dr. Kang, we are delighted to have you on behalf of our institution to deliver the prestigious Mahindra Al-Sarkar Memorial Lecture instituted in honor of the founder of this oldest institution of Asia, Dr. Mahindra Al-Sarkar, who himself was a celebrated doctor, a social reformer, and a propagator of scientific studies in the 19th century of India. That time there was a Bengal Renaissance, which is famously known. I think the first nationalist movement took place. Dr. Mahendralal Sarkar started a campaign in 1867 for forming a national science association. He planned for an association that would be funded, run, and managed by native Indians with the aim of turning out a pool of scientists for a national reconstruction. The Indian Association for the Cultivation of Science was established in 1876, and Dr. Sarkar was its first secretary. IACS was the first national association of India. Basic science departments such as chemistry, physics, mathematics, physiology, geology, botany, etc. were established, and notable Indian scientists participated in the association. Regular lectures and demonstrations were arranged for the public to popularize science. Dr. Sarkar supported women's education in the 19th century India, when higher education among women was very rare. IACS is the oldest research laboratory of Asia, founded in 1876 with the financial support of philanthropists and national leaders. It is where Raman joined and started his laboratory and discovered the Raman effect. I think if you look at one corner, Raman's instrument is visible perhaps to you. You can see that one corner, this is his original spectrometer, which is on display on the corner, with which he did his Nobel Prize winning work. And various other famous scientists such as Satyendranath Bose, he for his pioneering work on Bose-Einstein condensate, and national professor in physics, worked here in the theoretical physics department. The modern IACS, which from where we are now talking, is in the campus, which was started by Professor Meghnad Saha, who is worldwide known for his celebrated Saha ionization theory in stars as the first official director. Today, IACS is one of the major research centers of India, working in several frontier areas of biology, chemistry, physics, and also in various interdisciplinary research areas. Recently, Government of India has conferred a deemed to be university status to this institution on the recommendation made by eminent scientists of the country and University Grants Commission. IACS organizes a number of endowment lectures named after the luminaries of Indian science associated with IACS. And of these, Mahindra Al-Sarkar endowment lecture is among the foremost, and which has been previously delivered by multiple luminaries. I deeply appreciate your kind acceptance of our invitation and for agreeing to deliver the prestigious Mahindra Al-Sarkar Memorial Lecture for the faculty, staff, and students of the Institute today as part of National Science Day celebration, and also Golden Jubilee celebration of the Department of Science and Technology. Now, I would formally introduce Professor Gagandeep Kang, FNA, FASC, FRS. Professor Kang is a professor of microbiology at the Wellcome Trust Research Laboratory Division of Gastrointestinal Sciences at the Christian Medical College, Vellore. She is an independent director of the Heilman Laboratories, a partnership established to make affordable vaccines by Mark and Wellcome Trust. Gagandeep grew up moving around North and East India, changing schools several times. She practiced science frequently at home during her childhood, building a lab with her father at home when she was only 12 years old, and experimenting by cutting up leaves, then observing them through a microscope. She completed her Bachelor of Medicine, Bachelor of Surgery in 1987, a Doctor of Medicine in Microbiology in 1991 from Christian Medical College, Vellore, and obtained her PhD thesis, PhD degree in 1998. She obtained her membership of the Royal College of Pathologists and carried out postdoctoral research with Professor Mary Estes at the Baylor College of Medicine in Houston before returning to the Christian Medical College, Vellore. She is a medical scientist who has worked on diarrheal diseases and public health in India since the early 1990s, as a key contributor to rotavirus epidemiology, vaccinology in India, focusing on vaccines, enteric infections, nutrition in young children in disadvantaged communities. She has combined field of epidemiology with intensive laboratory investigation to inform both the science of the infectious diseases and policy in India. Her comprehensive research on rotavirus has demonstrated the high burden of rotavirus disease across India, the genetic diversity of viruses, the lower protection from infection and vaccines, and the exploration of several approaches to improve the performance of oral vaccines. Her work has led to her being described as India's vaccine godmother. She has published more than 300 scientific papers and is on the editorial boards of several journals, including PLOS, Neglected Tropical Diseases, Current Opinion in Infectious Diseases, and Tropical Medicine and International Health. She's on many review committees for national and international research founding agencies, has served on several advisory boards, mainly related to vaccines, including India's National Technical Advisory Group on Immunization, the World Health Organization's Global Advisory Committee on Vaccine Safety, and Vaccine Implementation Research Advisory Committee. She chairs WHO's SEERS Regional Immunization Technical Advisory Group from 2015 to present, has received honorary appointment as an associate faculty member from the Johns Hopkins University, Bloomberg School of Public Health in Baltimore, Maryland, and adjunct professor at the Tufts Medical School in Boston, Massachusetts. Gagandi played a significant role in the efforts that culminated in the development of Rotavac, a vaccine from Bharat Biotech International and targets diarrhea. She is one of the three principal investigators in the phase 3 clinical trials of the vaccine. She is the first Indian woman scientist to be elected a Fellow of Royal Society, FRS, in 359 years of history of Royal Society. She is also the 9th woman to be awarded the Infosys Prize. She is the first Indian and the first woman to edit Manson's textbook of tropical medicine. She received numerous honors, and that included Women Bioscientist of the Years, Abbott Oration Award, Indian Society for Gastroenterology, Fellowship of Indian American Academy of Microbiology, Y.S. Narayana Rao Oration Award of Indian Council of Medical Research, Ranbaxy Research Award for Medical Research, Infosys Prize in Life Sciences in 2016, and elected a Fellow of Royal Society in 2019. It's my great pleasure to invite Professor Kang to deliver your much coveted lecture on pandemics, vaccine, and the new normal.
Thank you very much for the very detailed and very kind introduction. It's such a pleasure to be with all of you today, and especially for a lecture that is named after Al-Sarkar, who was a pioneer at a pioneering institution. I wish it could have been in person, but that is not currently possible. So I'm going to be talking to you today about pandemics, vaccines, and the new normal. And I think this is something that is of interest to all of us today. Are you able to see my slides?
Yes, yes.
Okay. So one of the reasons that I work on viruses is because I started out with humans, and humans were intensely complicated, very heterogeneous. So I moved then for my PhD to bacteria, found that bacteria were too difficult for me to understand, and thought I would settle on viruses, which were even simpler and had fewer proteins that needed to be studied. Now, rotavirus the virus that I work on is a virus that is smaller than the coronaviruses. It only produces 12 proteins. Coronaviruses have about 30 and are also RNA viruses like rotavirus. Rotavirus is a little more complicated because its genome shown for the coronavirus here as a spring has 11 different segments, whereas the coronavirus has a single strand that encodes all the proteins of the virus. Coronaviruses are very large RNA viruses, and they have some unusual features about them that determine their ability to cause the disease that we now know as COVID-19. You know, in 2020, a lot of things happened. And I think we forget that in addition to the virus, there were other things as well. So 2020 was the year where we saw the greatest number of forest fires in Australia, in the Amazon, on the west coast of the US. 2020 was the year where we lost a significant proportion of the Arctic ice shelf. 2020 was the year where we saw coral bleaching that was worse than almost any other year on record. 2020 was one of the hottest years that since we started recording temperature. And of course, 2020 was also the year of the virus that was discovered in late 2019, but spread across the world in 2020. Now, why are we seeing outbreaks like this? And is there a relationship between what we are doing to our environment and the emergence of new diseases? There very clearly is a relationship. Why do we get new viruses? We get new viruses because the viruses already exist. But as humans, we change and shape our environment in ways that allow viruses to come in contact with us. SARS-CoV-2 is only one in a long line of infectious agents that are spreading around the world. I use the alphabet as an example, from AIDS to Zika, but there are literally hundreds of viruses that we know of that have crossed the species barrier and come from animals and birds into humans. Why is this happening? This is happening because we are coming in contact with animals that we don't usually encounter. If we think about deforestation, if we think about increasing agriculture, every time we cut forests down, we make animals that live in remote parts of the forest lose their habitat. They come into closer contact with humans. In addition to that, we have humans living in much denser parts of the world. So there is a lot of migration from rural areas to urban areas, looking for economic opportunities. And when humans live closely with each other, the chances of disease spreading among them becomes much greater. So if we think about increasing trade, increasing travel, population density, displacements, migrations, we really are in a new era where the risk of epidemics and pandemics is concerned. In just the past 20 years, if I ask people to name the outbreaks that we have seen, the major ones that everybody knows about, obviously we know about SARS in 2003, we know about MERS in 2014, we had H1N1 that was in 2009, we had the Zika outbreak, now we have SARS-CoV-2. And there are other outbreaks that are happening at the same time. We had Ebola in 2014. We had Ebola again in 2017-18. And this year again, there is an uptick in the number of Ebola cases in the Democratic Republic of Congo. Now, if we go back to just the coronaviruses and compare SARS-CoV-2 with the previous coronaviruses that have caused severe disease in humans, there are currently 7 coronaviruses that we see in humans. 4 of them cause very mild disease, the common cold, and we can be repeatedly infected with common cold coronaviruses. But the disease is not severe, so we don't really bother too much about it. But we do have coronaviruses that cause much more severe illness. The severe acute respiratory syndrome virus was first reported in 2003. It came from China and from Hong Kong. It spread to many other parts of the world, mainly in Southeast Asia and in Northern America, but really countries in practically every continent. Now, SARS-CoV was a little bit different from what SARS-CoV-2, and the key differences are that it was a virus that spread only when a person was sick. And this was a key enabler of the ability to control the virus. So if you know that an infectious person is sick, it's possible for us to isolate that person and make sure that they don't spread infection to anyone else. Unlike that, SARS-CoV-2 can be infectious even when a person is not sick, asymptomatic infection. And that has been a critical reason why we have seen so much greater spread of SARS-CoV-2 than we saw for SARS. The other part that we need to be aware of for SARS is that it had a very high case fatality rate. About 1 in 10 people who were infected with the original SARS in 2003 died of this infection. Totally about 8,000 people had the infection and nearly 800 people died. But because it was a virus that spread only when it was symptomatic, it was possible to test people, identify that they were infected, and then isolate them before the disease could spread to other people. And this resulted in a matter of months in our ability to control spread of the infection. The virus essentially died out because it could not spread to any more new people. And since 2004, there have been no more cases of SARS reported anywhere in the world. We also have the Middle East respiratory syndrome virus. This is a virus that is still with us. This is a virus that was first reported in 2014 and since then has spread to many other countries. Saudi Arabia has the most number of cases, but the second most number of cases were in Korea, where people returning from the Middle East brought the infection and then set up human-to-human transmission there. We've had much fewer cases of MERS, about 2,500 cases. This has an even higher case fatality rate, where about 1 in 3 infected people die when they get this infection. However, we are very fortunate that the MERS virus does not spread very easily. What is seen in the Middle East is mostly infections that result from people who come in contact with camels. There has been human-to-human transmission reported, as in South Korea, but they're mostly in hospitals where healthcare workers were badly affected because of the virus being shed at very high levels by people who were admitted in hospitals and were very sick. Now, both SARS and MERS are viruses that originally came from bats and then passed through other animals before entering into humans. So in the example of SARS, that was civet cats. And in the example of MERS, this was in camels. for SARS-CoV-2, we do not know what that intermediate animal species is. We do know that in the 1980s, we had something that looked like SARS-CoV-2 in bats, but where this virus has been in the interim is not something that we have been able to elucidate as yet. So what has this virus done? This is a picture just for India and placing India in context. If we look at the daily new confirmed cases, in India, we had 3 cases at the end of January last year, and then from March 2020 onwards, we started to see cases. We had a lockdown from the end of March and through the month of April. And as the lockdown was released in various steps, we saw an increase in the number of cases being reported every day. We reached over 90,000 cases a day in September, and after that, the virus seemed to decline. We have had a few upticks here and there, and currently over the last 10, 12 days or so, we have been seeing an increase in numbers. Where will we go from here? I think that is something that we will need to wait and see to see whether the increase that we are seeing today persists and whether the peak that we reach in number of total daily cases increases to as much as it did last year. I think it's unlikely that we will get to the same peak, but it is very clear that we need to intensify control and prevention measures right now. Now, if we look at the figures for how much we are seeing in terms of cases, and these are bi-weekly averages, you can see that India is somewhere in the middle of showing up here in the approximately 100 to 1,000 per million population range. If we look at the share of COVID-19 tests that are positive, WHO recommends that you should be testing, every country should be testing enough to keep their rate below 5% positives. And in India, even though we are seeing in some areas very high positivity rates in Kerala, in Maharashtra at this time, overall for the country, we are well under 5% at this time. The really unusual feature about the virus in India has really been how come we are seeing so much less severe disease and such few deaths. So if you look at the map shown here in shades of red, you can see that in India and in sub-Saharan Africa, other than South Africa, the rates of mortality are very, very, very low. And this is despite the fact that India has had nearly 11 million cases in the country. Now, why is this? I think we have a lot of hypotheses for why this is happening, but we really need the kinds of studies that will allow us to test these hypotheses. Now, moving from the state of the pandemic to vaccines, I think we have every possible platform that we can make vaccines on. It is being applied to SARS-CoV-2. So if you look at the top panel here, you can have the whole virus being used to make vaccines, and this can be live attenuated vaccines or inactivated vaccines. In India, the Covaxin that is being used is an inactivated vaccine that consists of the whole virus treated with chemicals to make it immunogenic, but not capable of replication. Similar inactivated vaccines are also being made in many countries around the world, and there are licensed products from China that are being used in China and in many other countries. Live attenuated vaccines are in development in India, with both Indian Immunologicals and Serum Institute of India developing vaccines there. Virus-like particles look like the virus, but don't contain any of the nuclear material or the genetic material, since viruses don't have nuclei, of the virus. In the case of SARS coronavirus 2, the spike protein is considered the protein that is most important for generating a protective immune response. So virus-like particles carry the spike on their surface. Virus-like particles can look just like the virus, or they can be smaller VLPs, um, which carry the spike protein on the surface. In addition to that, you can have just the spike protein or components of the spike protein that are expressed in mammalian, insect, or bacterial cells. And these proteins can be used as an immunogen. Whenever you use a small protein, it's necessary to have an adjuvant to make sure that the immune response is as strong as possible. Now, these platforms, live attenuated, inactivated, virus-like particles, recombinant DNA, are platforms that we've had for quite a long time. In the bottom panel, we see the new platforms that have come into real prominence with SARS-CoV-2. We have vectored vaccines, and the vector that we hear most about is adenovirus vectors, but there are vaccines in development that are using BSV, using measles, using rabies vectors. And essentially what you do there is you introduce the sequence for the spike protein into a carrier virus, and that virus then goes and infects the host cell, delivers the message for how to make the spike protein. And then if it is a non-replicating virus, the cycle is done. If it is a replicating virus, virus vector, then it will multiply for a few cycles, still continuing to deliver the message for how to make the spike protein. When host cells make the spike protein, they release that spike protein and display components of the spike protein on the surface, thus stimulating both the humoral immune response, which makes antibodies, as well as the cell-mediated response, encouraging the immune system to come and kill the infected cells. In addition to that, we have DNA and RNA vaccines. In DNA vaccines, the message for the spike protein is carried on a plasmid. In RNA vaccines, it's messenger RNA that is delivered, usually in a lipid nanoparticle. It conveys the message to the host cell, and there again, the host cell makes the spike protein, which is then released, and the immune system responds to it. So these are the basic platforms for making vaccines. And the question that is frequently asked is, why were we able to move so fast? Whenever anyone talks about vaccines, we are told that it's very expensive, it takes a really long time to make a vaccine. So how come we got done so quickly? I think one of the things to remember is that Newton said, we see so far because we stand on the shoulders of giants. And in vaccinology, that is certainly true. Every vaccine that we develop builds on what we already know. So here I just have the example of a respiratory syncytial virus. In the late 1950s, early 1960s, inactivated vaccines were developed against the respiratory syncytial virus. And instead of, these were given to children, they seem to work quite well in animals. These were given to children, And the children who got the vaccines, when they were exposed to respiratory syncytial virus, they actually developed much more severe disease and some children died. For about 30 years, nobody understood why that had happened. And then at the Vaccine Research Center, at the National Institutes of Health, researchers who were working on a vaccine for HIV tried to figure out why this was happening and found that if you deeply interrogate the immune response of people who have natural infection due to respiratory syncytial virus, you actually make three kinds of antibodies. You make weakly neutralizing antibodies, moderately neutralizing antibodies, and potent neutralizing antibodies. The weakly and moderately neutralizing antibodies are made to a form of the glycoprotein of the respiratory syncytial virus that is after the virus has bound to cells. And the potently neutralizing antibodies are made to a form of the glycoprotein, which is called the pre-fusion glycoprotein. So what had happened when we made vaccines in the past is that we had made a vaccine that induced the weakly neutralizing antibodies, not the potent neutralizing antibodies. And as these weakly neutralizing antibodies circulated in an individual, they actually resulted, when they saw the virus, they resulted in an enhancement of disease. Once this was understood, it was possible to stabilize the RSV glycoprotein in its pre-fusion conformation so that it would induce only potently neutralizing antibodies. There was then protein engineering that was carried out to stabilize the glycoprotein and make sure that it induced a really robust immune response. So with that, it became possible to design a RSV vaccine that we could be confident would induce a protective immune response and not an immune response that would enhance disease when a vaccinated child was exposed. These vaccines are now in clinical development. In addition to the vaccinology advances, and we've had many of them in the past 20 years, there was also the lessons that we had learned from Ebola. So what had happened in Ebola in the past was, for Ebola in 2014, there were actually vaccines available. The Public Health Agency of Canada had developed a vaccine. It was licensed to an American company, and that American company was just sitting on the vaccine. They had not taken it into clinical development because they thought there is no market for an Ebola vaccine. We don't know where an outbreak is going to occur. We don't know how many people are going to get sick. We don't know when this vaccine is going to be used. So they kept the vaccine in their freezer. When the outbreak happened, WHO got a lot of people together. The major research foundations also did the same thing. And they said, okay, we really need to evaluate these vaccines. But because they didn't have a playbook, because they didn't have a protocol for interacting with each other, essentially, it took about 10 months from the outbreak being declared a public health emergency of international concern to starting the vaccine trials. And by that time, the Ebola epidemic had already affected 30,000 people and was waning because good infection control practices were being adopted. When the vaccine started to be tested in countries in West Africa, within a matter of 3 months, we found that the vaccine was effective. Now, just imagine if that vaccine had been available 6 months or 10 months before that, 10,000 people, 15,000 people would not have needed to die if we had had a vaccine available. And the really scary part about it was, it wasn't like the vaccine wasn't there. The vaccine had been there for 15 years. It just had not been taken into clinical development. So in response to that, WHO and other partners came together with the World Economic Forum and India's Department of Biotechnology as a founding partner, and formed the Coalition for Epidemic Preparedness Innovation, where the idea was preparedness, response, and sustainability, to make sure that vaccines could be developed so that they could be used when an outbreak occurred, and make sure that you could have these vaccines given to people without needing to worry about whether people could pay for these vaccines or not. Most outbreaks occur in low-income countries that don't have resources for new vaccines. Where is deforestation taking place? Where do new diseases emerge? They emerge in biodiversity hotspots, which tend to be around the equator, and that's where poorer countries are located as well. Now, for CEPI to function, for all of us to function, for us to make vaccines quickly, we have to understand how vaccines are made. So historically, from Jenner to Pasteur to Maurice Hilleman, who made a dozen vaccines in the 1950s and 60s, the principle has been very similar. You take the whole organism, you isolate it, you inactivate it, you attenuate it, and that becomes your vaccine. You inject it into people, and you can then induce an immune response without the person getting sick. So up until the 1950s, this was the approach that we used. We had lots of very successful vaccines being made, including ones that are in use today. These bacterial vaccines, a number of viral vaccines, all made using this approach, which was in play from Jenner in the 1790s until the 1950s. But after 1950, we got many new technologies that allowed us to advance vaccine development beyond the older empirical approach. So in 1950, we got cell culture. In 1980, we had recombinant DNA technologies. In 1990, we learned how to link sugar molecules to proteins to enhance the immune response and make it durable. And by 2010, we had reverse vaccinology, where you could take the sequence of a pathogen and then design a vaccine, identify which would be the immunogens, and design and test very quickly what potential vaccines might be. So since 2010, we've had even more advances. We use structural vaccinology, an example of which I showed you with the respiratory syncytial virus. We had synthetic biology, so the making of RNA and DNA vaccines. We had new adjuvants being made. We had human immune response driven antigen selection, which basically is in people who are protected from infection. You can clone their entire antibody repertoire and find out which are the functional antibodies, and then work backwards to make vaccines that induce that functional response. So really, everything that we have done in the past year has built on the work of the past 20 plus years. So the Coalition for Epidemic Preparedness Innovations was designed this way to recognize how much was available in terms of vaccinology. And the approach taken was very strategic. It was to identify agents that caused outbreaks for which vaccines were likely to be needed, as well as look at disease X, the disease that would emerge at an unknown time from an unknown place, caused by an unknown agent, affecting an unknown number of people. So could we actually think about having a vaccine for disease X and be ready for it? So among the pathogens that were originally chosen by CEPI, which was founded in 2017, were Lassa, MERS coronavirus, and Nipah, and then Rift Valley fever and chikungunya were added to that. In addition, in 2019, CEPI funded Disease X programs or platform technologies programs, where the idea was as soon as you have a sequence, within 3 months, can you make a vaccine that can get into the clinic? When the sequence for SARS-CoV-2 became available in January of 2020, CEPI very quickly went to all the people who were doing their MERS coronavirus program or their Disease X programs and told them, can you switch to work on this virus? Who were they? The University of Oxford, BioNTech, and Moderna. So the first 3 vaccines were all vaccines that were already working with CEPI. Since then, CEPI has funded many more vaccine candidates, including Novavax. And CEPI has also tied up with WHO and the Gavi Alliance to lead the vaccine pillar of the ACT Accelerator. Some of you may have heard of the COVAX facility. The COVAX facility is the vaccine pillar of the Access to COVID-19 Tools Accelerator established by WHO and partners. And in the case of vaccines, those partners are CEPI and the Gavi Alliance, with a commitment to ensure that 20% of the populations of low and middle income countries get vaccines without needing to pay for them. And India is also getting vaccines from the ACT Accelerator. Now, if we think about, again, why we moved so quickly, I think one of the things that it's really important to recognize is that we knew a lot about this virus before we started to make vaccines about it. Vaccines for SARS-CoV had already been in development. It had already been identified that the spike protein was the dominant immunogen of this virus. And the receptor binding domain of the spike protein of SARS-CoV was what bound to the ACE2 receptor on human cells. And if you look here at these ribbon diagrams of the spike protein, what you can see here is that SARS-CoV and SARS-CoV-2 are near identical structures, which allowed us to move very, very rapidly to say that if we focus on the spike, our chances of making a vaccine and making it quickly are really very good. So where are we today? We have in preclinical studies about 200 vaccines, 40 that are in safety testing in humans, 27 that are in safety and immunogenicity studies, 20 that are looking at clinical efficacy. So to look at vaccine development, you start off first by establishing doing preclinical toxicology in animals, and then in a small number of people, about less than 100 usually, you do phase 1 studies. In phase 2, you move to somewhere between 100 and 1,000 people. And then in phase 3, you go to 1,000, 10,000, 30,000 people in order to measure whether the vaccine actually prevents the disease that it is supposed to prevent. How do you do that? You do that by vaccinating some people and comparing the vaccinated individuals with the ones who received a placebo or a sham vaccine or a comparator vaccine. Today we have 8 vaccines that are in limited use and 4 vaccines that have full approvals. There are also 4 vaccines that have been abandoned following phase 1 studies because they did not meet the GO criteria for those vaccines. We are also in a state today where we've never had so many successful vaccines before and so many more to come. So there are many vaccines that have efficacy data. Pfizer BioNTech was the first, followed very quickly by the Moderna vaccine, followed by the Oxford AstraZeneca vaccine, known as Covishield in India, the Gamaleya vaccine, 2 inactivated vaccines from China, Sinopharm, Sinovac, the Janssen adenovirus vectored vaccine, which is the only single dose vaccine that we had until I think today, where CanSino Bio has also announced that its adenovirus vectored vaccine can also be given as a single dose. We also have Novavax's subunit vaccine. So we have at least 4 platforms where we have shown that vaccines really work. When WHO was deciding how it would choose a vaccine, how it would say a vaccine is successful, they had established a target product profile, which is 50% efficacy. At least 50% efficacy we must reach. We should be able to give this vaccine to adults, and we should not need more than 2 doses. It should give protection for 6 months. This target product profile was made in May of 2020. And as you can see here, it looks very unambitious at the moment because every vaccine that we have that has efficacy data is doing better than we had hoped. If we look at the share of people vaccinated, here I'm just showing the data for last week for the United Kingdom, the United States, and India as a proportion of the population of our countries. So even though India has given out a large number of doses of the vaccine, so far by vaccination, we have only protected a small proportion of our population. Nonetheless, we know that the more people that we vaccinate, the more protection we will see. Last week, we had these wonderful data coming from Israel, where it appears that there is over 80% protection with the Pfizer vaccine against infections, symptomatic infections, and then over 80% protection against hospitalizations and severe disease. However, there is some reason for us to begin to think that we need to move faster, do more, and think about new vaccines. And that is because of the threat of variants. There are variants that began to, well, variants are there all the time, but variants of concern are variants that matter for one or the other reason. And if you look here at the orange to red colors, these are the variants that are variants of concern for us. Why do they matter? They matter because sometimes if a variant has a mutation in a particular place, we may not be able to find the virus anymore using the methods that we use. The variants could cause more severe disease, they could spread more quickly, or drugs and monoclonal antibody therapies might not work, or vaccines might not protect us, and that might result in reinfections or disease. So if we just look at a couple of examples of variants of concern, this is the one that emerged in, or was first detected as a public health problem in the UK. It appears to be 30 to 50% more infectious, and it may cause more severe disease. but it seems like vaccines work very well against this variant. So if we look at neutralization by immune sera for this variant, there is a reduction in our ability to neutralize, but not enough to make a difference in terms of the performance of the vaccine. The other variant is the one that was noted in South Africa. In this variant, however, it seems like people who were previously infected are not able to neutralize this virus. So that means that if you had a prior infection with an ancestral SARS-CoV-2 strain, then you may not be protected from reinfection. So this is an example of immune escape and demonstrates why we should be concerned about certain kinds of variants. And this has been validated from results from the Novavax trial, where with the original strain, there was 96% efficacy, with the UK variant about 86% efficacy, and with the South African variant, 60% efficacy seen against these strains. There is a new variant which is emerging in Brazil, and the reason that we are concerned about it is it's likely that this also causes immune escape. In Manaus in Brazil, about 3/4 of the population was infected by October. You would expect this to be herd immunity without disease spreading anymore. But you can see that from January of 2021, the number of cases has begun to climb a lot. So what does all of this mean? SARS-CoV-2 is an interesting virus from a virology and clinical medicine point of view. It causes disease that is the patterns of disease are strange. There are a lot of pathogenetic mechanisms at play, from affecting the endothelial system and resulting in clotting to autoimmunity. There are a lot of risk factors which are well described, but it's still not possible for us to predict how severe disease will be in each individual person or in populations. We saw the example of India. The vaccines work surprisingly well. This, for a mucosal infection, you don't expect vaccines to do this well. The virus evolves, and it evolves to become more transmissible. It evolves to escape from immunity. What we don't know is there a limit to immune pressure and how much the virus can change before it stops changing? This is something that I think 2021 will show us. Viruses very rarely evolve to become more virulent, so I'm not too worried about that. But if zoonotic spread occurs, where humans transmit the virus to animals and then it comes back into humans, then it's possible that we might see a more virulent strain of the virus. This is what happens very frequently with influenza, particularly with avian strains of influenza. We've seen this happen with mink in Denmark, where the virus went from humans to mink and back into humans. Fortunately, it was not a very transmissible strain, so only about 12 people were infected. Overall, I think it's important to think about what the new normal is, and to place that in context, it's important that we recognize that we have done quite well, particularly in India. In some ways, we've been lucky. This is not a very virulent virus, and there are many things that we have learned that I hope we will be able to keep. In clinical practice, we've learned the importance of infection prevention and control. We've had all kinds of new experiences, including telemedicine. We've transitioned to team-based care. We've developed new approaches to respiratory managements. But I think the most important lesson for me is how important clinical trials really are. The new treatments that we have, did not come from small studies. They came from multi-site, large studies. And if we do anything in India, I think it's important that we emphasize the importance of clinical research and trial participation from our patients. In terms of policy, I hope that we will do better with surveillance so that we can control future pandemics. We learned a lot in terms of PPE, diagnostics. We did a lot of indigenization and backward integration. This is good, and we need to continue. I hope that we will have increased health spending, including for research, and that we will understand that the stresses on healthcare workers are high and they need support, and especially for vulnerable groups. It's very important to ensure that we.
I know it's hard to remember the people. It's even harder to. You're right next to me. Too late to make it. Too late to try. And all our time that you wasted, all of our bridges burned down. I've wasted.
Right.
Hoy
So I
estamos aquí
think,
para que
I think that is telling me that it's time to come to the end of this presentation. I hope that we will have system level changes where we continue to understand the importance of health, and that health is important not only to healthcare workers, but to all of society. So one thing that has been a huge positive is that science has brought us solutions, and I hope that all of society recognizes the importance of science. So together, I think now the stage is one where we need to build trust and deliver vaccines and interventions wherever they are needed and to whom they are most needed. So thank you very much for your attention, and I will stop there.
Insightful and important lecture. Thank you, Professor Kang, for very insightful and useful lecture for all of us. I was wondering whether you would like to take a couple of questions.
Sure, I'm happy to take questions.
I would start with one. You know, we have read in literature that people who have high levels of interferon lambda, they are, somewhat protected. They resist the infection, and they manage to be, unscathed even during the peak epidemic. Is that true in case of India as well?
We actually don't know. So one of my particular concerns has been that we are not investigating human immunology in India the way that we should. Mm-hmm. We very rarely have clinical populations that are linked to good immunology laboratories. There are a couple of, if you think about human immunologists in India, you can count them on the fingers of your hand. You're fortunate that in Kolkata you have a couple, but there aren't that many in the country. So I'm hoping that that will happen. Now, where antiviral responses are concerned, one of the hypotheses about why we see less severe disease in India is the hypothesis that if we have lots of recent viral infections, if you're constantly being infected with viruses, are you in an antiviral state when SARS-CoV-2 enters? And in that case, will you be able to limit the replication of the virus? It's possible, but unproven. So there are a number of questions in the chat.
Yeah.
Should I take them directly from there?
Sure. I mean, it's depending on your time that is available.
Sure. So from Siddharth Jana is the question of mutations in the viral S protein. Can it allow SARS-CoV-2 to infect a vaccinated person? Yes, absolutely. It can, and examples of reinfection have been shown. Particularly if you look at the data from South Africa, in fact, that's exactly what we are seeing with the new variants. The rates of infection in people who were previously seropositive and people who are negative are exactly the same. So the next question is a direct message from Kaushik, I think, about pangolins. We have no evidence to support pangolins being an intermediate in the from between bats and humans. It was believed to be the case earlier, but deeper study has indicated that it is not. Why are HIV affected people, HIV infected people not affected? Actually, they are. And in fact, one of the hypotheses for why the strain has emerged in South Africa is that it may have gone into people who with HIV infection and been able to evolve there because their immune system was not able to control replication. The next question is about post-COVID-like Kawasaki disease. So this is the multi-system inflammatory syndrome, which is seen in children as well as in adults. And we have no explanation for why this happens. It is a subject of active investigation in multiple parts of the world. There are registries that have been set up, and I think we are likely to have a better understanding of what is going on with these conditions, as we accumulate more numbers of cases. Can antibody-rich plasma be given to everyone till you have vaccines? Well, there have been trials that have looked at plasma, and the Indian trial was unsuccessful, but it has been shown that if you have antibody-rich plasma that is given early in infection, then that seems to prevent progression to severe disease. The question from Kaushik about will we get a medicine along with a vaccine? I certainly hope that we get more medicines. One of my worries has been that we are focusing so much on vaccines that we are forgetting the fact that vaccines don't give us perfect protection, and people will get infected, the ones in whom the vaccine does not work. That is not predictable. We don't know when that will happen, and some of them will go on to severe disease, and we will need medicines, and we don't have enough medicines at this time. The next question is about, will vaccines give us 6 months protection? Well, I think it's important to emphasize that the WHO wanted a minimum of 6 months protection. Right now, we don't know how long protection lasts. So we will continue to monitor people who are vaccinated and then decide on the need for booster doses. For influenza, we are supposed to take a booster dose every year. Will SARS-CoV-2 be like that? I actually think, given everything that we've seen, the fact that vaccines have been so successful against SARS-CoV-2, I actually think that we will need a vaccine booster much less frequently than every year. But it may be that this first generation of vaccines that we have might not be the ones that we will use in the future. So do you think pseudovirus could be used in the generation of vaccine development? Well, pseudoviruses are currently being used to study neutralizing antibody responses. And one way of thinking about the virus vectors that we are using is that they are very similar. They are essentially, you have a viral gene that is taken from SARS-CoV-2, and put into the virus vector to be carried into host cells. What exactly makes blood group O relatively resistant to COVID-19? I think for many viruses that attack mucosal surfaces, the histoblood group antigens really matter. For noroviruses, for rotaviruses, we know that there is a difference in susceptibility based on whether you are a secretor or a non-secretor, and if you are a secretor, which blood group antigens you express. So this is not unusual for viruses, but we don't understand why more resistance comes. Yes, absolutely. So from Samudra, SARS-CoV-2 mostly came from bats. Yes, all the coronaviruses that cause severe disease came from bats, but the cluster 5, I think there is a bit of a misunderstanding there. We think cluster 5 was from humans to minks and back to humans, not something that emerged from humans. So just to clarify that, 99% of non-human animals used by humans are factory farmed. Absolutely. I think we need to worry not only about wildlife and the viruses that we can acquire from them, but also about the possibility of acquiring viruses from domestic animals. The thing is, the variety of viruses that we see in wildlife is somewhat wider than the variety of viruses that we see in farmed animals. So I think I've addressed all of the questions.
Thank you so much, Gagandeep, for such a wonderful opportunity that you have provided to us. I mean, we would have very much liked to have an interaction physically, but that would not happen. But I'm looking forward to time when you could get some time to visit this city and our institution. And, we have many young students in our, very ambitious undergraduate program that we have undertaken here, which is highly interdisciplinary in character. And that would be actually very appropriate with the kind of research that you have talked about. And again, I look forward to having further interactions with you. Thank you very much.
Thank you.
So what is the next?
12:30 we have this. This is our presentation.
Is it 12:30? Is this fellow is in the country?
Yeah.
Oh.
We have presentation.
But then how you will give the lecture?
Yeah, you share screen. Help video like YouTube এ ছাড়া
You should load all this stuff. So she gave a very, broad, I think very informal, I would say, not so much technical. She's a very important person, actually, important person in the context of this. She's from Punjab. But I think she stayed sometime in Bengal, maybe 1 year or so, in the school. Must be in Calcutta. And she has, 10 times she changed her school in 10 class. Her father was all the time traveling. North and east, north and east. MBBS onwards. Then UK and US. But I think she was, I didn't mention that she was also a director of Translational Health Center, Delhi. But I think she's in sabbatical from being executive director. She has gone back to CMC.
But for some reason she resigned. That's what news.
Not resigned, it is on sabbatical. I think she wants to go back to clinic.
Hello.
And that is a more of a bureaucratic position, like I am doing all the time.
Yeah.
No, but I think she wants to go back and she's doing. That is what, Wellcome Trust has created a lab for her.
Most of our intelligent doctors, they are not involved in research.
That's what, this is.
Hello. So,
Word beyond this.
I know.
you can start.
Good afternoon. I think we will have the presentation made by Dr. Somu Chatterjee, who has received.
2017, Ashutosh Mukherjee Award.
This is, who has received the Ashutosh Mukherjee, Sir Ashutosh Mukherjee Award, which is given to the best thesis presented from Indian Association for the Cultivation of Science by a panel of judges. And this program we have started from 2017. And this year, the recipient is Dr. Somu Chatterjee, who has done his thesis work under the tutelage of Professor Amlan Jyoti Pal in the School of Physical Sciences. And this is, incidentally, this is the second best thesis from the same group. And now I think floor is open for Somu to make the presentation. Your presentation is, you know the time.
10 minutes.
Please go ahead.
So, good afternoon, everybody. And first of all, I want to thank the organizing committee. Oh, okay. So good afternoon, everyone. And first of all, I'd like to thank the organizing committee and the committee that has given me the opportunity to be here. It's an honor for me, and it's a pleasure for me to share a few slides of my research work with you in the next few minutes. So as my research title suggests, that I have mostly done my research on thin film solar cells, and these are based on sustainable or environmentally friendly materials. Now, solar cells actually does not need any formal introduction. We all know about them. We actually use them in our daily life very frequently. And they actually convert solar energy directly into electricity, and by the means of the photovoltaic effect. So if you place your solar cell outside in the sun, what you get is a solar energy incident on it, and you finally get the electricity out of it. But the uniqueness and the novelty of my research title actually hides in the two keywords here. Sorry for the interruption. So the novelty of my research work lies in the two phases of my research title. First is the thin film, and second is sustainable materials. So what I have done in my last 5 years of research career, that I fabricated semiconductor thin films using mostly low-cost solution-based approaches. And then I have used environmental friendly materials, and these materials are always beyond silicon. So I'm trying to move away from silicon, and in order to introduce the next generation of solar cells.
Sound is not coming.
So all these materials are non-silicon. So we are moving towards the next generation of solar cells, which are based on non-silicon materials, but they should contain earth-abundant and non-toxic elements in order to avoid the cost of the materials and their health hazards. So right now, I need to move away from silicon. I think these things need to be discussed, because if we compare silicon with the other, right now, the other research materials of solar cells, then silicon is mostly the most abundant material in earth crust, and therefore it possesses also a lot of other properties that makes them a good solar energy materials. But the problem with silicon is that their cost of production is very, very high, and therefore only a few countries in the world have the stock of the silicon, and therefore the other countries need to buy from them and then align the other parameters and assemble the solar cells here. Unfortunately for India, we have to also buy this thing mostly from China and other countries, and then we assemble the other materials and other gadgets here, and then we sell them in our normal market or traditional markets. So if we compare the price of cost per watt, which is the figure of merit of solar panels in market, then the overall cost per watt in the global scale is way less than $1. Whether here, if you need to buy a solar panel, furbished solar panel from any online store or in any other store, the price is around ₹60, which is close to $1. Now there's a difference of almost 6 times or 7 times, and this difference because you have to purchase the raw materials from other countries and you have to assemble the other things here. So what is the way out? How we can actually reduce the cost? The first way out is to use non-silicon materials, what I have done here in my research tenure. And second, you have to move away from the conventional approach of silicon making and other crystal making to the thin film deposition, because thin film foundries are easier to be actually produced here, and therefore it is the future of solar energy in India as well. So I'm talking a lot about the materials and silicon. So if you're moving away from silicon, then what are the properties that you should look for in another material? And here's a list of them. And the first property is very, very important around the optical bandgap. Now, it is a straightforward method that if you correlate bandgap with the color of the thin film, it is easier to detect, because if a material has a white bandgap, its color is quite whitish, whereas the bandgap is a low bandgap material, its color is quite black. Now, it is quite easy to understand that if you place a black material in front of the light, then obviously it absorbs light very well. Similarly, if you make a solar material which is blackish in color and then put it in the sunlight, it will absorb sunlight very well. And people have done theoretical studies and shown that the optimal optical band gap should be around 1.5 electron volt. There is a very significant paper on that. I'm not going to be in depth of these things, and there are other parameters as well. So based on all these properties, people have actually figured out that a lot of materials are potential materials in order to replace silicon in solar cell fabrication. There are some organic materials like this P3HT and PCBM on top, you can see. There's a bottom left one, the PBS, it's a very unique solar energy material as far as the inorganics are concerned. And there is a hybrid materials, the perovskites or methyl ammonium lead iodide and these analogs are coming into the scenarios right now. And they have almost outperformed others in terms of materials engineering and device applications. And therefore they are right now called the crown prince of material dynasty. So what I have done in my research tenure, I have fabricated and synthesized a lot of nanostructures, and then from there we have moved to the thin film form of these nanostructures. And CZTS, PBS, all these materials are solar energy materials, and I have fabricated them in our lab under Professor Kumlan Pal's supervision. And you can directly fabricate the thin films as well, where you use the Szilard technique, which is a very well-known technique, but it's quite unique because you can just repeat the sequence of this 4 precursor solution dipping, and you finally get a very good quality inorganic thin films, mostly chalcogenides and oxides, in order to convert them finally into device structure and the solar cells. And then after fabricating the solar cells, I characterize them mostly by current voltage measurements, because in solar cell, when you put them into sun, what you get in the output is current. So when you characterize them in your lab, we actually put a bias across the solar cell. Then we change the bias in small steps and measure the current out of it. And from there, we get the current voltage characteristics, and we can calculate the efficiency of the solar cell that's well. So these are some efficiencies that I have recorded in my lab, and you can see starting with a very low efficiency by changing the device structure and the materials, we have finally achieved close to 13% efficiency, which is almost 1 order of magnitude improvement in my research career, and the improvement is endless. So the process is ever widening. So in a nutshell, what I have done, I have mostly characterized and fabricated thin film solar cells in my research tenure. I have used low-cost solution-based approach because these are the future for India. And sustainability of the materials are also in concern, and reproducibility and device structures and all those stuff also be taken care of. So I'd like to acknowledge Professor Pal for giving me the opportunity to work in his supervision, DST for the financial support, IACS, my present and past lab mates, and also my parents and relatives. And thank you for your kind attention as well.
Let's keep change.
Just 1 minute. Sharing the stuff.
আমি এরকমই পেয়েছিল। ঠিক আছে। এটা কি? Congratulations. You can take it. What's the next program?
Next program is their program now.
Now the program goes on. Chinese. English. Hello. Hey, can you mute it? Mute.
Scientists and society, right?
We're going to start.
Science, scientists and society. Yes. So master পড়েই পড়তে হবে। So আবার সব ভুলভাল মিউজিক আসছে ফেসবুক start.
So,
Welcome everyone to this live presentation. This is the final round of the essay competition, Indian Science, Society and Scientists. So we have the authorities and the governing council have shortlisted 10 essays from the numerous essays that we received. And out of these 10 people, 5 people will be winning the final prize. And we shall be moving on to the presentation round. The first person to present will be Devashrija Mondol from IACS semester 5. So if you are here, kindly can you share your screen and start your presentation?
You have to admit Devashrija.
There's a waiting
Ma'am,
room.
she's already okay.
Please admit, okay.
Excuse me, I think the screen sharing is still disabled. If you could check that kindly.
Yes, sure.
Yeah, sure.
No, sir, only now we will look at our screen only.
Yes.
Pin
We don't need this screen.
কি নাম আছে
Devashrija Mondol.
She's from ICS, right?
Yes.
Okay.
এটা তাই তো
Yeah.
এটা
Yes.
সবাই গেল one participant can share.
One participant.
Can share all participants.
Trial run on Friday.
Start sharing information.
Can start sharing.
সেটা বলে participant করার দরকার নেই তাহলে
Only.
ঠিক আছে।
এবার ask the question you are enabled.
Can you just yeah.
Yes, we can see.
So you can just enter the presentation mode and the timing.
Yes, please give me a moment.
The maximum time will be given to you is 10 minutes.
So try wrapping it up from 9 minutes, and then from 9 minutes we will be giving you a reminder, and at the 10 minutes we shall ask you to stop.
Okay, can you just give me a moment, please?
Yeah, sure.
Yes.
See that all a notice to all the participants. All the participants will be judged on the basis of their presentation, how well you are presenting your essays and creative work, and you will be marked accordingly. And then the final score will be declared.
Yeah, can you see my presentation now?
Yes, Didi, we are able to see yours.
Yeah, sure. Okay. So, hello, I am Devashrija Mondol, a UG third year student from IACS Kolkata, and I feel really honored to be given this opportunity to present my thoughts on the topic Science, Scientists and Society, which I feel is a rapidly evolving dynamic where one cannot function without the other two. Science is as much as a tool as a way of life. If we use it well, we progress, as did human race when early humans discovered the uses of fire or fabricated a wheel. We could definitely call them scientists. If we do not use it well, its ramifications rain on us. There have been examples of bioweapons, product of science, but they caused profuse harm. It is thus the responsibility of scientists to realize it themselves and make citizens realize the same fact. Now, along with knowledge-based efforts, scientists have major social responsibilities that fall into 4 main categories. Number 1, advancements in biomedical research. Number 2, assisting policymakers to make sustainable choices where there is a possibility of adversely affecting the environment. Number 3, helping to improve the quality of human life by pioneering technological advancements. And finally, to help propagate this knowledge to the next generation by means of teaching. I have also listed some examples of scientists who have made significant impacts on society and the human race with respect to the responsibilities that I have mentioned. Earlier, it was thought that the disengagement of scientific thoughts in the more political aspect of policymaking was a desirable thing. So scientists also chose to remain aloof so as to not affect their credibility as the disseminators of knowledge. However, with technological and scientific advancement of society as a whole, it became imperative that scientific knowledge should be applied in administrative matters as well. It did not always yield desirable results, though, as we could see in the Einstein-Szilard letter in 1939. Nevertheless, the benefits quite outweighed the pitfalls like these, and we must also note that some discoveries came purely out of academic interest. For example, no one even imagined the existence of a nuclear bomb at the time when the structure of the atom was being discovered. This continued to the present era as scientists work on a huge variety of experiments with the same fervor. So popular culture has often portrayed scientists as slightly crazy introverts with a reckless disengagement with the world around them. For the movie I'm talking about, called Mahapurush, the same has occurred, with Professor Noni, played by Santosh Dotto, being an eccentric, rather misunderstood character with a noble cause but misplaced plan of work. As his foil, we have Birinji Baba, a self-proclaimed clairvoyant godman who speaks pseudoscientific nonsense and makes even the educated members of society lap it up. It is interesting to note how pseudoscience has tried to win over scientific belief with charisma that scientific communication often ends up lacking. However, we are gradually bridging those gaps. One of the major ways we are doing so is popularizing science through social media. For every self-proclaimed mystic like Teal Swan, we have dozens of pages and Facebook groups and YouTube videos and blogs that dispel these blind beliefs. We see that if a concept is well explained, the public would accept it readily as they are actually interested to know more about the advancements in science. For scientists themselves, taking to social media gives them other benefits like directly connecting to the public, networking with like-minded people, and connecting with administrators. Even after all of this, we do notice a general discontentment between scientists and the general public. The public trust in the scientific departments of a country is often low in some places, and the dynamic still represents a sort of walled garden that only a few can get across. With scientific studies conducted across the world, we could see that there are some concurrent issues that I have listed over here. For example, let's say there's a
reminder, sorry to interrupt you, like it's actually 5 minutes, okay, like 1 hour program as had been communicated earlier to you guys.
Okay.
Just please accordingly, and it would be very great if you could just please put on your video, because you know, right, like we are
please give me a moment. Yeah, am I visible?
Yes, you're perfectly visible. Okay, sorry for the interruption, you can continue.
No, it's fine. So should I continue?
Yeah, so you have 4 minutes up and 1 minute more left.
Okay, cool. Thank you. So we see that despite all of this scientific advancement, there is a lot of blind belief that is still popular in society, simply because there are, during education, students are not encouraged to ask questions and test the facts that they are taught. They are often encouraged to blindly believe in them. And India is a multilingual country, so I think we require more of the scientific communication in regional languages, which I feel is still lacking. And there are places where blind faith statements could be corrected with scientific explanations, but the scientific community often chooses to not do anything about it, thinking that it might cause some kind of discontentment along public in public forums and the like. Now we see that the earlier images of the research lab, that is one scientist and a few graduate students like-minded, it's no more the case. Research labs are now collaborating across the world, which is very much similar to the way that society should, the members of society should collaborate with one another. The principles of scientific thinking, that is free speech, free thought, the power to question, all of these are actually basic rights that citizens in any democracy should enjoy. And in the ideal case, the hierarchy of professionals in the lab is the same as the hierarchy of the different members of society. Now, I have talked about how scientists and science influence society. So does the opposite also occur? As we see, it definitely does, because there are scientists who are working in order to make the lives of other common people who are not directly involved in scientific endeavors much easier. For example, we can see that there are two persons that I have shown the profile of here who are having different priorities, but none of them would be able to function fully without the other. Without knowing the needs of society, the scientists would not be able to always understand what they should prioritize on. And without the scientists, the society would not progress.
Sorry to interrupt you again. So could you please just wrap up now?
Yeah, sure. This is the last slide.
Sure.
Yeah. So for spreading and popularizing science in the society, the scientists have to bridge the gaps. First of all, there are endeavors that are going on in trying to popularize science among people by encouraging them to do science, to test the facts that they have been told since childhood. We see there are people like Arvind Gupta and Gopal Chandra Bhattacharya who have spent their whole lives trying to do the same thing. We see that people are actually understanding the need for scientific research, especially during times like these, when the COVID vaccine, when we are all looking at scientists for developing a COVID vaccine, and we see that they have been quite successful. So with all of these, I can conclude that the scientist and society dynamic is not one that is meant to fizz out or die out. Rather, it requires people to get involved more and more in this sort of a dynamic where it would help society to advance as a whole. Thank you very much.
Okay, so thanks a lot for that. Wonderful presentation, really. So with this, we would be moving on to the next speaker. So it is Sanindya Das. Are you here?
Yes, I'm here. Am I audible?
Yeah, you're audible. So could you just please put on your video and share the screen?
Yes, sure.
Yeah. So general note for all. So if it would be very great if you could all introduce yourselves a little bit, a 1 minute thing or 30-second thing. That won't count in your presentation time.
So 1 minute. Yes. Is it visible?
Yeah.
Okay. So very good afternoon to everyone. I am Shanidho Das. I'm a UG1 economics student from Jadavpur University, and I am really privileged and honored to present my writing with you all and in this very occasion of National Science Day 2021. So before I go on further, I would like to thank the organizing committee, esteemed judges, and my fellow participants for this wonderful day. So to start with, I have given a very short introduction of my work. It starts with that a harmless try to captivate minds to uproot the present people in power for the sake of science, scientists, and society in India. So it's basically a try to pursue the ideas where the people, the present government or the people in power, which they are propagating fallacies in our world, in our India. So here I start with the idea of nature, nature with the concept of chaos, that is also can be regarded as entropy, or can be said by the entropy. So here the thing which I want to say that nature, in an effort to create, 1 minute, this thing. So nature, in an order to create chaos, create some pockets of order. So these pockets of order are things which promote the chaos. So suppose let us consider a bucket full of water. So when I drop a bucket full of water, say from a 30-meter height of a building, so the chaos that would be created would be much greater than a glass of water. So it simply says that to efficiently create chaos requires some order. Now, in our day-to-day life, we see that there is a triangular relationship between science, scientists, and society. So suppose I draw a triangle. Here, suppose this is science, this is scientist, and here it is society. So science develops society's ideals and thoughts and how it develops and everything. Society in turn gives scientists or produce scientists, and scientists in return develop the concepts of science. So this triangle helps to create a major development in the system, and also which increases the entropy. So that in a way, it actually maximizes the disorderliness by creating the order in the society. So to maximize the entropy of the system, we need to have science and technology. But today's scenario is quite different. The influential people, that is namely the present government, has taken a great leap of responsibility in promoting unscientific hoodooism and abstract nationalism and religionism. So as a result, we see cow science. Also, what it promotes is collecting gold from cows, and also how killing of cows brings destruction to the civilization. Yes, it is true that cows are part of the nature, and killing them might destruct the nature too, but it is not only constricted to that part, but it also to the other parts of the other animal species too, and mostly for the endangered species. Cow is nowhere close to endangered species, I guess. So now, what are the stands of scientists? So scientists, most of them have wholeheartedly reject such nuisance, and there are very few of them who have mentioned nothing about this system, about these ideas of hoodooism and all this, and probably they are acknowledging the unscientific norms, people in power, for any reason possible. So here the idea of Hindutva has been mentioned, so I am not going to the details, but we can surely understand that there, by Hindutva we cannot be advanced. There cannot be advancement in food industry or other sectors of development, may it be research or anything. So I want to say that it is a shame to nurture the very idea of religion to not proliferate the advancement of scientific and technological growth. I'm not against religion, but the thing is the very idea of non-proliferation of the advancement of scientific and technological growth. Because there's a basic trade-off. Suppose you are making a temple or a mosque and you are giving some funding to that. In place of that, if you would have given some science, if you have given funding to science labs, parks, eco-promoting zones, then it would have been a better service to the society as a whole. So scientists are an integral and influential part of the society, and we see that people also, like from Jacobian University, people are going against this bullshit, as I mentioned, like cow stuffs and all those, and they are against this unscientific, illogical, and illegitimate things. And we are we have went through the struggle of independence, 2 centuries of struggles, and we should not offer our independence and strive back to this dependence of unscientific, illogical, illegitimate bullshit within 7 decades.
Sanithya, your 4 minutes is over. You have got just 1 minute to wrap.
Yeah. Sure.
Please refrain from using derogatory words.
Sorry. Okay, then last, I would have used here a very I have used terms like democracy. I have changed the word from democracy to democracy ruled regime, which is being going on, and which is proliferation, which is continuously proliferating the non-scientific ideals and decreasing the investment in scientific innovations and human resources. And lastly, I would end my presentation by the lines of Allen Ginsberg. Here he says, Moloch, incomprehensible prison, Moloch the crossbone, soulless jailhouse, and Congress of sorrows, Moloch, whose buildings are judgment, Moloch the vast stone of warheads, and Moloch the stunned governments. So here, basically, the idea is that incomprehensible prison. This prison can be the prison of the jailhouses, or it can be the prison of our own self, the mind, the irrational thoughts, which also you can see in the poetry of Rabindranath Tagore. So these are being promoted by our present government, stunned government rather. So too, I would like to conclude my essay by saying that to maximize the entropy of the system, we need to have some order, and that can be only be created by the people who are like scientists, rational people, influential rational people, to promote scientific ideas and stop the proliferation of non-scientific establishments and fallacies. To develop a nation, the nation builders must acknowledge science, scientists in the society, and not illegitimate religious divides and hoodoo.
Sorry to interrupt you,
Thank you.
Sanithya. You need to stop.
Yeah, I'm done. Finished. Thank you, everyone.
Yeah, thank you. We have Sohan Biswas as our next speaker. Sohan, are you here?
Yes, sir, I am here. I am audible?
Yes, you're audible. Please switch on your video and.
Yes, sir. Am I visible?
Yeah, please switch off your video. You're present. Yes.
Okay,
So,
sir.
you may present your screen and start your presentation by introducing yourself. Thank you.
What is his name?
Okay,
Sohan Biswas.
Sir, is it visible?
Not yet.
Mobile. It isn't visible yet.
Hello, sir. Is it visible?
No, it is not visible yet.
Approximately by 25 years ago, Los Angeles experienced a massive power blackout due to an earthquake.
Yes.
Okay, yes. Okay, yes,
Please
please
start,
continue.
yes.
Just introduce yourself a little bit and then continue.
Yes. Thank you. Approximately 25 years ago, Los Angeles experienced a massive power blackout due to an earthquake. The entire city was just thrust into darkness. The emergency call service, 911, was inundated with panicked residents reporting a giant silvery cloud was engulfing with the sky. Unknown to the callers, they were seeing the Milky Way, the galaxy continuing our solar system at the night sky. Some of these urbanites had never before experienced a non-light polluted sky. Greeting, good afternoon to everyone. All of you respected judges. Yes, sir.
You can just introduce yourself a little bit at front. Like it would be easier for the judges to guess you and mark you on that.
Which stream and which year?
Please repeat
Your
again, ma'am.
stream, your year. Your stream, your year. If you could please kindly mention and introduce yourself.
Yes, ma'am. Just little bit. Greeting, good afternoon to all of the audience and the judges. I, Sean Vishwas, a student of Botany UG first semester in RKM VC College, Rahoda. I'm going to give a presentation on the topic Science, Scientist, and Society. I believe that there is holy nexus between science and society and scientist at the connector to it. But sometimes the holy nexus become unholy due to overuse of science and scientific products, which affects on to our existence. So, on behalf of the topic, today I would like to give a short presentation on pollution-free lights powered by microbes. I'll be glad if audience and judges ask their queries after the presentation. So let's move on my next slide. So what is light pollution? Light pollution is the presence of anthropogenic and artificial light in the night environment, can have serious environmental consequence, focus for the human, wildlife, and our climate. There are many types of light pollution like glare, sky glow, light trespass, and clutter, etc. So let's move my next slide. What is the effect of light pollution? Now artificial lights overpower the darkness and our cities glow at night, disrupting the natural day-night pattern and shifting the dedicated balance of our environment. The negative effects of the loss of this inspirational natural resource might seem intangible. For example, sea turtles, hatchlings, and puffins move away from sea at birth, mistaking the artificial light for moonlight. Astronomy is very sensitive to light pollution. Sky glow reduces contrast between stars and galaxies and sky itself, making it much harder to see fainter objects. It also affects on human hormonal system as well as other ecosystems in the world. So, bioluminescence, an alternative to light pollution. Commonly, bioluminescence is the emission of light by living organisms. It is a chemobiological process seen in some animal, fungi, algae, and obviously a huge number of microbes. Bioluminescent bacteria are light-producing bacteria, maybe free-living, such as Vibrio harvey, or in symbiotic position or terrestrial. Bioluminescent bacteria have luciferin in their cell that metabolized by an enzyme called luciferase. That's the heterodimer of Lux A and Lux B genes. The products of the reaction include oxidized flavin, mononucleotide, fatty acid, and energy in the form of blue-green visible light. Various tests are conducted by isolating the genes and intertesting in E. coli to obtain the desired results, glow for longer period and less pollution. So let's move on next slide. That is bioluminescence and future world. Glowy, a startup company based France, has developed a microorganism-based material that produces bioluminescence, just like fireflies, glowworms, and over 80% of marine organisms, including jellyfish, plankton, and squid also. The light it produces can light billboards, infrastructure, storefronts, and streetlights. Hence the goal of working with energy companies, municipalities, and architects to better understand how bioluminescence could be used in future. There is a concept of biobulb. The biobulb is essentially closed ecosystem in a jar. Biochemistry major Michel Jaikin said in the Rocket Hub speech. It also conserves exhaustible natural resources like the rare metals used in LEDs, reduces the pollution generated by traditional lighting systems. The technology emits 10 times less CO2 than the LED bulbs that are normally used to light storefronts. This soft light is easy on the eyes, help reduces light pollution and non-disruptive to existing natural ecosystems. The lifespan of the material has increased from a few hours to 7 days. The CEO of Chloe, Sandra Day, said that, I believe that all the solutions to our biggest ecological challenges are right under our nose. The pictures are some examples of using bioluminescent products for our future world.
Sorry to interrupt you. Your time is almost up. Please wrap up within a minute.
Okay, sure. So ecologists have entirely ignored the potential disruption of ecological system by an artificial night lighting. Frontiers in Ecology and the Environment reviewed that ecological light pollution includes chronic and periodically increased illumination, unexpected changes in the illumination, and direct glare. They also described that the light pollution this puts a serious implication for the community ecology. H. Wang and Z. Ren, two China scientists, wrote on the paper in the support of microbial electrical system on a platform technology. Pollution-free lights by microbes in India. Though our country is reaching a high-risk pollution in light, but day by day, we cannot see the direct involvement of our Indian scientists about the topic pollution-free lights powered by microbes. Though various famous business organizations are really curious about the marketing of bioluminescent microbe light products, in foreign it is a well-known product of marketing. Our scientists are now innocent too about that. We hope we could see our scientist involvement about that. We can use the products very soon. To sum up my presentation, I think concepts of pollution-free light powered by microbes is very positive to our world. Think one day our great-great-great-grandchildren have to live in the sea, as we the human before them have used all the resources. So they had to be submerged to survive, and this what a world with no electricity and no energy. So the light will be provided by jellyfish, microbes, or squids. But hope, the science will not be so cruel as we think, because we human will overcome the impossible to do something like that. I'm very glad to participate in this competition organized by IACS, and special thanks to International Dark Sky Association, TEDx University, Standard Ray, and some YouTube videos. Thank you, everyone.
Thank you, Sohan, for a beautiful presentation. Now we have Ronak Chakraborty. Is he there in the meeting?
Hello, am I audible?
Yes, you're audible. Please, can you please switch on your video and you can start your presentation?
Unfortunately, I can't because I don't have a web camera in my desktop. Is it fine if I just present my presentation with my voice?
Okay, it's fine.
Okay. Thank you.
Start your presentation.
Is my screen visible?
Yes, sir, visible.
Yes, it's visible.
Thank you. So I am Ronak Chakraborty. Hello, everyone. It's a great pleasure and a great honor for me to present a presentation on such an interesting topic, science, scientists, and society. I am studying UG first year in Vivekananda College, Thakurpukur. I am in my first semester. History has proved that man is a curious animal who has walked miles to make sense of the world around and beyond him. Delving deeper into his own mind, man has created arts and philosophy, while trying to comprehend his surroundings and all its phenomena in a rational manner, man created science, with the help of which our human civilization has been progressing. Now, one may ask, what exactly is science? Science for me is the art of observing the nature around us. It largely consists of conducting experiments to either make sense of the world or to come up with something new, an invention that would help us to move forward. Observation, experimentation, and analysis, these are the integral parts of science one must go through before he can come to any conclusion or make a final statement. Now, scientists, science, and society, these three things are completely interlinked. Scientists, with the aid of science, help in the development of society and in improvement of the living standards. Any scientific research, however, needs funding, resources, and time. And for the former two, scientists are solely dependent on society. Science has catered to the society's needs every now and then. The early half of the 20th century witnessed a massive advancement in nuclear physics in order to create a weapon. Although successful, it brought along the losses of lives numbered in lakhs, the decimation of 2 cities, and the radiation from the bombings that persisted for several years after. However, scientific research is often like that. It does give us invaluable knowledge and facts, but the utilization of that knowledge is solely up to the discretion of our society. While talking about how society and scientists, they influence each other, we can talk about another series of incidents. The accidental discovery of moevine, a purple dye by W.H. Parkin in the 1856 England. W.H. Parkin was trying to synthesize quinine while he stumbled upon this dye, and this dye became a fashion sensation among British and French aristocrats, and hence organic chemistry took a giant leap forward due to the massive increase of interest in it. Scientists, as vanguards of science, are still people. They have wishes, dreams, and ambitions, and this fact is clearly proven by the concentrated research that we can see in the societal needs, such as cancer research, AIDS research, to further cure these things. While we are talking about the viability of scientific research, we have to talk about how society treated a lot of our brilliant minds. Notable Italian astronomer Galileo Galilei faced life imprisonment for promoting the Copernican model of solar system by the church. He was imprisoned for the rest of his life. Henry Oldenburg, the founder of Royal Society in London, was also held in the Tower of London and interrogated for several months for exchanging correspondence regarding scientific research with his colleagues across Europe. Giordano Bruno was prosecuted, and ultimately it led to his execution due to promoting the cosmological model of Copernicus. More recently, Alan Turing was prosecuted for being homosexual, and he was chemically castrated with estrogen injections, leading to his physical deformity and mental instability, and ultimately causing his death. Scientists are often stereotyped. Like all professions, people have a large perception of scientists, and large parts of our society think that scientists are antisocial and work alone in dark laboratories while squealing eureka once in a while. However, that's far from the case. That's far from the case. Scientists often work in large groups, and they have to communicate with their fellow scientists in order to ensure better results. While discussing society's perception, we should remember how often scientific advancements are associated with a particular person or a brand. All of us have heard the name of Elon Musk and his company Tesla, or Steve Jobs and his company Apple. But while entrepreneurs like them are integral to these breakthroughs, the teams of scientists who work tirelessly for these projects are often not acknowledged. I might have led you to believe that it's all dark and negative, but it's far from the case now. There have been scientists who have tried to explain science in layman terms and influenced countless minds to wonder, to question. Scientists have massively reshaped the thinking of modern society through books, lectures, documentaries, and various other media. Here I have put a few pictures of famous scientists and their popular science works. On top left, we have Richard P. Feynman with his legendary books on physics. On top right, we have physicist George Gamow with his popular science book 1, 2, 3, Infinity, which contains a lot of fun puzzles and mathematical and physical explanations of phenomena. On bottom right, we have popular science writer Martin Gardner with his book The Night is Larger, which is a collection of 47 essays that he has compiled over the years during his tenure as a popular science writer.
Sorry to interrupt you, Ronak.
Yeah.
Time is almost up, so
Yeah, I'm almost done.
wrap it up within 1 minute.
Yeah. As I have said before, science and society are linked intricately. Science and society have a complex relationship. They influence each other, they further each other, and they push each other forward towards more and more development. Scientists in this saga are the interlinking agents or bridges who tirelessly keep illuminating the path of truth ahead of us while pushing aside the ominous mist of ignorance, and they guide us towards the gleaming light of knowledge and absolute truth. To end it all, I would say that one cannot restrict scientific advancement and progress within the walls of a certain region or a nation. We have to work together as a civilization, as a species, to better our living conditions, to further our understanding of the universe. And like Pastu said, science knows no boundary because knowledge belongs to humanity and is the torch which illuminates the world. Thank you.
Thank you, Ronak. It is a very interesting presentation. Now we have with us Ritam Roy. Is Ritam Roy present in the meeting?
Yes, am I audible?
Yes, you're audible. Thank you for switching on the video. You can start your presentation. And please introduce yourself at the beginning.
Yeah, absolutely. Good afternoon. Good afternoon, judges. Good afternoon, audience. Thank you for, it's a privilege to participate in the National Science Day program of the IACS. I am Ritam Kanti Roy. Sorry.
Okay. Please share your screen. We cannot see your presentation, unfortunately. Okay, yes, it's visible now.
Is it visible?
Yes,
Yeah.
it's visible.
Okay.
Carry on.
I am Ritam Kanti Roy. I am a second-year undergraduate student at Bidhannagar College. I am pursuing physics. My today's topic is science, scientists, and society. And for this, I would love to take you on a journey inside my mind. Okay, first of all, I'd like to discuss with you the idea of science. According to me, there is no perfect definition of science. I mean, till recently we were high school students, we would consider it just a subject to secure marks. Currently, most of us see it as a means to secure a stable profession. Our seniors and peers would tell us that it is quite an interesting medium where they search for answers and discover new topics. So science is just something that breaks stereotypes, that helps us discover discover new facts about our surroundings and explain the unknown truths of the universe. Okay, so I would like to take you to the very beginning of the evolution of humanity. Science first evolved as a means for coping with our necessities. I mean, the first scientists would be classified as the people who discovered fire or the humans who discovered the wheel. They were all born out of coping with the necessities. The ancient civilizations, we see from archaeologists that the ancient civilizations had often devised wonderful mechanisms and technological, I mean, medieval but primitive technologies. So they were the early scientists. The Middle Ages was kind of a dark time for science. The people in power always tried to dictate the direction in which progress would be made. But since the last 2 centuries, with the advent of technology and machinery and the boom of the industrial civilization, the whole dynamic has kind of shifted. Modern science, I feel, is currently being fueled by just curiosity. Science has branched into 2 counterparts. One is driven by necessity, and the other is fueled by pure curiosity. Now, I would like to walk through the character of a scientist. We have an existing stereotype that a scientist is just a mad introvert, disconnected with the world, and we kind of forget always that they are but normal people. Scientists were, I am a student of physics, so I have read about ancient scientists who were actually philosophers, and they always tended to theorize on certain topics they couldn't understand. This gradually evolved. This free school of thought was gradually aided by rationalities and proofs by different experiments. Scientists would just be people who have something different to say. They try to answer their own questions and in turn help the society. Now, science and society would be the connection between science and society has been a bit of a rocky road. Society has been benefiting from necessity aided science since the advent of time. I mean, the previous examples like the discovery of fire or the wheel, or in more modern times, we just had the COVID pandemic. The vaccines are gradually being distributed throughout different countries of the world. So science does make the world a better place. But is that the only perspective? I say no. Because in the last century, we would remember the devastating effect of the atom bomb, the result of the Manhattan Project. The Manhattan Project took together all the mainstream theories of modern physics and formulated a deadly weapon from all of them. So that isn't to be expected. Now, being an Indian, I would like to talk about a bit about the Indian perspective. The National Science Day is celebrated as C.V. Raman's Nobel Prize anniversary. So it also helps us young scientists in the making to live up to their expectations. I believe that the Vedic ages gave us pretty rational thinkers and world-class, I wouldn't say scientists, I would say philosophers. You have Aryabhatta, in Aryabhatta Brahmagupta in mathematics. We had major advancement in medical sciences by Charak, Shushruta, etc. In the last century, we have had pretty huge names in the field of sciences: Jagadish Chandra Bose, Prafulla Chandra Roy, C.V. Raman.
Can you please wrap up your presentation?
Absolutely.
Time is almost.
So even currently, we are leading the world in some particular sectors of science. I would particularly like to mention astronomy. Now, I would like to look towards the future, the human standpoint. Science has the power to benefit the human race as a whole, but it has also the power of massive destruction. So as young scientists, I would believe that we intend to only do good. As young scientists, we should promote racial equality, gender equality in the scientific field, and we should also try to educate the masses from our own perspective. Because if we don't bridge the gap with the society, I don't think science can thrive alone. This is a time-bound topic, so I couldn't discuss all my ideas. I would love if you would reach out to me and we could discuss it further in detail. Thank you.
Thank you, Ritam. Now we move on to our next presentation.
So we have Priyadorshan Chaki. Can you please present your screen and switch on your video?
Please tell me if I'm visible.
Yes, you are visible.
Okay. So, good day to everyone. I am Priyadorshan Chaki. I am a class 11 student from DPS Siliguri, Delhi Public School Siliguri. And I'm greatly honored to have been selected to present my presentation here in this celebration of the National Science Day. So what I'll be talking about is about science, scientists, and society. So nowadays, the prevailing trend in the science-society relationship is to engage with the broader public in a larger way, which is beneficial for the public also, and for the scientific institutes, for the findings of scientific occurrences, and the legitimacy of science as a whole. This so I will provide a broad review of the rapidly progressing research on open article sciences and identifying the gaps in the current knowledge for the future research. So The relationship between science and society has been discussed with increasing intensity and frequency, and its improvement has been the main goal of open science. Open science is a practice which aims to make scientifically generated knowledge and its method of production more accessible, applicable, transparent, and responsive to both the needs of the scientists as well as the public, the people who want to know what is being found out and what is it all about. These principles are also shared by the Responsible Research and Innovation Initiative, which is also concerned with the ethical, legal, and the social implications of research, but also addresses various types of actors in this entire thing, such as scientists, the policymakers, the educators, the business people, and the industry innovators and the civil society. Therefore, communication with the stakeholders, the people who are involved in it in every level, opening up the research process and engaging with the public in every sector seems a major trend of the science society relationship, both on the academic and on the institutional level. Several authors have described the importance of science communication and public engagement. Specifically, Eagleman in 2013 identified several reasons why science communication and public engagement with science are important. These include dissemination as a way of thanking taxpayers who fund most of the research. Further, scientists are also capable of inspiring critical thinking and initiate public debates within society, also as to correct misinformation from the media and other sources of information also, which bring up many sorts of false stories and all. Science is also important in improving law and public policy, in explaining what science is and how to deal with uncertainty related to various scientific ideas. The public should also know how beautiful and complicated the pursuit is. And as scientists are trained to think, write, speak, and discuss, they also must do so to educate the public. So to systemize current knowledge on the science-society relationship, there has been many reviews on the recent types of literature or the publications related to the relationships between science and the public. So the literature review drew on the most recent articles and books published since 2005 that are available in various academic databases like Google Scholar, like Web of Science. So this review is divided into 4 key topics: science communication, public engagement with science, public cognition of science, and the challenges of open science. So, how public is informed and learn about science. Mainly it is divided into this: science communication, how the public is informed about the various things that are found out, how people learn about science, how public engages with the scientific breakthroughs, scientific ideas that have been created almost every day with the citizen science and science education also. Public cognition of science, understanding, explaining to the public what actually is occurring out there, to place their trust in the talents and the skills of the people who are working out there, and the public knowledge of science. And also the last one is the challenges of open science, the risks related to it, the ethical concerns about what is being given out there, and the risks related to the giving out of types of data out there. So next, let's go to paper or people. More often than not in our systems, paper, that is all the written sort of the diplomatic part or the paperwork, becomes much more important than the people who are the major people behind it. Bureaucracy overrides meritocracy. Risk-taking innovators are shot down, most of them. Decision-making time cycles are much longer than the product life cycles. Therefore, the second grand challenge is that of creating an innovation ecosystem in which questioning attitudes and healthy irreverence can grow. So let's go to public engagement with science. Public engagement with science is a very broad range of techniques for transmitting the knowledge and improving the science-public relationship. Examples of these are science cafes, science shops, deliberative workshops, needs surveys, focus groups, and many others. In general, the techniques and activities of public engagement have evolved from science communication, as the preferred mode of science communication seems to be an interactive process, as has been proved scientifically also, closer to a dialogue than more than a one-way mass communication, sort of like a broadcast. In this process, the information transmission is also strongly interconnected with increasing science literacy and engagement of the public. So now communication in the media. It is one of the most important tools for the improvement of science education of the general public. Science education also serves as a prerequisite for effective communication. The disseminated information cannot be oversimplified, and thus some prior knowledge of the topic is usually necessary for the proper understanding. Although the complexity of the message challenges understanding by a layperson, a major simplification of the content in science communication would create a distorted perception of both content and science itself. Now, this pre-understanding of the concept itself is gained via the educational process or the informal learning. Now, learning by more traditional methods has its creative means also, has its merit also. So nowadays, the prevailing trend in science-society relationship is to engage with the broader public, which is much beneficial for the public, scientific institutes, scientific findings, and the legitimacy of science as a whole. The article provides a broad review of the rapidly growing research on open science and identifies the gaps in the current knowledge for future research.
Sorry,
so I would like...
Priyadarshan, your time is almost over. So wrap it.
Yes, ma'am, of course. I will wrap it up. I'm actually over only. So I would like to wrap my presentation up with a quote from J. Michael Bishop, a very distinguished immunologist from America. Science now finds itself in paradoxical strife with society, admired but mistrusted, boasting remarkable advances but criticized. And this is especially seen in a country like in ours, India also, where many people are there who distrust science, who distrust the authenticity of many scientific discoveries, who question the findings made by the people. So the objective of scientific understanding and science as a general, and those who hold the main pillars of science on their shoulders right now, is to make more and more of these people understand the importance behind understanding what is this thing all about, explaining them the eccentricities behind the working, behind the simple environment we have in front of us, all the complexities which exist behind this, which exist in this universe around us. So I would like to thank IACS for letting me present my presentation here. So I would like to stop my presentation here. Thank you very much.
Thank you, Priyadarshan. Now we can call upon Spandan Upadhyay to start his presentation.
Spandan, are you here?
Okay, so
Spandan
is not there, I guess. So let's just move on.
Let's move on to the next participant.
Okay.
Call her once.
Yes, I'm calling you, trying to contact her.
Supratim Haldar. Supratim Haldar is there. Okay, no. Then let's keep the slots and move on to Bishwadip Dey. You are there, right?
Yes, ma'am, I'm there.
So you can start your presentation. Please switch on your video and give a short introduction.
Can you see me?
Not yet.
Yes,
No,
we
you
are
can see
able
him.
to.
Oh, I see.
Presentation.
You can share your screen now.
Ma'am, I'm actually having a problem with the presentation.
You cannot share your screen.
With my presentation. Yes, ma'am. I'm having actually a severe network connection out here.
I see.
We have this presentation then.
But it's my laptop. Taking place of that.
You can come back later.
So
Can you please try once again as
How is the joining issue?
Vishwadip, can you again try sharing your screen?
Yes, ma'am, I'm trying.
Network.
But actually, it's not had. I'm having a severe network issue out here.
If you cannot share, you can just listen this voice.
Listen. Okay.
Loudspeaker.
Actually, আমাদের কাছে প্রেজেন্টেশনটা আছে দেন
আমরা কি ডাউনলোড করে নেব মানে আমরা প্রেজেন্ট করব জয়েন করে এখান থেকে
I think just listen up. What is it? That is enough. You can see.
But if he has sent a presentation, they can show. সেটা না প্রেজেন্টেশন মানে প্রেজেন্টেশনটাই আছে আমাদের কাছে
কল করে হ্যাঁ তো ask him to just
Vishwadip,
Yes, ma'am.
can you only like describe whatever you have presented or whatever you have shown in a creative work? You can just describe whatever you have written, done. You need not present the screen here.
Okay, ma'am. First of all, I would like to thank all the members of IACS who have given me a chance to speak today for this national creative work. So every year on 28th of February, we celebrate the National Science Day in the honor of the Pride of India, Dr. C.V. Raman, who won the Nobel Prize in Physics for his discovery of the Raman effect. As he was the first Indian to win a Nobel Prize in Physics. Sir Chandrasekhara Venkata Raman, which was the full name of Sir C.V. Raman, received the Nobel Prize in Physics in 1930 for his work on the property of scattering of light. India has always a rich heritage in the field of science, starting from Aryabhatta to Bhaskaracharya, from C.V. Raman to Srinivasana Ramanujan, from Dr. APJ Abdul Kalam to Dr. Vikram Sarabhai. India was always among the top contenders for becoming a land of wonders. Speaking of wonders, we cannot forget these great contributions for those scientists who helped in developing so much in technology and communication. All the scientists who were all ahead, probably due to which they had to face a lot of criticism. As we all know that Aryabhatta was the first mathematician who made the discovery of zero and worked out as the exact value of pi. He also covered a wide range of topics such as extracting square roots, solving quadratic equations, tracing ellipses. Bhaskaracharya was also known as Bhaskaracharya II, was a great mathematician and was a great mathematician. There was also another mathematician named Bhaskaracharya I who was known for finding an approximate value for sine and was honored by ISRO on 7th of June 1979. And on this day, ISRO launched Bhaskaracharya I, honoring this mathematician. During the British rule, one more mathematician was born from India who lives still in our heart as one of the greatest. His name is Srinivasana Ramanujan, and he's regarded as one of the greatest mathematicians who ever lived. If India has also a human computer named Shakuntala Devi, who was one of the greatest female mathematicians in the country. And during the last 21st century, India got his missile man, Dr. APJ Abdul Kalam. And there was C.V. Raman with his discovery which made him earn the Nobel Prize in Physics. What C.V. Raman has done, C.V. Raman won the Nobel Prize in Physics for discovering the property of scattering light, which was the second Indian to get a Nobel Prize after Rabindranath Tagore. With student K.S. Krishnan, he discovered that when light traverses on a transparent material, some of them reflected light changes wavelength and amplitude. C.V. Raman was born on 7th of November 1888. Tirupalli, and died on 21st November 1970 at Bengaluru. Besides Nobel Prize, C.V. Raman has also won the Bharat Ratna, Lenin Prize, and more. Now, over the years, the theme of the National Science Day was changing. Last year, it was Women in Science. On 28th of February 2009, 5 institutions in India were presented the National Award for Science and Communication by the Indian Department of Science and Technology. The highest award was given in 2009 to Vikram Sarabhai Community Science Center for its contribution to the science-related learning material and conducting training program on science education. A festival of measurement in space was held at the Nehru Planetarium, New Delhi. It is all done to encourage the technology in India. The day is more celebrated because C.V. Raman won the Nobel Prize in Physics for discovery of the Raman effect. It was in the year 1986 that the National Council for Science and Technology Communication asked the government of India to designate 28th February as a National Science Day to start to recognize outstanding efforts in the field of science and communication. It enhances people to know more about the world and its wonders to a scientific way. India is now progressing in a field of science at a very high pace. National Science is celebrated to spread a message about the importance of science used in daily life of the people. It is celebrated to discuss all the issues implement of new technologies for the development in the field of science. In the end, I would like to conclude that on the note that the National Science Day is a day to be remembered for. It's a day to remember for. It's a day to encourage the growth of science of our nation, a day to remember and respecting all the great scientists who helped in progressing in science to such a great extent. Thank you.
Okay, so Vishwadeep, could you just introduce yourself? You just missed that point. Hello, Vishwadeep.
Yes, ma'am.
Could you introduce yourself?
Yes, ma'am. I'm Vishwadeep from Rammohan Mission High School.
Which class?
I'm class 9. I'm class 9.
Okay.
Which institution is it?
Sir, Rammohan Mission.
Rammohan Mission is there.
Someone else has joined. So Akanksha, Spondon, Supratim, these three people, are you there? Join
Supratim Haldar, Akanksha Pal, are you there?
Spondon.
In the meeting? Spondon Upadhyay as well.
She has been able to join.
She's not responding.
So Akanksha, can you hear us? Someone is in waiting room. They're connecting that.
Okay.
Supratim Haldar is also joining.
Okay.
Supratim ke dite bolta na? Yes, we have called.
We are calling constantly.
Supratim
Haldar, are you here?
It's Akanksha Paul is here. You can ask me.
Where?
Akanksha, are you here?
Yes.
Okay, so you can start your presentation. Please present your screen. Switch on your video, please. Yes, sir.
Akanksha?
Is she removed?
No, I don't think.
She was there.
She was there.
Waiting room ta dekho.
Waiting room ফাঁকা।
I guess again problem holo.
Internet issue.
So we have Supratim here. You can continue in the meanwhile. Supratim, can you hear us? He's there. Yes, sir. Hello, Supratim, can you hear us?
Hello, sir.
Yes. So can you please start your presentation by sharing your screen and turning your video also on?
Introduction.
I think he's unable to hear.
Supratim, are you able to hear us?
Excuse me.
Yes.
Yes.
Sir, I'm having some network issues. That's why I'm not able to hear you clearly. Can I please rejoin?
Yes, sure.
Okay.
এদের প্রেজেন্টেশন তো আমাদের কাছে আচ্ছা তাহলে যদি ওই না হয় তাহলে তুই ইউ জয়েন না জুম লিংক দিয়ে তুই নিজের ল্যাপটপে জয়েন করে প্রেজেন্টেশন পাঠিয়ে না
ওকে ওকে হ্যাঁ হ্যাঁ correct.
and ask them for the description and we can change the slides
Yes,
accordingly.
yes, that's perfect. I think he's rejoining.
He's
in the waiting room.
Waiting. Admit.
He got
Hello.
Yes. Am I audible?
Yes, sir.
Yes. So you can start your presentation. Please switch on your video and present your screen.
Sir, please let me join with my PC then. I'm actually joining with my mobile phone.
Yes,
Sorry
please.
for the inconvenience. Sorry, sir.
No problem. Please join.
yourself.
So, the subject around 35,000
কি উড়ে যাবে? হয়েছে।
Science includes the basic like biology, earth science, space science.
Akanksha,
Yes.
Can you please again begin with your introduction and presentation? Now all will be able to hear you perfectly.
Yes, there was an audio problem.
There was
which
an
has been
audio
resolved.
problem on our part.
Start with my introduction too.
Yes,
Yes,
absolutely.
yes, please, please.
So, I'm a student of class 9 from Mahindra High School.
Okay.
And this is my first presentation. So I'm very nervous because that we don't know how to update number. But still, I will try to do my best. So I started the first bit of my presentation with introduction of science, or like from the Latin word scientia, means knowledge. And science is systematic study of various things in nature and its roots can be traced in ancient times of Egypt around the times of 3500 to 3000 BC. And it has various conclusions in different fields of mathematics, astronomy, which has helped in many ways. So science has many branches and 3 branches especially, which are further divided into small categories. The first branch is natural science. This is divided into 2 more branches, including basic and applied. Basic branches include physics, chemistry, biology, art-based science, while the applied branches include engineering, agricultural science, medicine, and material science. The second main branch is social science, which includes in its basic form anthropology, economics, political science, sociology, human geography, and psychology. And the right form includes administration, public policy, marketing, law, pedagogy, and international development. The third main branch of science includes formal science, which is basic form includes logic, mathematics, and statistics. And the applied form includes groups of human science. Scientific researchers have helped us in many ways, discovering and inventing many things that are very useful to us. Previously, man used to do everything manually, but now we came to everything with the help of machines. These are the results of scientific researchers and discoveries and all. So, the next thing we come to is scientific method. Scientific researches involve using scientific method, which helps us to produce different various objects. Then there is the scientific community, which is a group of interacting scientists. So, scientists are the individuals who conduct scientific research and who make various inventions, discoveries to help make people's life better. So, the term scientist was termed by William Weevil in 1833. In modern times, professional scientists, teaching trainees, and different academies, and they receive a degree. A very famous scientist was Albert Einstein, who was a German-born scientist, and we all know about him. He developed the theory of relativity, and he won the Nobel Prize in Physics in 1921 for his work in theoretical physics. The last page describes science and its types. So, science can be described as a boom or a curse, depending on how we are putting it to use. So, it concerns the public as well. If we put it to use in a good way, obviously help us to do useful things that can make our life better. But it can also be put it to use in some dangerous way. Like it can be used to produce atomic bombs, nuclear bombs. Then, due to scientific researches, different kinds of changes that create which are creating pollution, like the nuclear power plants. They are source of radioactive pollution, which is the most toxic nature, and which is the most toxic nature in other pollution. So they are actually harming us in many ways. Depends on how we are using it. And since it is a very important thing in our life, we should use it in a very should do our best to use it in the proper way so that it can be for the betterment of the people, lives of the people on earth. Okay. So, we can all your life future in ahead of us. Thank you.
Thank you, Akanka Paul. It has been quite a interesting presentation from you. Okay. Now we can move on to the next presentation.
Pratim Haldar, are you here?
Non-existent. Does not exist. Vanished.
Yes, sir.
Yes, Shupratim, we can hear you. Are you here?
Yes, sir.
Okay, so please begin your presentation by switching on your video and sharing your screen. Shupratim is chatting. Please share your screen.
No, share. No, too much.
Hello, sir.
Yes. You are audible.
Sir, is my presentation visible?
Yes. So you can start by brief introduction of yourself and then you can continue.
Well, I am Shupratim Haldar and I study in class 9 in Raman Mission High School. Okay, sir. So can I start, please?
Yes, please start.
Science, scientist, and society. Science is the systematic study of the physical universe and its contents by means of observations,
Sorry for a small
measurements.
interruption. Hello, can you please zoom in a bit? Actually, we cannot see your presentation. Yes, you can put it in your landscape mode or you can zoom in. Yes, yes.
Okay.
It's fine now. Continue.
So is it visible now?
Yes.
Yes, fine.
Science is a systematic study of the physical universe and its contents by means of observations, measurements, and experiments. Scientists have an important role not only in avoiding inappropriate and dangerous decisions, but also advising policymakers and other stakeholders about the best and wiser moves to make towards a human-centered society, thereby fomenting scientific knowledge and enhancing cross-cultural connections and joint research. They should also not forget the objective limitations of science, which is always incomplete. Science, which has given so many blessings to mankind, has also simultaneously created instruments of destruction which can annihilate the whole world in no time. We cannot underestimate that science can not only heal, it can also kill. However, the society is not immune to eventual serious unintended consequences. Scientists have to be alert, therefore, in not only avoiding inappropriate and dangerous decisions, but also advising policymakers about the best and wisest movements to make science having a human-centered society is advantageous to everybody. Natural science is, in its modern form, can fairly be said to date back no further than 17th century. With Bacon as its Saint John the Baptist, it developed its gospel and its ministry. Curiosity for its own sake, but also interest in industrial techniques and practical control, freedom of inquiry, experimental verification in place of authority, full publication, and abundant discussion. With these, a truly new phase was inaugurated. During the dark ages of the West, the Arabs kept the scientific spirit alive, and by means of their mathematical inventions, paved the way for immense improvements in the technique of scientific research. Marx, on the other hand, developed a system directly based on social facts and directly applicable to them. Now, vaccination is a particularly important issue to think about here. Given the rise of anti-vaccination, anti-vax movement, that has the potential to reverse the health gains achieved uh, through one of the most powerful interventions in medical history. Researchers estimate that between 1963 and 2015, in the US alone, nearly 200 million cases of polio, measles, mumps, rubella, varicella, adenovirus, rabies, and hepatitis A, and approximately 450,000 deaths from these diseases were prevented, thanks to the development of a human cell strain that allowed vaccines to be produced safely. With Leonard Hefflich's discovery of W138 in 1962 to safely grow the viruses needed to produce vaccines against more than 10 diseases. The anti-vax is an emotionally charged phenomenon disrupting healthcare, uh, undervaluing many vaccine preventable diseases that have become much less common, like smallpox and polio. It is based on flawed debunking of a chronological but not casual relationship between vaccination and autism, based on falsified and discredited study by Andrew Wakefield in 1998 that has since been shown to be fraudulent but often highly cited. Vaccine refusal is not just a problem for unvaccinated children, measles outbreaks, but for everybody because it endangers the health of an entire generation of children, lowering local herd immunity. We stand on the brink of a technological revolution that will fundamentally alter the way we live, work, and relate to one another. In its scale, scope, and complexity, the transformation will be unlike anything humankind has ever experienced before. We do not yet know just how it will unfold, but one thing is clear. The response to it must be integrated and comprehensive, involving all stakeholders of the global polity, from the public and private sectors to academia and civil society. As Klaus Schwab, founder and executive chairman of the World Economic Forum, exposes in the Fourth Industrial Revolution 2016. This fourth industrial revolution is characterized by a fusion of technologies that is blurring the lines between the physical, digital, and biological spheres. Ubiquitous mobile supercomputing, artificial
Sorry for interrupting. Just a gentle reminder. You have just 1 minute left.
artificially intelligent robots, self-driving cars, neurotechnological brain enchantments, genetic editing. The evidence of uh, dramatic change which is happening at exponential speed is all around us. Even if we cannot live without IT, we should not forget that its use is not free of risk. Social media webs so efficiently for agglutination of attention and not appropriate for public discourse. Given their volatility, they are uncontrollable, unstable, short-lived, and amorphous. uh, Appear suddenly and disperse with the same speed, showing a lack of stability, consistency, and credibility. As the Korean philosopher Byung-Chul Han 2017 argues, digital communication enables instantaneous impulsive reactions, being in fact responsible for the disintegration of community and public space. Uh, Science and its borders. The continuous appearance of new scientific discoveries, some by serendipity, like the usefulness of some drugs, or the law of gravity, which was discovered after Newton observed the falling of an apple, shows that science has no borders. Science quest for knowledge about reality presupposes the importance of truth both as an end in itself and as a mean for resolving problems. We would like to add to these considerations that there is a need for a bridge between science and religion because both have things to say about the same subject matter. They are different ways of studying the same territory. They have different kinds of things to say, and and their contribution to make to the efforts of human to cope with life. Religion without science is superstition, or as Einstein said, science without religion is lame. Religion without science is blind. Ake 2001. Consequently, science and religion should not be seen as a conflict forces. On the contrary, they have to progress and share the same pedestal. In spite of their limitations, scientists can play an important role in favoring a human-centered society, which suggests a few simple examples of how this may be done. An international team of experts, after estimating that as much as 85% of the US biomedical research effort is wasted, has recently produced a manifesto with a master plan to improve the quality of scientific research, to perform good, reliable, credible, reproducible, trustworthy, useful science. Who are responsible for improving quality of science? Not just the researchers, but also the other stakeholders such as research institutions, scientific journals, funders, and regulatory agencies. Fomenting science, knowledge, and enhancing cross-cultural connections and joint cooperative research have to be their main goal. Conclusion: all stakeholders have to be conscious of the importance of investment in science, fostering scientific knowledge through the interconnections between all its branches with an open mind, transdisciplinary approach, enhancing joint research and cross-cultural connections, and providing funds not only focused on real-life problems but also on the fundamental uh, tenets that will underpin the future of a human-centered society. If development of science is important, what is even more important is human development, that is, development of human beings themselves, which is all about growing up truly to human beings capable of governing themselves and the universe through the well-balanced development of science, art, and religion. Thank you.
Thank you, Shubha.
বাচ্চা বলে প্রেজেন্টেশন কি সেই টপার বোঝেনি কিন্তু এগুলো লিখেছে আমার ওইটাই খালি প্রশ্ন
We have just one participant
তো যা এসে লিখেছিল তার
trying to join.
সেটা জানা
After that, our presentation session will come to an end. Thank you.
এটা এসেটা লিখেছে মানে তার মানে আলাদা করে প্রেজেন্টেশন বানায়নি
ম্যাম এসে প্রেজেন্টেশন সব
Phone তুলছেন এখন।
He's the only one.
Yes, yes.
এই আশিস ডাক্তার এখানে শ্রীমন্তরা আছে নাকি
ঠিক আছে।
Who is this person?
So this is এটা বাস ঠিক আছে, এটা ঠিক আছে, বাকি যা শুনে শুনে।
Okay, so this is the presentation of Spandan Upadhyay, a class 8 student at Rammohan Mission High School. Unfortunately, he is unable to present himself, so I'm just sharing the slides, sharing his slides, and presenting on his behalf. The title of his presentation is Science, Scientists and Society.
Do that all the time.
দাঁড়া দাঁড়া, ক্লিক 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 করো, নিজের থেকেই চেঞ্জ হবে।
So, some of the earliest records from history indicate that 3,000 years before Christ, the ancient Egyptians already had reasonably sophisticated medical practices. As far as historians can tell, the first true scientists were the ancient Greeks. Remember, science consists of collecting facts and observations and then using those observations to explain the natural world. Although many cultures like the ancient Egyptians, Mesopotamians, and Chinese had collected observations and facts, they had not tried to use these facts to develop explanations of the world around them. So after the first few centuries AD, however, the progress of science stalled dramatically. By that time, the Roman Empire had a great deal of influence throughout the known world, and Rome had a distinct dislike of science. The Roman Empire did not mind inventions, especially those that made work more productive, but it had little use for the practice of explaining the world around us. As a result, real science was actively discouraged in most parts of the world. Alchemy is one of the best examples of what passed for science during this time period. Alchemists mostly wanted to find a means by which lead could be transformed into gold. You see, many people had observed the fact that when you mix certain substances together, they change into other substances. Alchemists saw changes like the one you saw in your experiment and thought if they were just able to find the right recipe, they could mix lead with several other substances and make gold. Of course, we know that this is impossible because we know that there are several limitations on how much one substance can change in a chemical reaction. You will learn all about that when you take chemistry. The alchemists didn't know this, however, so they strove to mix substances after substances with lead, hoping one day they find the magic mixture that would turn lead into gold.
So interestingly enough, even though the ideas of Rome held a great sway in most of the known world, the Roman Empire itself began to crumble. As that happened, trade and large-scale communication became harder and harder, since science thrives on the free exchange of ideas from one scientist to another. This puts another roadblock in the way of scientific progress. Many historians refer this period as the Dark Ages, because compared to the previous time period in history as well as the next time period in history, little was learned. So here we find another lesson we can learn from the history of science. Scientific progress depends not only on the scientists, but it also depends on government and culture. Since the Romans actively discouraged science and concentrated on inventions, the progress of science slowed. Since the crumbling government caused trade and communications to become more difficult, scientific progress slowed even more. For science to proceed, then the government and the culture must support it. Towards the end of the Dark Ages, the real science slowly began to emerge again, thanks mostly to the Roman Church. It might seem equally obvious that the natural world must obey certain laws. However, that kind of thinking was relatively revolutionary at the end of the Dark Ages. Now realize that this kind of thinking wasn't really new. It was just different from the predominant idea of the day. After all, Greek scientists like Aristotle and Ptolemy also believed that the natural world could be explained by laws that did not change. Nevertheless, that part of their thinking was mostly ignored during the Dark Ages due to the influence of the Roman thought. Grosseteste thought that a scientist should make observations and then come up with a tentative explanation for why the observed events happen. The scientist should then make more observations to test his explanation. If the new observations confirm the explanation if the new observations contradicted the explanation was probably wrong. And this essentially the method that we used in modern science. Thus, Grosseteste is often called the father of the scientific method.
The 16th and the 17th centuries, 1580 to 1780, were incredibly exciting in the history of science. The excitement took off in 1543 when two very important works were published. First and most celebrated today was published by Nicholas Copernicus. It was a book that laid out this idea about the Earth, Sun, planets, and stars. Like Nicholas of Cusa, Copernicus believed that Ptolemy's view of the universe was wrong. Rather than placing the Earth at the center of everything and believing that the Sun and planets traveled around the Earth, Copernicus placed the Sun at the center of everything and assumed that the planets, including the Earth, traveled around the Sun. This view was called the heliocentric system because Helios is the Greek god of the Sun. Sometimes, however, it's called the Copernican system in honor of Copernicus. Nevertheless, the Roman Catholic Church publicly denounced Copernicus's work and put his book on the list of prohibited reading. That's all.
नाम और स्पंदन
स्पंदन उपाध्याय
So we now formally come to the end of the presentation session. Thank you to all the participants who participated in it. And thanks to the audience as well. For listening so patiently. The winners will be announced at the end of the video presentation, which we will be having now.
আজ প্রথম পাঁচজন
They are not.
ঢুকতে চেয়েছে কি?
Okay, so the results of the essay writing of the final results of the creative writing competition, which was held as a part of the National Science Day, is ready now. We will be announcing the results. So our director, sir, Professor Shantanu Bhattacharya, will be announcing the name. Sir, please. It's fine.
Good afternoon. This is the results of the competition on the scientists and society. The essay writing and subsequent oral presentation. This has been examined by a 3-member committee, and the results are as follows. We have participants from various states, but I think the following people were selected to receive the prize. Devosrija Mandal, first.
IACS.
She is from IACS undergraduate program. Number 2 is Raunak Chakraborty. What is it?
Raunak Chakraborty is from Vivekananda College.
He is from Vivekananda College, Thakurpukur. Supratim Haldar.
Rammohan Mission High School.
He is from Rammohan Mission High School. Number 4, Spandan Upadhyay.
Rammohan Mission High School.
He is also from the same institution. Number 5 is Priyadarshan Chaki.
DPS Shiliguri.
Is from DPS Shiliguri. Number 6 is Vishwadip Das. Is from Rammohan Vidyalaya. Rammohan Mission Vidyalaya again. Number 7 is Ritam Kumar Roy. He is from Bidhannagar College. Number 8 is Akanksha Pal. He is from Ramon Mission. And number 9 is Shohon Bishwas. He is from Ramakrishna Mission Rahada. Congratulations. The first 5 will receive a cash prize of rupees 5,000, which will be transferred online. So you should actually give your bank account number, and the rest will get 3,000 each. Again, the bank account number are needed. Congratulations again.
So now you can say that this last part is over, and when are going to start the second part?
15 minutes or half an hour.
13 minutes.
Just announce, just announce.
So the creative writing competition has formally come to an end. We just now heard the results of the top performing participants. So we will be starting the second half of our program in just half an hour.
Thank you.
Thank you.
These all the sessions.
Just mute. Is Tapas coming?
Sir, actually,
No. He said you start, he will join better. So,
What are we going to do now?
they have made that video.
Video about institute.
Yes, sir. So that day.
This will be for how long? 10 minutes, 15 minutes? Half an hour?
No, 2 or 10 minutes.
Oh my God. Who is going to sit through that?
তো দেখতে পাচ্ছেন না, এটা রিমোট দিয়ে করা যায় না?
What is this other fellow? Agro?
Okay, so we have entered into the last phase of the program. So it's a short documentary made by us about different labs at IACS that we had visited. So under normal circumstances, there are lab tours organized on National Science Day. But this year, due to the unforeseen COVID situation, we have demonstrated this thing in a virtual mode. So you can take this as a virtual lab tour. So we hope that all of you will be enjoying this. We shall be sharing the screen shortly.
শেয়ার করতে হবে।
Screen share.
আর audio?
After that, audio. I think সেটা দেয়া আছে।
We work in various different areas which are interdisciplinary in nature.
we work at the interface of chemistry and biology and material science primarily. And any field which is required to solve a problem, we get into it. Sometimes little bit of biophysics, sometimes little bit of engineering we get into, so that we solve a problem. We try to solve a problem, and most of the problems are of such a type where, disciplinary boundaries are not there. So where disciplines meet, there actually you try to get into. One such problem we get into is chemical biology. Chemical biology and synthetic biology involve different type of new application of chemistry in the drug design, in understanding different cellular processes, in epigenetics, and various other current phenomena. As this is a developing field, our understanding is growing, so we try to ask questions, different types of questions. For example, we try to mimic virus. Now, essentially, in this opportunity, we try to create synthetic systems which will mimic virus. So it will make a complex with nucleic acids, different forms of nucleic acids. Nucleic acid will have either DNA or RNA, and then now even CRISPR-Cas9, which is the latest sensation. So we are working on all of these things and try to implement that after incorporation in different cells and see whether specific areas we can target and we can achieve some function. So our idea is that if you can deliver nucleic acid and you try to look for expression of the protein, and then quantitatively you can find out whether your delivery vehicles are working appropriately. So this is one area that we are active. Another area we are active at is involving non-canonical nucleic acid structures. Normally, if you look at nucleic acid literature, overwhelming percentage of DNA remains in the Watson-Crick double-stranded helical form. But lots of interesting things happen. For example, Holiday junction and various other cellular events, you will find that it adopts structures which are not necessarily Watson-Crick structures. So we are interested in these kind of secondary structures which are non-duplex structure. So they could be four-stranded helix, G-quadruplex. We can have structures which could be I motif, C motif. These are various types of structure depending on the sequence that is available, and try to synthesize molecules which stabilize them. Now, the significance of these comes in telomere biology. Telomere biology is a very fascinating field which has been recognized a few years ago with a Nobel Prize. This has relationship with your aging. This has relationship with cancer. And therefore, such kind of research will give you potential opportunities for drug design. Okay, so this gives you some idea about, our activities in the area of chemical biology, medicinal chemistry, and so on and so forth. I mean, we do whole gamut of things. I'm just giving you examples. We also work on biophysics of biological membranes. So here, either we isolate natural lipids, or we synthesize naturally occurring lipids or their analogs, and try to establish a structure-function relationship. So if you have a molecular structure, they form bilayer membranes, and then you try to characterize using whole lot of physical techniques, for example, electron microscopy, cryo-electron microscopy. You use techniques like line width broadening using NMR spectroscopy. You use calorimetry to measure their phase transition because they undergo thermal phase transition. You know why archaebacteria has one kind of lipid and whether animals have another kind of lipid. They have different molecular structures. And how do you try to generalize? So in order to do that, you need to have a quantitative structure-function relationship so that you will have some kind of a predictable basis towards that. So you work towards that. So these are membrane biophysics, and since we also make the molecule, which makes it more interesting, so we call it molecular membrane biophysics. So these are tailor-made systems which are not only naturally occurring, but it could be different from naturally occurring. And you know, most of the naturally occurring lipids are through, biosynthetic process. Therefore, their structures are depending on what series it is. It could be glycerophospholipids, it could be sphingolipids, or it could be, different glycolipids. So they have specific functions, and lipids are fascinating molecules, and they don't remain as single entity. They actually undergo self-organization once they are in contact with water, because lipid molecules are amphipathic molecules. They will have fatty acid tails and polar head groups, and therefore this is a schizophrenic molecule. So they will behave little differently in presence of water. They try to hide their hydrophobic parts and expose their polar parts to water. And in the process, what they call is a cell. Cell means you will have an habitat, you have an interior and exterior. So what we do, we try to entrap solutes in that and try to see their transport. If you have appropriate solute will actually try to come out or go in depending on the osmotic pressure gradient. And so this gives us miniaturized picture of cell. And once you build with lipid vesicles, then you can add different types of players which are there in biological membranes. You can add different proteins. Protein could be traversing through the lipid bilayers. It could be associated on the surface, either integral membrane proteins or peripheral proteins, and then try to see these lipid protein complexes and try to analyze them, the effects, again a structure function relationship, because then only you will be able to have a quantitative understanding of what goes on. Now this is about our interest in the area at the surface of chemistry and biology primarily. When you form a lipid vesicle, which is the miniature of this biological membrane, which is an oversimplified version, it does not have any address delivery code. So what you need to put is a delivery code through an immune recognition system. So if you want to drive it to particular cell, you have to find out what is their recognition repertoire. If you have that, then it will be targeted to that particular cell. And then if you actually can entrap certain solute could be a drug, it could be a pathogen, it could be many things depending on your design vesicles and the material that you would like to entrap within it. And you would like to see whether it can deliver there. So first of all, you have to go to the right cell or target tissue, and there it has to be delivered. So first of all, you need to create the targeting liposome. So for targeting, there are strategies. One can actually add different types of, antibody functionalized liposomes. I think we have just published a paper very recently. You can look at it. And various strategies are available. So one can actually functionalize lipids with such type of system. Now you have to functionalize lipid molecules with such systems and then incorporate in the liposome in order to achieve such kind of goal. But there are challenges in doing so, because while it is going inside, there are various types of enzymes which it has to traverse through, and those are not necessarily will allow you to, pass through that circulatory system, because these enzymes would chew up. If you have lipases, they will try to hydrolyze your lipid molecule. You can have, if you have protein molecules, for example, protein molecules, if they are open, bare, those protein molecules will be proteolyzed. So there are events of this kind. There are tricks that one has to follow to protect, and at the same time your job will be to deliver it to the target zone and then do its job. I think there are, this is an area which is fairly active in a worldwide scenario. So it's a very active area of research. I think, we work on soft matter, which you have not been interested, but soft matter is very important. You people are interested in taking, so many soft type of foods. Foods are essentially soft matter, And have you asked yourself, what is the relationship with the softness and its taste? Because many of them are food. There is a relationship, and this relationship is purely physical. We have a taste transduction mechanism. There is a signal transduction molecule, but that again would depend on factors like rheology. Rheology means flow. Okay? This is, many of these things are, this kind of materials are non-Newtonian materials. So they don't, fall under the influence of gravity. They try to retard. And that kind of systems, many of them are soft materials. Okay, if I will give you a very simple example. If you try to boil rice, what happens? You have suppose once the rice becomes tender after boiling, there is an extract which is in water, which is a turbid solution at high temperature. You keep it separate, and after some time it sets into what is known as a gel. So since this is in water, this is a hydrogel. Now this will have many physical properties. So I am just giving you examples. Many natural products in contact with water, they will form that. Similarly, there are many synthetic molecules which can do this. They can also do in different solvents. So there could be application in oil spills. If this is oil soluble, it will, suppose in an ocean bed, you have an oil spill, it can selectively pick up that oil. So there are applications which could be very interesting. There could be entrapment of enzyme in this kind of system, but their interior structures are different from that of typical micelles and vesicles. So again, this is a fundamental area of research which we call it soft matter. Another type of activity we work on is creation of sensors. Now what is sensing, all of you know. So you try to find out whether we can detect an analyte in a very small concentration, sub-nanomolar concentration, or even lower. And if this analyte is a biological analyte inside your body, then it could be a very attractive target for you to estimate its concentration, because this could be an indication of a disease. Many markers are there. It could be an enzyme. For example, I will give you a very simple example. We can have uric acid, all of you know, and you go to doctor sends you to a pathological lab and try to find out. We try to make very simple systems, and we try to analyze in blood whether we can measure uric acid at a concentration which is pretty low. So if you can develop such kind of systems, they would be not only give you new insights in pathological detection, but also it's an advance which will be very useful for mankind, because you can detect them at a concentration. If it is lower than the currently available standard, then it should be possible for you to make it useful, because much at the beginning of the onset of any disease, you should be able to figure it out, their presence. I think there are various kinds of, you all must be aware of determination of blood glucose. This is there are technologies which have been developed. People measure by, putting a probe inside the blood, and one can find out how much concentration of sugar. I mean, sugar is not only thing that needs to be measured. There are various other causative molecules which are consequences of abnormal metabolism which could be measured, and that could have value in medical science.
So we had learnt in our class about various spectroscopic methods. So now here we are seeing many instruments. So practical application of the spectroscopy we are being able to see. So if you could little bit in short tell us a glimpse of these cutting edge research instruments that we can see.
Yeah, okay, so thank you, Nayan, for raising this point. See that in our laboratory, mostly we use various spectroscopic methods, particularly high resolution spectroscopy. And specifically, you can see here that different this laser-induced spectroscopy. Now, the detection methods that we use, this is actually an apparatus where I use this laser-induced ionization followed by mass spectrometric methods to investigate some of these fundamental issues of the chemistry. One of the very fundamental issues is, you can think about, it's the hydrogen atom transfer. Okay, so hydrogen atom is the lightest atom, and the transfer of this hydrogen atom from suppose this donor to acceptors, it involves many complex chemistry. So one of the things you can think about that in the photosynthesis, one of the major issues is this electron transfer followed by proton transfer. So electron-proton coupled transfer is basically a hydrogen atom transfer, although it is also a reduction process. So what we do here to understand the very, very fundamental issues of the that is involved in this chemistry, we take the different donor-acceptor complexes. Now, one of the pertinent complex here, the donor particularly, which can donate this hydrogen atom, is the phenol moieties. So we take the phenol as well as we prepare the complex, and this complex is prepared in the gas phase, so that these environmental interferences are removed. And then what we use here, a technique what is called the supersonic expansion. It's a very similar kind of supersonic expansion that you can see here when the jet flies. So under this condition, keeping the molecules isolated, you can create a situation where the temperature is very low. So very low means that we can get these isolated gas phase molecules and molecular complexes at temperature about 10 Kelvin. So at this low temperature, what we can do that if you use this laser, you can selectively excite the molecule to specific different vibrational levels. So in other words, that you can energize the molecule very selectively. Under the thermal condition, what happens that if you just heat it up, you have in a molecule all different degrees of freedom, vibrational degrees of freedom, rotational degrees of freedom, electronic degrees of freedom. But if you want to make some selective excitation, that if you put some energy to this particular mode, how the chemistry is going to be evolved. So that is what we try to do here. So basically this hydrogen atom transfer chemistry, but these are this involved apparatus that is required, that once you try to understand this chemistry at this very basic level. This is one thing. And this secondly, this another mostly our laboratory is actually, it's the cryogenic laboratory. This is a system at this moment that although just work has been slowed down for this apparatus, but it is a very productive apparatus in our case. We prepare also this kind of molecular complexes, but in an argon environment. So this argon is not gaseous environment. This argon is cooled down to temperature about 7 Kelvin. So at this temperature, argon solidifies. And what you do that you just dope your molecules and molecular complexes in this solid argon. Now solid argon, basically it's a refrigerant medium. Being inert gas, it does not have much kind of this chemical influence. But what happens that it gives a low temperature environment. So you can see here again, if you energize these molecules, how the chemistry under this low temperature, that is cryogenic chemistry, which is also important in many of your astrophysical processes, that becomes important. So that's what we try to do with this apparatus. And secondly, that we have also other activities here, particularly many of these atmospheric processes. One of these important atmospheric pressure is the oxidation process. Like many of the pollutants which are released into atmosphere, they are mostly removed by means of this oxidation process. So how this oxidation process in presence of the sunlight, they actually take place in the gas phase, that's what we try to understand. Taking some of these model pollutants which are typically emitted by the automobiles and many different kind of industries. Yeah. So that is the basic aspects of our research here. And for the techniques, other than these, for a long time, we also have used this laser-induced fluorescence spectroscopy. So that method also, we use only under this cryogenic condition in the supersonic jet expansion. Okay. Now, if you have some specific questions about some of these apparatus, that how it is working, that the PhD students who are actually doing this work, they would be able to give you this more detailed information on this.
We are in Professor Tapos Chakraborty's lab, and we are with his PhD candidate, Dr. Priyali. So if she could kindly explain to us the working principle and a little bit highlights about this particular instrument.
As sir mentioned that this is the laser-induced ionization and mass spectrometric system. This is basically a time-of-flight mass spectrometer. Here particularly we take some kind of volatile molecules, and this is the sample chamber where these volatile systems are there. Initially they are heated and vaporized, and then there are supersonic jet expansion technique that is used in this case to produce these molecules and molecular complexes, particularly hydrogen bonded complexes with very low temperature, we can say, that is in the lowest vibrational and rotational states that could be possible with this system. And then these molecule and molecular clusters, they are ionized with the laser light. So this is the ionization chamber where the molecular beam that is intersected with the laser beam, and these molecules are ionized by absorbing 1 or 2 or 3 as required number of photons of a particular laser wavelength. And then these ions are actually reflected upwards by applying some voltages to there are some plates, electronic plates, and which are called electrodes. These ions are then vertically, they are reflected upwards, and they are allowed to fly through this region, which is a field free region. And these ions, all those ions with different mass, they are allowed to fly through this region with different kinetic energies or different velocities. So the ions with the lighter ions, they actually move faster through this region, and there is a detector upward, which is the microchannel plate detector. It detects the traveling time of this ion. So the lighter ions move faster and they are detected at an earlier time. And that signal, that is actually recorded with this scope. This is the oscilloscope, and we can get a response of voltage against the arrival time of these ions, and this arrival time then can be converted into their mass. So we can get the time of flight mass spectrum for different kind of ions with different masses, and we can detect that which fragments are formed due to interaction of this laser light with this particular type of molecules or molecular clusters. And that is how we can actually detect some chemical reactions with this system.
This is our commercial FTIR instrument. You have learned spectroscopy in your classes. So here spectroscopy means molecule absorbs light and we get some absorption from there. And here we have chosen light in the mid-infrared region. That's why it is called FTIR spectroscopy, where the vibrational motions of the molecules are detected by this instrument. Here inside the setup, here it is a multipass absorption cell, means samples are taken here, and I have told earlier whatever the photochemistry and all other things which have done in our lab in some quartz cells, they are transferred to this multipass cell. Then we detect the infrared spectroscopy of this species. And second thing, sir have told about that matrix isolation setup. This is the matrix isolation setup. Here the molecules mixed with argon gases are frozen at 4 Kelvin. Here it is written 4 Kelvin. Inside this, the molecules are frozen at 4 Kelvin, and this instrument is situated inside this sample compartment when we use to detect matrix isolation spectroscopy of the gaseous molecules in the matrix environment. And in the multipass cell, since if we want to detect some trace amount of products which are formed after some oxidation methods or whatever, if we want to detect this low concentration, we have to take a larger pathway so that we can detect that concentration. That's why we have taken this multipass absorption cell here. Here, after entering the light, this light are reflected multiple times, and that's why the optical path length was increased, and we get larger optical path length. And using this multipass absorption cell, we can detect trace amount of products. This is the FTIR spectra of HCl molecule recorded in gas phase. Here you can see the rotational lines which you have studied in your class, I think, PR branches. These are the PR branches of HCl molecule, which is only visible in its vapor phase spectra, not visible in liquid phase and solid phase. So these are the PR lines of HCl molecule, and which is recorded by this FTIR instrument in the gas phase.
So now we are with Professor Shudit Ghosh, and sir, we have already learned in our 10+2 level about polymers and other associated fields. So sir, if you could please explain that what topics of supramolecular chemistry and polymers is your lab currently working on? If you could please explain the viewers.
Yeah, so we work on different aspects of self-assembly of polymers. So polymers are very well known in the biological domain. For example, proteins you can consider as a biopolymers, and you may know that the elegant functions that the protein do is due to their highly complex structure, which involves folding, interchain interactions, and also a tertiary structure. So these are the inspiration for polymer chemists like us who are interested in exploring synthetic macromolecules for a predictable self-assembly and functions, and we particularly use hydrogen bonding as a tool to kind of program self-assembly of pi-conjugated systems and polymers, and look for their properties like surface functional group display, their interaction with biological systems, and to some extent their applications in drug delivery, antibacterial property, charge transport, etc.
Now we are in Professor Shurit Ghosh's lab, and we have with us a research associate, Gargi Di with us, and now she is going to, Gargi, if you could please explain about this.
This instrument is called as GPC, means gel permeation chromatography, and it is used for the determination of the molecular weight of unknown polymer. So here you can see this is mainly the polymer peak of unknown sample. Here we have determined is by the calibration curve of any known polystyrene or reference sample. And here this is the x-axis is considered as the retention volume, and here the y-axis is considered as a refractive index. So by this we can calculate the weight average molecular weight and number average molecular weight of unknown polymer sample. And this is the column, the guard column. So initially we inject the sample here, and then through these it comes and here inside the column is there of acrylate, polyacrylate gel or polystyrene that is used for the column. So about the molecular weight variation, it differs the different polymers, and they show the different molecular weight of the polymer.
So now we have with us a senior research fellow, Sukanya Di. So Sukanya Di is going to tell us about microscopy. So Didi, over to you.
So hi, I am Sukanya. So now I am going to give the features of this. This is the whole setup is the fluorescence microscopy. So here we check generally the fluorescence property of the compound, whatever we have synthesized in our labs. It may be macromolecule or any small molecule. Generally we use this instrument for check the fluorescence property of polymeric sample which is uptaken by any cancer cell line. And here we use three different wavelength laser light, and at whatever dye we are used, as for our required we set the wavelength of that laser. And as you can see, this is we used the cancer cell line HeLa. So in this case we used the mitotraker is a dye which we strained this cell with this mitotraker, and after irradiating FITC laser we got this image. So like that way we take the images of our polymeric sample which we treated with this cancer cell line. That's all.
So we have learned about cell biology in our classes, but in your lab we saw that it is extensive work, very cutting edge research going on. So if you could kindly explain that out of the textbooks, how in practical life you are implementing this cell biology.
So yes, cell biology is, is a modern interest in the field of biological sciences. So to understand the cell, you need to know that how cells migrate, how cells divide, how cells adhere to the substrata, and what are the other cellular basic processes by which an organism can function. So there is a hypothesis that whatever disease we see these days are basically the malfunction of a cell. So in our lab we are trying to understand the basic cellular processes like migration, adhesion, and so on. So we work on particular molecules. It's an actin binding molecular motor protein we call cytosolic myosin 2, which basically provides the force, or it also can help to sense the substrata. And so we are trying to understand the myosin molecules as well as the basic cellular processes. We use many techniques like molecular cloning, and also we use various microscopic techniques like fluorescence microscopy, electron microscopy to visualize how cells are behaving, and also what is the localization of this type of protein molecules. And also we use different techniques like qPCR, quantitative PCR, and and mass spectrometry to analyze the, that PTM, we call post-translational modification. These are the basically modifications happen to the molecule to change their property. So these are the all, molecular level, you can understand that how molecules are being changed during their function.
So we are here at Jana Sir's lab and we are surrounded by a plethora of beautiful instruments. We'll have Ditipriyadi lead us today about the experiments.
So this is qPCR, which is just like the normal polymerase chain reaction, which is quantitative polymerase chain reaction. And this basically we get to know what is the quantity of the initial sample and how much it has got amplified. The reagent that we use is cybergreen for this particular instrument. So this is how we give the samples. And we get an amplification plot, and this amplification plot shows us the CT values for each of the targets. So the lower the CT value, the greater is the amount of sample or the greater is the amount of the target that is there in our reaction. This is how the plot comes, and you can see after I click the threshold, this is the threshold for each of the samples, and here are the CT values. This is ELISA plate reader by Thermo Scientific, and we use this instrument for measuring the OD of different experiments on the basis. We can measure fluorescent OD, we can measure, we do MTT assay with this, we also do Bradford assay, and we use it for measuring the enzyme kinetics. So this is the 96 well plate that we use, and we put it over here and we start the run. So I'm connecting to the instrument right now. So we are taking the OD of the samples at 570 nanometer, and this is I'm doing an MTT assay. So after taking the reading, we take our OD and then we analyze the samples or data for our later experiments.
So we are here at Jana Sir's other lab, and here we have the instrument for live cell imaging, and we will have Indranil Da to lead us now.
I am Indranil from Professor S.S. Jana's lab. So we did here live cell imaging for two types of live cell imaging. One is using bright field and one using laser for confocal microscopy. So I am showing here the bright field time-lapse imaging here right now. So this is MDMB231 cell line. These are the MDMB231 cell, a triple negative breast cancer cells, and I am showing you how to capture the image with longer period of time. So I am setting here 30-second interval and for 90 minutes, and then I am selecting this field, and I can use multiple field, and after that I can press the run. So again, now every 30-second interval the microscope can capture the image of these cells, and it will continue for how much time I have set here for. So I have set here for 90 minutes. So throughout 90 minutes, every 30-second interval, the microscope will capture this image. So this is MDMB231 cells, and this is the lamellipodial phenomena. And I treated, this is a LifeAct transfected, LifeAct GFP transfected cell, and I treat blebistatin, and after blebistatin treatment, finger-like spike structure is seen here. This before treatment and after treatment cells showing this finger-like structure.
We have been learning so much about organic chemistry in our textbooks, covered such a huge portion of our syllabi. So today we are at Professor Jordan Quinn Sir's lab to explore the practical organic chemistry and the research work being done in his lab. So, sir, if you could kindly suggest that what kind of work is being done, or throw some light on the practical aspects of organic chemistry.
Yeah, sure. So, as you learn that organic chemistry is very important, particularly the synthetic organic chemistry. So that means you are developing a new method to make a molecules, the molecules which is not available unless you prepare it. So that means the chemical synthesis is very important. And why this is important? With this chemical synthesis, you can make a library of molecules with a various functionality, and this is very important for many aspects like drug discovery, agrochemicals, material application. So if you do not do chemical synthesis, you don't have access to those molecules. In addition, I would also like to stress upon this point that there are several natural products which nature prepare, and we isolate from them, and then we find out this natural product is biologically active. Some of them, they are probably drug molecules, but when we isolate those things from nature, we get very small amounts. So in order to meet the requirement of the market or the society, you have to develop a chemical synthesis of the same molecules. So there also you have to design the chemical synthesis in the synthetic laboratory like this. So in that respect, obviously organic synthesis is very important. And in our group, of course, in IACS, we are developing different methods to make a synthetic synthesis of the molecules. And synthesis is very challenging, it's not so trivial, right? So one of the major challenge nowadays that the modern organic synthesis is how you can perform a reaction with environment-friendly condition. That means when you deal with the chemicals, there is of course, possibility that you're producing a lot of byproducts, and that obviously harming your environment. And the modern synthetic chemistry, it is very important you take care about that problems. So therefore, we have to develop a new generation synthetic organic chemistry, or you develop a new generation reagent for the known synthesis, where you will have a minimum effect on the society as well as the environment, right? So in that respect, in IACS, what we are trying to develop, particularly in this laboratory, we try to develop aerobic oxidation chemistry. So that means we are doing a oxidation chemistry using air or molecular oxygen at the source of oxygen, oxidant. And as you know, the air is expensive, not expensive, and it's a green oxidant, and end of the reaction, the byproduct is only water, which is perfectly environment friendly, right? So that is one area we are working. We are also trying to develop a new catalytic reaction, because catalytic reaction is also very interesting in terms of sustainable organic synthesis, because you use a very small amount and that catalyzes the reaction. Therefore, you produce, you don't need a large excess of reagent, and at the same time, you can avoid production of or the formation of chemical byproducts. Okay, so in that context, our group in IACS, we are dealing with a visible light catalysis things and also asymmetric catalysis. So asymmetric catalysis is particularly important nowadays because our whole body is made of chiral materials, and when you deal with the drug molecules which you have a stereogenic center, so one of the enantiomer would be important for drug activity, other probably not. So in that respect, what you have to do, you have to make a material enantiopure. That means only one enantiomer you are forming, not the other one. So if you use mixture, then you might have a poison effect. So you want to avoid that. For that, the best modern synthesis is the asymmetric catalysis. So that is also we are working here, and I think you will see all this technique later on, and you will see how we perform all those things. Yeah. Thank you.
So we are here at Joyram Sir's laboratory, and we see very sophisticated instruments here. We have with us Ishita Di. She is a student of Joyram Sir, working under Joyram Sir. So she would be explaining us the working principles and the techniques using these sophisticated instruments. So
this is fume hoods, and this is a ventilation kind of setup, and this is designed to limit the exposure of the hazardous chemicals from these labs, and there is suction fans over there, and it sucks the air from this lab and it protects the user from this inhalation of the gases. And let us suppose there is some accident or something that, and it works as a barrier in between the user and the occurrence behind these glasses. This is the working principle and the utility of these fume hoods.
So we have with us Saurabh Da. He will take us further through this working principle and the uses of this fume. This is a slank line or vacuum gas manifold which is used for setting dry condition or inert moisture free reaction. Now see, there are two manifolds, and one is connected with the vacuum pump and one is connected with the argon line, and the argon line is connected with the oil bubbler. Now how we set up reaction here? We first connect with the vacuum line and we create vacuum here, and after vacuuming this, the all air or moisture goes to this chamber, and after that we flow the argon here by using this oil bubbler to understand the flow of the argon. And now we connect it with the this argon line with this RB. Now see, there is a one line which is connected with the vacuum pump. Now first we vacuum this using this stopcock. Now the RB is moisture and air free and fully vacuum. After that stop this, and there is an argon balloon and we fill the RB this argon. Now this RB is inert or argon atmosphere, and we use this technique for setting the moisture free reaction or inert condition reaction.
We have here with us Ujjwal Da, who is working under Dr. Jairam Gui. He will be showing us the solvent purification system now.
In this hood we generally do solvent purification and solvent drying. In this first setup, this is a simple solvent distillation setup, where a round bottom flask is equipped with a condenser and a chilled liquid is flowing through this condenser. So if you want to distill some solvent, you put it in this round bottom flask and heat it beyond its boiling point. After reaching its boiling point, it gets evaporated and ultimately it condenses to this round bottom flask, and then we collect the solvent. And here these three is the solvent drying setup. To dry particular solvent, we have to use some drying reagents such as sodium, calcium hydride, depending upon the solvents. Now here, as you see, this is tetrahydrofuran, this is toluene. Both are dried under sodium, and the other one is dichloromethane, which is dried under calcium hydride. And here is also we use the same technique. We heat the solvents using heating mantle and heat it beyond its boiling point, and then it gets evaporated, and ultimately when it gets condensed using this condenser and stored here, and then we collect it through syringe, and that's how we use dry solvent, and that's how we purify the solvents.
So we have with us Ashwata, who is currently working in Professor Joyan's lab. Today he will show us the instrument Epidemic.
This is rotary evaporator. So in this here basically we evaporate solvent from the compound. So here basically compound is mixed up with solvent. So basically this constitutes 4 parts. This is a chiller, this is a vacuum pump, here basically this is a condenser, and this is a water bath. Okay, so now I start it. So here in the round bottom flask we have a compound with DCM solvent. So DCM solvent, the boiling point is 40 degrees centigrade. So that's why we are setting pressure. So I can set pressure here manually. So I am setting pressure, this is 530. Okay, and after that I start the vacuum pump. So basically the vacuum generating, and now I have to start the rotation also, because if you don't give the rotation then it will bump. Okay, so that is used for a homogenized solvent. So basically you are seeing that here after solvent will evaporate here, and here basically this is a chiller connected with chiller. This is minus 2 degrees centigrade. Then it will reduced here, condensed here, and it will finally collect in this envelope flux. Okay, so this is happening here. After that, after compression of that, you can see that there is a compound will be isolated and solvent will be isolated here. So if you want, you can also reuse this solvent, so that can protect our nature also. So that's why this rotary evaporator is using it. So this is a very good technique also.
So here we have joined the day, who is currently working in Professor Jacobian's lab, and now he is going to show us the light experiment.
So this is blue LED, and its wavelength is 456 nanometer. This belongs to visible range. Inspiring from nature, as the organic compounds, organic molecules occurring around us at presence of sunlight, chemists also tried to replicate the same synthesis in laboratory. Therefore, in this process, there are also chemical hazardness, less toxic, and we can also use less harsh conditions. Therefore, and in this process, we can synthesize the chemical compound in different modules. So this is generally the source of photon, which can excite the substrate, or in case it cannot excite the substrate, we add an additive, and it can excite the additive, and this excited state, the additive can excite the substrate, and that the additive is known as photocatalyst. And after the reaction take place, we can monitor it through TLC. This is thin layer chromatography. So to monitor the reaction progress, we need help from TLC, which is thin layer chromatography, which is generally coated with silica gel or aluminum oxide. In our case, this is silica gel. In this case, we just spot the sample of the starting material with which we have started the reaction and the reaction mixture. And at a certain suitable solvent condition, if we run the TLC, as the adsorption coefficient with the silica is different, therefore it will come at different height and different positions. So you can see on UV light, we can spot it there. The starting material is at higher position, at higher RF, and the product is more polar, therefore it interacts with silica more, therefore it is lower RF. The same technique we use in large scale. In case of large scale, we cannot isolate in TLC, there we need column chromatography. In this case, we first pour a cotton, then silica, and then we make a bed of silica, and we will pour the reaction mixture in solid or in liquid form. Then we will apply cotton, and then we will elute solvent. And this is stationary phase, and this is mobile phase. More polar compound will interact more with silica, and it will move less, and the less polar compound will move fast because it will interact with silica is less. And using this principle, we can easily isolate our desired product, and the product will store on those test tubes. Now we have to evaporate that solvent in rotary evaporator to afford the desired product, and it will have to send for further spectroscopical analysis. So in this case, this is my starting material. The spot is over there because this is less polar, therefore it is in higher position. And this is reaction mixture, and this is my new spot, and there is not full conversion, therefore starting material also there. After the column chromatography is done, I have successfully isolated the product. The starting material is there, this is reference spot, and this is the product which has been successfully isolated.
So here we have Monotosh Bhapur, who is currently a senior research fellow in Professor Jacobian's lab. Today he will guide us through gas chromatography.
This instrument is known as GCMS, that is gas chromatography mass spectrometry instrument, and we use this instrument to optimize or characterize products formed in our reaction medium, that is we perform in our laboratory. When we perform a reaction by combining 2 or 3 component there is a possibility of formation of one product, that is our desired product or may not be, or there is a chance of formation of two or more product. When we inject the little amount of the reaction mixture to this instrument, there is a formation, if there is a formation of one product, you will see in the spectrogram, that is there will be only one peak, but if there is a formation of more than one product, then you will see that there are more than one peak. Here we can see that in this reaction mixture there is a formation of two products, therefore there is the appearance of two peaks, and if we click on separate peak, we will get the corresponding mass value formed in the reaction medium. Since there is two different product is forming, so the mass of different component will be different, and that means using this technique we can characterize a compound by their mass, that is m by z value, and similarly we can also characterize their ratio by using this instrument also. Now let me tell about how this instrument works. First of all, we have to send an instrument method, and when you send the instrument method, the temperature of this injecting port will increase from 40 degree, the initial temperature is 40 degree, and it can reach up to 300 degree centigrade. And while it will increase from 40 to 300 degree centigrade, and when we inject the reaction mixture in the liquid form, that liquid will get vaporized, and that vapor phase, that means it is going to the gaseous phase, and that gaseous phase will be carried to the detector by the carrier gas that is used here, inert gas, that is nitrogen. We generally use inert gas, since if we use reactive gas, that can also react with the component and give erroneous result. And similarly, and after going to the detector, it will give such type of spectrum from which we can get the mass of the different component, and there is another detector by which we can calculate the ratio of the different component. Here you can see that there is two ports. One port is connected to the mass detector, and another port is connected to the FID detector, that is flame ionization detector, from which we can calculate the ratio of different peaks. For determination of mass, we have to inject in this port, and for the determination of the ratio of different component, we have to use another port. So this is the working principle for GCMS instrument.
So we are now here at Jordan sir's another lab. We have with us the HPLC high performance liquid chromatography setup, and Orkoda, who is a research fellow under Jordan sir, would take us through this setup and its explaining principles.
So this is our high performance liquid chromatography. In our laboratory we basically use this instrument to measure the enantiomer selectivity of chiral samples, and the basic principle is just same like any other chromatographies. Actually in other chromatographies we separate two different molecules based on their polarity difference using a stationary phase and a mobile phase, and in HPLC we basically need to separate the two enantiomers, and as we know that the enantiomers have similar physical and chemical properties under a chiral environment, so in order to separate them we need to place them in a chiral environment, and that's exactly what we do here. And I can show you that this is basically a chiral column. This is basically a chiral column, which is at the stationary phase is basically tagged with chiral enantiomer-enriched sugar molecules, and when the molecule passes to this column, they get separated and we get peak just like that. As we know that in racemic sample the two enantiomers are in 50-50 mixture, so we can see this from this chromatogram. The two enantiomer is in almost equal area, that is 50-50 mixture, and when I put an enantiomer-enriched sample of the same molecule, we can see that one peak is in large and another one is small. So the difference in area of these two peaks is basically known as the enantiomeric excess. Basically, as we know that in racemic sample the two enantiomers are present in 50-50 mixture, and from the picture we can see that the two enantiomer are in 50-50 ratio, and whenever we put an enantiomer-enriched sample, one enantiomer is in large excess than that of the other enantiomer, and the difference in area of these two enantiomer is known as the enantiomeric excess, and that's exactly what we measure in HPLC.
We have here with us Dr. Surajit Sinha, Professor in the School of Applied and Interdisciplinary Science. His major research work is in organic synthesis, chemical biology, drug discovery and delivery. His specialization is in morpholino delivery against the cancer cells and muscular Duchenne dystrophy cells. Sir, we would like to ask you further about your research work. So can you elaborate it?
Actually, we have been working in the area of chemical biology, that is broad area. So actually we are trying to target disease, particularly genetically disordered diseases where genetic defects are involved. So our approach is to design antisense based technology which can target the wrong mRNA, and then wrong mRNA if you block, then it will eventually block the functions of wrong protein. And you can understand if you block the functions of wrong protein, and then you will have a therapeutic efficacy of the particular drug. And what is antisense? Antisense basically it is a short stretch of DNA or RNA that is 20 to 25 mile long, and that targets mRNA through Watson-Crick base pairing. It blocks. Now we specially working on antisense compound that is called morpholino oligonucleotide. Now as far as drug development is concerned, perhaps you know that drug which has molecular weight higher than 600 is difficult to deliver in the biological system, because those high molecular weight drugs are not penetrable to the cells. Therefore you need to have a delivery vehicle, and it becomes notorious particularly for biologics. Biologics means biological drug. Biological drugs, what are those biological drugs? Like a peptide, DNA, RNA based drug, protein based drug. As you know today that people are talking about my mRNA 1273, that is a vaccine for COVID-19, and that is actually developed by Moderna. So how will you deliver such type of long complex molecules in the body system? Unless and until you have a delivery vehicle, suitable delivery vehicle, it will not reach to the target area where actually it should show its therapeutic efficacy. And in this direction we have been working for several years. And genetic diseases is very, you can say that it is very difficult, it is complex disease. So what happened, that is particularly we are working on area that is called neglected or orphan disease. Neglected or orphan disease, actually you can say almost there is no medicine still today. So cancer, you know, medicine is there, but even you know that those medicines are not good for the treatment of cancers. But what is the solution? Therefore you can say it is a big problem, complex problem. So we have been working in this area to solve or to bring the therapy against the treatment of this type of, all these type of genetic disorder diseases. And among them we have applied one RNA based technology that is used already. I will tell you, I am glad to tell you that very recently our drug controller of government of India, DCGI, gave approval for the treatment of Duchenne muscular dystrophy. Duchenne muscular dystrophy is a type of disease which actually the most of the boys are affected with this disease, and they do not have a protein called dystrophin, and dystrophin protein supports the muscle. Now this area we have been working, and one drug recently it has been approved, and many more things need to be done. We are, you can say, still it is in the premature stage, but our research actually we are in that direction we are doing this research.
Thank you, sir. It is an interesting area of research which you are doing here. Sir, we would like to ask you to show us the working of the lab and how the different instruments are working and what are the areas in this lab we are pursuing, and sir, you can take the help of the scholars. And
so actually this is the laboratory. We are, as we are working chemical biology area, so we have two groups are working in my lab. One is one students come from organic chemistry background, and another area students come from biology background. And this lab where I am standing now, this is the biological lab where we are working molecular biology research, and actually my students here are standing, so we please come here. Yeah. So Chandra actually is doing PhD under me. She is going to submit her thesis. She almost completed. and she is working in that is anti-sense based therapy, and Dr. Ujjwal Das, he did his PhD in Calcutta University and he has joined under me as a research associate. So he is working now in this lab. So I think you can show,
we can show the
instruments to the students, that is what are the instruments we have and the purpose of these instruments.
So like sir gave a very nice introduction about our work. So basically what we examine is that the different expression of the proteins after the addition of the compounds that are being made in the chemistry lab. So to check the expression level of different proteins, the main instrument that is being used is this ChemiDoc machine of Biorad company. So what do we do here? This is used basically for the development of the membrane in Western blot. So what is Western blot? Western blot is a technique by which we can measure the level of protein expression in case of cells. So this is a wonderful machine that helps us a lot in case of the development of the membranes. And this is a centrifuge which is of Eppendorf company. So this is used for basically for centrifugation of the cells when we want to separate the supernatant from the cell pellet. So we generally centrifuge them. So here we can control the temperature as well. Like if we want to, since proteins are stable at cold temperature, so if we want to centrifuge at lower temperature, so this machine is of great help because it helps us to centrifuge at 4 degrees centigrade. So this is also a part of our Western blot technique, which is used in case of centrifugation of the cells. And this is a PCR machine, that is polymerase chain reaction machine. This is also of Biorad company. So basically this is used in case of amplification of the DNA. Suppose we want to make more and more copies of a particular gene of interest. So how can we do that? By amplifying that particular segment of gene. So that we do in this instrument, that is polymerase chain reaction. So this is a luminometer. So when we want to measure the expression of a luciferase gene, so luciferase gene is basically light emitting gene. So for example, we want to see the expression of a particular transcription factor. So when the transcription factor gets activated, the downstream luciferase gene gets transcribed. So in that case, the light gets emitted and we can measure that light in luminometer. So this is basically a luminometer by which we can measure the expression of luciferase assay. And apart from that, here we have another transblot machine that we use for the Western blot purpose for the transfer of the bands from gel to membrane. This is a dancing shaker. As we can all see that it's moving right now. So we are basically trying to incubate the membrane with this particular liquid. So since we want a uniform distribution, so that is why this dancing shaker is used. This is of great help. And this is also a similar kind of a shaker which tilts side and on both sides. So this is also used for shaking purposes. And this is basically the instruments that are mostly used. Apart from this, we have a cell culture lab where we culture the cells. So there we have our incubators, the laminar hoods, and separate setup we have for cell culture. So, and this is the basic setup in our molecular biology lab. Thank you.
So we have with us Professor Subroto Ray of School of Material Sciences, IACS, Kolkata. We all know that material science is an emerging field of study and it's very interesting. Today, Sir will share various aspects of material science on which his lab is currently working.
So I've been asked to share a few ideas about material science, and it's always a confusing area, especially for the younger people. What we find, people with interest in physics, people with interest in chemistry or in biology, they always come and ask, what is material science? It's biology, or it's physics, or it's chemistry. And the answer is a puzzling one because even we do not know what it is. But at times, I think everything comes into play in the research of material science. And it's known that at certain level of scientific research, this demarcation of subjects are often blurred. So in material science, we do physics research on materials, we do chemistry type research on materials as well as on biology kind of research. So in my laboratory, my training had been in solid state and structural chemistry unit of Indian Institute of Science, Bangalore. And I essentially did all my work during PhD and also in postdoc on oxides and essentially condensed matter physics, strongly correlated systems, magnetism, ferroelectricity, multiferrocity, etc. So I continued to do similar kind of things after I came and joined here in 2007. However, things change. I mean, subject topics change. And last few years, we had been working on iridium-based systems, quantum spin liquids, very beautiful names essentially, but also very important science-wise. The idea of quantum materials is extremely important in today's world. So our group started working on iridium-based systems, quantum spin liquids, and things like that. However, when the students told me to participate in this particular discussion, they gave me a little brief of the questions they have, and they wrote a beautiful thing. It reads, your lab has got a very intriguing description. Water spin asymmetry disorder. I think that it's there in the top of my homepage somewhere, right? So, and you have seen a picture there in the homepage, right? Yes. So that's a picture, it's a painting done by a famous French painter, Claude Monet. So basically, I just took the idea of making that homepage like it's quantum spin liquids, and then from liquid I went to water. And when I go talk about water, of course, one doesn't do, at least I am not doing physics of water. Actually, sometime in 2010 or so, I essentially thought of, a few of us actually thought of doing things which has some simpler idea of science and which has some importance of on human life. And based on that, we started thinking of completely different area of water purification, which involves a lot of chemistry instead of the physics that I had been doing all along and am doing right now. And in that, we did certain things. We tried to play around with few things. And what we realized is that there are a lot of interesting materials science or even materials physics to be done on water-related problems. For example, we try to use the idea of mineralization to trap contaminant ions in a permanent fashion. Minerals, everybody knows, is a core of nature. So we just try to trap contaminant ions like arsenic in mineral structure. And then when we get, so essentially my training is to handle solids. So as soon as I find a solid, be it arsenic, be it iron, be it iridium, I know what to do with it, and I just play around. And the idea of asymmetry and disorder is a very material science specific thing, because in solids, in textbook, one draws beautiful structures and pictures. But in reality, what happens is all entropy related factors never allows nature to really settle down to that beautiful picture of the structure. You always have certain disorder, you always have certain elements, certain atoms sitting, changing their places, making some bond angles a bit higher or lower, making certain distortions. And it's these asymmetries, these kind of disorders often affect the properties of the materials, and it's very fascinating to study these, and it's even more important to learn about them and at some point of time even think of manipulating them for our own advantage. So these are the kind of things that we had been doing in IACS for last, I don't know, 14 years or so.
So here we are in a lab which is used for the material science, and today we will be having some live demonstration.
This is an instrument called XPS, or X-ray photoelectron spectroscopy. It's an extremely useful instrument to learn about materials, and it's largely used in material science. And this is based on photoelectric effect as discovered by Albert Einstein. It's based on that. It's a complicated looking instrument, and it works in under ultra high vacuum of 10 to the power minus 11 torr. So it's an extremely difficult instrument to maintain and an extremely useful one. And you can see that right now here's Mr. Bhomik, who is the operator of this instrument, and you can see that nickel metal is being studied, and one can see these peaks of nickel 2p core electron levels. So that's the kind of experiment that does. It's a very involved experiment and a very useful one. And the whole system is under very strong vacuum. So the thing is, it's never possible to, you cannot just take thing and put inside it. You cannot break the vacuum. So keeping the vacuum, there are ways by which one can move the sample inside the chamber. So that hole is basically a gateway to this chamber, which using this, you can move the sample to this chamber, and from there you can move the sample to this chamber, and then we do the experiment here. That's called an electron analyzer, and it's called a monochromator. So everything is under a huge vacuum. You can see the number there. It's 1.1 into 10 to the minus 10. If you can think of atmosphere.
We have Professor Tapun Kanti Pain with us, School of Chemical Science. Sir, I would like to request you the field of bioinorganic and biomimetic chemistry on which your research group is currently working on, and your research works.
So primarily my research group has been working on several projects that includes like bio-inspired chemistry, biomimetic chemistry, and bio-inspired catalysis. So just to give you a brief outline of what exactly that means. So it's basically, you know that metal containing proteins, particularly in biological systems, they use oxygen for aerobic organism to catalyze many oxidative transformation reactions that are metabolically relevant, and that take place with a very effective way in biological system with very high turnovers. So these enzymes, primarily iron-containing enzymes, where my research group is interested in. These reactions take place in biological systems. But being synthetic chemist, my research group is primarily involved to develop synthetic models. So what we do in that case, we just look at the enzyme and then try to emulate the structure of the enzyme and then see whether the synthetic systems work the same way as that of the biological enzymatic systems. And then we try to understand the mechanism of the reaction, which in turn not only help us to understand the reaction of the biological systems, but it also help us to develop bio-inspired catalyst, because you know that enzymes are catalysts and they are biocatalysts. So inspired by the biocatalyst, we try to develop synthetic catalyst, which will have implications for doing transformation reactions in industrial system. So that's basically a bio-inspired catalysis reactions, and the model compounds are actually called the biomimetic models.
As we know that there is another part on which your group is working, that is the oxygen evolution and the related chemistry. So can you please explain something regarding that?
My group is not really interested in doing oxygen evolution reaction, but what we do is try to understand the oxygen activation chemistry. Because all of you know these basic principles that triplet oxygen, which is from air, is actually kinetically inert. Although the reaction of the organic compounds with oxygen is thermodynamically favorable reaction, the reaction is kinetically sluggish. It's because of the energy gap between the singlet oxygen and triplet oxygen is about 25 kilocal per mole. So the relatively non-reactive triplet oxygen needs to be activated. So these synthetic compounds that we develop, akin to the biological catalyst, these compounds activate oxygens, and then the oxygen undergoes different reductive steps, and so therefore that's called a reductive activation of dioxygen, and then it generates different metal oxygen intermediates. So we try to understand the electronic and structural properties and reactivity of those metal oxygen intermediates. Because these metal oxygen intermediates have been implicated as the key oxidizing agent in enzymatic reactions. So for that purpose, we do synthesize the metal complexes, try to activate oxygen, trap the reactive intermediates, and then characterize those intermediates upon trapping at very low temperature, and then subsequently they are subjected to different spectroscopic tools. Okay, so this is a very typical synthetic chemistry laboratory. As you can see, the students are working here, and these are like wet laboratory. We have a standard instruments that are regularly required for carrying out experimental research, and these are the hoods where they perform the synthetic chemistry. Some of the regular and simple instruments are there on that island bench. And now here, this is actually a kind of, I call it a bread and butter for our group, because this is called an inert atmosphere glove box. And as I was telling a few minutes ago, that we synthesize a lot of metal complexes that are reactive towards oxygen. So we cannot make those compounds under oxygen. So we have to prepare those compounds under inert atmosphere, and this is actually an inert atmosphere. So air sensitive compounds are actually prepared inside this box, and all the manipulation and their storage are done here within this box. In fact, we have a low temperature facility inside that, where at minus 40 degrees Celsius, we have a freezer there that is utilized for the crystallization of the compound, or even sometime we purify some of the compounds by doing normal crystallization also within the box. And here, as you can see, that this is a display unit which actually shows the amount of oxygen present in the box. And for our work, that oxygen content should be less than 1 ppm, and that shows up here, and the vacuum and other things. And so when students use this, so basically what they need to do is basically they just have to take the hands here, and okay, so let me show you how this is done. We can actually do the reaction here, and then once it is done, something needs to be taken out. You can use this thing. And then using these chambers, which are called antechambers. So this is actually a big antechamber, and this is a mini antechamber. So for big things, you need to control this antechamber, whereas for the small things, you need to utilize this antechamber. And this requires a lot of very careful handling of the equipment. Otherwise, oxygen will get into there, and then it will actually destroy most of our synthesis and efforts involved in the synthesis process. Okay, so here in this instrument room, here you see that this is something called UV visible spectrophotometer, but with low temperature crash state facility. So using this system, what we can do, we can actually measure the kinetics of a reaction, particularly the kinetics for very fast reactions, like in the second scale reactions can be monitored. So, and that can be done not only at room temperature, but that can be done at very high temperature as low temperature. So we can go up to minus 110 degrees Celsius. Depending on the nature of solvent, you can utilize this. So for cooling purpose of so this is actually the spectrophotometer, which is actually the detector is a diode array. So as you understand, the diode array detector is utilized for very low range of time window by which you can actually collect the data for every. So the minimum time limit is 0.5 second. You can actually get one spectrum. And what we use is liquid nitrogen. We use it as a coolant. And this is actually the controller unit for the temperature. We set the temperature here, and depending on the requirement, the liquid nitrogen is sucked from this liquid nitrogen container. And here is the sample holder, and that actually keeps the temperature. The advantage of this particular facility is that you can do kinetics at very low temperature without any fogging problem, because the problem is that when you have a lot of moisture, and if you have an open kind of cryostat there, so air will go there, and the moisture in air will go and condense on the wall of the the path, and therefore you don't get a good baseline. Every time you will see that spectrum will keep on going. That intensity goes on increasing, and by this one there is actually a closed system, and we have actually connected with the nitrogen gas. So what it does, this nitrogen gas pushes the oxygen or any moisture from around the surroundings, and therefore nothing can be condensed. So this is what the spectrophotometer does. Here we do primarily for the kinetics at low temperature. And this particular equipment is called gas chromatography mass spectrometry facility. So what this is particularly used when you do a reaction. You might sometimes get a mixture of compounds, but sometimes they might be unknown compounds. So what you need to know its mass, you need to know its other characters, like exactly at what time it is going through the column, because chromatography is something that separates different components in a mixture. And in this case, what we do when we inject the sample gets evaporated in the gas phase, and then in the gas phase this goes to it moves in through the column, and then once it is separated from the column at a different time interval, it is subjected to the mass spectrometer facility. So this is the gas chromatograph part, and this is the mass spectrometry unit, and these two are connected. And here you have the mass detector that detects the mass, and then you know that what is the molecular ion of the compound. So for not only for the known compounds, even for unknown compounds also, you can separate, you can find its mass from the mixture of solution. So this is precisely a very useful equipment for any kind of synthetic chemistry. Whenever you do catalysis or any other things, this is really very, very important. So this is facility is called NMR facility, and this facility is an institutional facility under the Department of Center for Scientific Service. And what we have in this facility is these 3 NMR instruments. The only difference in these 3 equipments is nothing but is basically in their frequency. As you can see, that this is an old one which actually has a 300 megahertz NMR instrument. This is a 400 megahertz, and this is a 500 megahertz equipment. We also have recently procured a 600 megahertz NMR, which is going to be installed soon. Now talking about this, the general, as the name indicates, nuclear magnetic resonance spectroscopy. So here what we do, you basically utilize the nuclear spin. So probe the nuclear spin of atoms in molecules, and then try to understand about the constituent of the molecules and the different atoms present there and their orientation in 3-dimensional space. So the thing is that the difference between the three are nothing but the resolution, because 300 megahertz, 400 megahertz or 500 megahertz, whatever you use, you get the same information, but what the difference is nothing but you basically have the resolution in the spectrum. So here we probe different nuclei, not only the proton or carbon, which are very standard that are done in everywhere, but we also have probes like if you have fluorine in a molecule, what are the different types of fluorines present in a molecule? That can be done by 19F NMR spectroscopy. Then we have solid state samples we can do. You do not necessarily need always solution sample in deuterated solvent, but you can utilize, you can use solid samples for the measurements. And then also we have other nuclei, and not only that, not only the organic compounds, but you can also measure the magnetic or the magnetic resonance spectrum of paramagnetic samples also. So paramagnetic samples means inorganic compounds, and if you have unpaired electrons in inorganic compounds, that gives rise to electron spin, and then electron spin nuclear spin interaction can also be probed by this. In that case, the spectrum is not that simple as like the proton NMR spectrum, where you are used to see the spectral region between 0 ppm to 15 ppm, but there you can have from minus 200 ppm to plus 200 ppm or whatever, because of the line broadening, due to the paramagnetic center present in that molecule. So this is actually a very, very powerful tool, not only for the organic chemist, but also for inorganic chemist, for material scientist, for biological research. These are the very, very important facility. And we are actually very proud to have this facility, not only one equipment, but all sorts of equipments that we need for our present day research here at IACS. And subsequently, you will definitely learn these things in the course of study. You have to come here in this room to analyze. So our students also run their, that instrument is purely dedicated to the students so that they run. And these two equipments are run by our expert people here because they are pretty sensitive. Particularly this one is very sensitive. And we also have, you can see, that auto sampler. So at the end of the day, the rest samples that we have, we just put together, and in the morning all of them will be done, because this is actually a robotic systems that are attached to with that. So no samples will remain, remain like that. So yeah, it's a very unique facility that we have, and yeah, that's all. Thank you.
Professor Nina Gupta. He is a well-renowned physicist who has contributed greatly to the field of gravitational cosmology and high energy physics. And sir, so I would like to turn to you now, and I would like to ask you that what are you currently working on? Can you just let the audience know in a few words?
Right now, I'm working in the field of primarily in the field of gravitation, where the gravitation has various aspects. The cosmology, astrophysics are the two broad areas, where in astrophysics we work at the scale of interstellar objects. I mean the stars, planets, in the very common sense language. And on the other hand, cosmology deals with the universe as a whole. So these two, in these two arenas, gravitational force plays a very, very important role. Now gravitation actually interests me a lot for quite some time, because this is one of the force that is most abundantly can be seen all around. And in fact, I would like to tell you that one day you can think that if there was no gravity, what would have happened in this universe? And you will then realize the importance of the force of gravitation. Now, gravitational force essentially deals with it's a kind of attractive force. You have studied in the class, and Isaac Newton gave the first description of gravity through his laws of gravitation. And then it was extremely successful in explaining planetary motion around the sun, and then of course some other astrophysical phenomenon. But then subsequently, Albert Einstein, who made a revolutionary contribution in bringing in new ideas about gravitation, and where he explained gravitation in the language of space-time geometry. Now then that theory, of course, met with enormous success, more success than Newton's theory, but then it encountered a serious problem, and then now we have a strong reasons to believe that Einstein gravity, despite its success, it has a substantial limitation, and it cannot be the final theory of gravitation, and we need some more correct, complete theory. And one of my main objective of my research is to look for gravitation beyond Einstein. That is, the theories, the models, various proposals all across the world. There are hectic activities to look for signals of phenomenon which implies that there is a gravitational theory which cannot be explained by Einstein gravity. And in fact, through that probably we will be able to understand what that new direction should be. So this is one of my very primary area of interest. In this institute, we have formed a gravitational research group. It's called Gravitational Research Center at IACS. And there we have right now 2 faculty members apart from me, Professor Shumanto Chakraborty, and we have several PhD student postdocs and many people from other institutes. They are affiliated to this center directly or indirectly. So it's a very large collaboration within the country, even outside the country. So these are some of our objectives, and I would also say that our research essentially comprises of, while trying to understand from a theoretical point of view what could be the more correct theory of gravity, also we are very seriously taking into account all the observational aspects of gravitational physics. And one of the main observational aspects in recent times relating to black holes are one of the accretion phenomena around black holes, where the various gases and masses are accreting towards black hole because of very strong gravity, and that can be observed through the telescope and we can have data. And from that data we can understand that the gravity near such a high gravitating object like black holes actually follows Einstein theory, or it tells us beyond that. The other thing is that related to black holes and maybe some heavy stars like neutron stars, they recently discovered gravitational waves. Now all of you know that gravitational wave has been detected recently, and it has created a sensation that apart from electromagnetic wave, now we have another wave which is called gravitational wave, which we have discovered through a very interesting instrument called LIGO in United States. And this research is going to occupy a center stage in the coming days, because India is also building up a kind of laser-induced gravitational spectroscope, where this is a huge instrument which actually catches the arrival of gravitational wave by the collision of big objects in the sky. And from that data also we are trying to explore whether we have gravitational physics beyond Einstein gravity. And also we are doing research in cosmology, which is called the universe, the physics, the early phase of the universe at the time of Big Bang. So what happened at that time, whether the observations that we have, that also encodes the gravitational theory, which is not Einstein but something more than that. So that is one aspect, and the other from as I said, from theoretical aspect. So these are the main 2 focal areas, but of course my original background was from high energy physics, so where it is opposite, the microscopic particles, their properties and everything. So there also we certainly we are exploring various aspects of particle physics, its interface with gravitational physics. So these are also our area of interest.
Now, sir, I would like to ask you that what can students do to further cultivate their interest in science, or students who want to pursue science in their future careers? How can they develop a research-oriented mindset, especially in the college years?
See, the students, as you know, that when you enter a college or university, there is a prescribed syllabus which all of you will study, and you will take one of the main courses like physics, chemistry, biology, mathematics, according to your choice. But the whole idea is that, see, the syllabus, the examination, these are important. You have to take classes and appear. So there is a structure of that. But beyond that, you should understand the science is basically, the objective of science is to explain nature around you. And in order to understand nature around you, you have to be extremely curious. You should have that inherent curiosity of anything happening around you and trying to explain through your scientific knowledge and understanding. So science at this level, has become extremely collaborative, and you cannot do science sitting alone. So for this reason, even from at this age, all of you should learn to interact with each other, learn from each other. This is very important. It is not that you always need to go to a teacher. You can learn from from your friends, from your peer group. So for that reason, even beyond class hours, beyond your syllabus, you have internet, you have all the, you are so well informed, you know so many things are happening. You should try to interact regularly among yourself on various topics and try to read them without thinking about the syllabus. Try to read, go deep inside it, and you will see that you will see that there are many problems at that level, at a very usual the syllabus level, where so many things are unknown. So in order to do research, it is not that you have to do something very exotic. Even within your curriculum, you will find that so many interesting things which have not been explained so far. So you can try it out. That will give you a flavor of research. You can just try it out. I remember that, when earlier I was teaching in Presidency College, and then after several years I joined Alpur University, where I taught for several years. I had some wonderful students during that time, and they are all now faculties in various places, in big places in US or here. So even at that time, they used to come up with questions which we used to discuss. Of course, you discuss among yourself, and then we are also here, so you can talk to us also. And many of my students who even at that level finally could solve a problem which got published in well-known journals. And that gave them a research-mindedness which is very different from your usual study. The usual study you will do in any case, you have to read. But in addition, you should have that research orientation. And in this institute, of course, you have an advantage that so many people are doing so many different kind of research, so you can go and talk to them straight away, just out of your curiosity, that what are they doing? So many seminars happening. Even if you don't understand, go and attend them. And you can try to arrange student seminars. That is, you can find out some time in a week where you will organize seminars, where you will attend and some of you will speak, maybe occasionally we will also be there. You find out some topic which appeared somewhere and say 3 of you form a group and read that and report it in front of your friends, and then maybe next week's other 3, so you can rotate it among yourself. And you learn in the process how to read something unknown, how to give talk, lecture about that, and how to debate, how to discuss, how to question. So these will create that bind inside you, which eventually will help you enormously to do research. So I think the students should involve themselves collectively in various kind of activities that I was suggesting, and that eventually is going to help you in a big way.
Hello students, thanks for inviting me for this seminar. On behalf of the School of Mathematical and Computational Sciences, I would like to speak about how computer science could relate to our life and how it can be useful to us. Many of you already know about how to write programs, and some probably don't. But I won't be talking about coding, because computer science is not only about writing programs. So let's start with an example, a very interesting one. So some of you might have heard about an US company named Enron. In the 1990s, it was one of the biggest companies in the world. It was very lucrative for anyone to work for them. Forbes once declared Enron as the best company to work for. Suddenly in 2001, Enron filed for bankruptcy, and many accounting and insider trading frauds were unraveled by FBI. Initially, when FBI came to know about the fraud, they thought of building a network of the important persons inside Enron who would be sending emails to each other. So let's first have a look at all the newspaper cuttings that I could find. So Enron was bankrupt then. So now, this is the Enron email network where we can see senior management individuals, almost about 150 of them, and email interaction or email communication between these users. So this network helped the investigators understand who were the masterminds and how the fraud was done. In order to understand such networks, maybe we should try to have a look at a smaller social networks where we would try and understand who are the influential individuals in those social networks, and what are the components and the features of the social networks. So this is a typical social networks. Here the small points or the small black circles are the individuals, nodes in terms of computer science, and the interactions between them are known as the edges. As you can see, some regions inside this network, they're very dense, and most of the parts are very sparse. And you could also see individual nodes who might be influential inside the parts that are dense. The dense groups are known as community substructures. The edges inside the communities are called strong ties. So you can see here the influential, the strong ties, and the weak ties. So the weak ties are inter-community edges. Strong ties are intra-community edges, the ones that are inside the dense structure. Okay, so weak ties are very important actually. Weak ties are important because if a piece of information wants to flow from one community to another, then the weak ties are very important because they might be the only way the information could flow from one community to another. Okay. So some other definitions where we could see directed graphs and undirected graphs. So directed graphs are networks where interactions are not symmetric. In undirected graphs, the interactions are symmetric. So in undirected graphs, role is not important in the interactions that the individuals are trying to make, but in case of directed graphs, the roles are inside the interaction is important. Okay. So now the important question, which nodes are important? Given a social network, how do you understand which node is important? All right. So it all depends on the context. One easy way is to say that a node is important if it is connected to lots of nodes. In this case, the context is known as a metric named degree of a node. Okay, so degree essentially is nothing but the number of interactions in which a node is involved, which is something very similar to how many friends you might have in a social network like Facebook. So your friend count is your degree in Facebook. Okay. All right. So the next slide is something where we could see some fun. So a TV series, a very famous TV series, the prediction of turn of events could have been understood from the social network of the TV series, where you could see the individual characters of that TV series, they're interacting with each other. So here is the network, and the TV series, as you can understand, is Game of Thrones. Okay, all right. So in Game of Thrones, you can see the community structures clearly. By analyzing the network, the nodes in the same community, they have been colored with the same color. Unlike me, if you want something more serious, we could move on to something more serious. So what this might be, this, as you can see, is lots of amino acids interacting with each other. I mean, it's very hard to see from here, but if you can zoom on a certain part, maybe a certain portion, so if we follow this portion and if we try to zoom on it, you'll be able to see this. Alright, so now you can see the codes of the amino acids, and you can clearly see that these are the interactions. Okay, so the free energy actually mentions the strength of the interaction between two amino acids. So this is the sort of social network of the interactions between amino acids in ORF3A protein in SARS-CoV-2. Okay, so lots of information could also be found from here, that which amino acids are interacting more frequently with each other, what are the strength, which part is denser part, what is happening in those parts, etc. Okay, so now we go to something called degree distribution. So in a graph, the frequency of occurrence of degree values in nodes is depicted by degree distribution as shown here. In a random network, it is usually characterized by Poisson distribution. So which means that smaller degrees will be lesser in number, larger degrees will also be lesser in number, medium sized degrees will be the most. Okay, but social networks are not really like that. So in social network, you will see that very large degrees will be very less in number. Only very less number of people will have so many Facebook friends. Okay, and less number of Facebook friends, people who do have less number of Facebook friends will be more in number. Okay, they will be more in number. So this distribution is called power law distribution. Once again, which says it has very few nodes with very high degree and most of the nodes have very low degree. If you think about Zomato restaurant review networks, how many individuals would write reviews every day? But some people are there who actually do that, but they are very, very less number, right? Very, very less number of people would write every day. Okay, so I think I'll end by moving to the next part. In this part, we see an interesting metric which can be used to understand who are the influential individual inside a social network. All right, so this is known as PageRank. It was invented by Larry Page and Sergey Brin. Initially, it was used for Google search engine, which used to measure the importance of a web page. The essence of the definition of PageRank would be something like this. So it basically says a web page is important if it is connected to important web pages. What? So essentially it's a recursive definition. So it defines importance based on importance. Alright, so it is essentially a recursive definition. So we could have a look at how to calculate PageRank actually, and you'll understand. So I have a few pictures of Larry Page and Sergey Brin. In 1998 they came up with the algorithm, the the Google's PageRank algorithm. And this is a picture of World Wide Web, which shows many web pages which are connected to each other. So from one web page you could go to another web page, and hence they are interacting with each other. All right. So for PageRank, we would first maybe try to understand how the connection between web pages would work. Say if you are on the blue web page, then in the next step you could go to either the yellow web page or the smaller red web page or the green web page. All right. So 3 possible directions, and a normalized PageRank value for the same picture would be something like this. All right. So essentially these two are same pictures, but it would say these are the normalized PageRanks, and you can clearly see that the red one is the most important node here. And since the most important node is the only neighbor of C, C is also very important. All right. So this is how it works. So now let us try to see how it is calculated. But first things first, in degree and out degree. So the count of incoming edges would give us the in degree, and the count of outward edges would give us the out degree value. So let's go to a very small example where we could see a graph of 4 nodes. So if we want to calculate the PageRank, we have to initialize the values with something, right? So what could be an interesting value? If you start with 0, it hardly makes sense. So here we have to calculate PageRank of any node by summing up the influence that it is getting from the adjacent nodes. So like if we try to calculate for A, whatever influence C and D imparts, the sum of those influences would go to A. All right. So if we think of starting by initializing all the nodes with 1, then in the next step, in the next iteration, A would become 2, right? Because A is the influence of C and D is coming to A. So C is also 1, C is 1, D is also 1. So C plus D would be 2, right? And very similarly, if we talk about D, so you can reach D from A, B or C. So it's going to become 3. All right. So in the next step, from that structure, you can keep increasing, and it keeps increasing unboundedly. So if it is increasing unboundedly, that doesn't seem really right? Because if it increases unboundedly, it will reach infinity at some point of time. It's not going to stop really. All right. So why don't we make a sum of probabilities of the randomly moving, say we think of one person who's moving from C to A to B to D. So if that person is known as the random surfer, then can we not use the sum of probabilities of the random surfer reaching all nodes to be 1? All right. So if that is the case, then we would try to initialize or choose the initial values where the sum of probabilities from each node will be 1. All right. So if the total sum of probabilities over all nodes would be 1, and if you have 4 nodes, then all the nodes would get 1 by 4, right? So now, even if you keep adding now you have A has half, C has half, B has 1/4, and D has 3/4. So the sum would still become 2, right? So if it's 2, the overall sum is not 1. So we have to not renormalize it. So if we renormalize it, this picture would become something like this. It was 1 by 2, which will become 1 by 4. 1 by 4 would become 1 by 8. 1 by 2 would become 1 by 4. And 3 by 4 would become 3 by 8. Alright, so it's like this now. So we keep adding and we keep renormalizing. So these process will go on and it would converge at some point of time. So now question is, can we formulate it using some linear algebra? Can we use linear algebra in order to make it a little easier? Yes, we can do it. So what we can do is we can have a transition matrix. So the transition matrix you could see, which is actually a column stochastic matrix. So column stochastic matrix is one where the sum of all the values in one column would add up to 1. So this is a column stochastic matrix, which is the transition matrix. So first column is 0, 1 by 3, 1 by 3 and 1 by 3, because if you think of it, from A you could go to B, C or D. So from A, the chance of going back to A is 0. Going to B is 1/3, going to C is 1/3, going to D is 1/3. That's why the first column is 0, 1/3, 1/3 and 1/3. Alright. So the definition, the recursive definition of page rank at iteration I would be the transition matrix into the page rank of I minus 1. Okay, initially, so essentially we have PR1 equals to the transition matrix into PR0. PR0 is the initial state where all the probabilities are equal and some of them would be 1, right? So if we keep multiplying this, at some point of time you will see at PRI it's not going to change anymore from PRI minus 1. So if PRI minus 1 and PRI are almost same, then you stop at that point. Alright, and you have your final values. So I will end at this point. I think I have said quite a lot about graphs. So this is our computer science unit, and we have 3 assistant professors working on formal verification artificial intelligence, which is Rajoshi Rai is working on that. I work in machine learning graph algorithms. She works in machine learning, deep learning, etc. So if you are interested, please feel free to email us. All right. Okay then, bye, thanks.
So after a long day's program, we finally come to the end of National Science Day 2021 celebration. So it was a long event. We had talks, we had presentation sessions, we had then the live telecast of a very nice documentary which we had shot in the IACS some days back. So that's all for today. We really hope that next year we see each and every one of you in person, in offline mode, where we will be having talks, demonstrations in person at IACS. Okay. Thank you so much from everyone. Thank you. Bye.
In the meeting.